Great, wonderful. It's great to see you here. Good morning. This is Focus Meeting 5, first session with a lot of music. No, stopped. The future of radio astronomy in an increasingly crowded spectrum. So, yeah. I'm trying to switch. Thank you. So we built these million euro currency facilities. And million, whatever, I mean, choose your currency for facilities. Next slide bit, please. It doesn't work. And it's a good thing that I'm trying this. There. At the same time, a lot of our spectrum is occupied with what we call RFI. So now, if you look at this blue stripe there, this is actually what we, or is allocated to radio astronomy, this blue stripe. And the rest of the spectrum is basically by international treaty not allocated to radio astronomy. So in principle, we are the only ones who are talking about radio frequency interference if we see these radio lines that occupy all of our spectrum. This is regulated by the International Telecommunication Union, regional and national administrations, and of course, spectrum managers. So these are the specialists that are dealing with spectrum matters within radio astronomy. They talk to the regulators, they talk to the industry, but we need you to work with. And this is what this Fox meeting is about. It's to give the public and the regulators an idea of what we are worth, what we are doing, how essential we are, what our needs are. And that gives us, as the spectrum specialists, the means to talk to the regulators, to the officials. In parallel, there will be a white paper that is being written, and many thanks to all of you who contribute to this white paper. Many thanks to people who are here. One of the topics is which lines or which portions of the spectrum are important. If you ask a radio astronomer, the answer is very clear, all of it. But we have to choose. And this is why regularly we need to review which portions of the spectrum are important. It's one of the lines of work that we have to do with the astronomers, pure astronomers. So it's about informing astronomers, us, informing the spectrum managers about what astronomy is about or is doing. And then we use these results hopefully in the harmonization process. This is about networking. Please, let's talk to each other. As I mentioned, the white paper, if you're interested in that and you're not yet involved, please contact me. Just to test this, there is a challenge. And the prize is one of these CRAF Committee on Radio Astronomy frequency pins. If you participate, just check it out. It's also on the Slack and coming to the Slack. So this is the program. We have many disciplines in radio astronomy, many disciplines also dealing with the protection of radio astronomy. And this is all interwoven in this FM5, which is why the program is pretty tight. I'm sorry for this, but it's very important to have all these aspects covered. So there is a Slack to communicate. Please post your questions there. Please visit the posters, have a look at them online. And at the end, you can also contact me. Again, questions earn you as long as stock lasts one of these Committee on Radio Astronomy frequency pins. It's the only thing that I got here. And contact me if you have further questions on all this. And finally, I have to thank the IAU for recognizing that this is a very important topic, and all of you for coming and contributing. And yeah, with that, we step to the next talk. Chris de Boer. Are we? Yeah, no, I think they are sorted out.
They're mostly my technical difficulties, I
okay.
think, with my computer. So I get to use my laptop. I'm not going to use that. Apologies for that. Now I need to find the screen to share.
So our first talk will be on SETI by David de Boer. Thank you.
There we go. All right, with some technical difficulties there, I think we've started. So I'm going to, I guess, preface the things, start the day. We're talking about technosignatures, which is arguably one of the most insidious ways that RFI can impact us. And I take Josh's point very well. We call it RFI, but to be clear, it's us that's kind of going in on other people's territory. So but I'm going to use the word RFI for short because from us, it's interference. All right, so what is a technosignature? I think everybody knows by now. We've kind of gone with technosignature over SETI, which is typically what we've called the field for the search for extraterrestrial intelligence, for two reasons, really. One is that we're not necessarily searching for intelligence because that is some sort of value judgment. We're actually searching for the manifestation of intelligence via technology as a proxy. And also, it gives us a nice analog to biosignatures. It's really a way to find life, and we're using technology as a proxy as opposed to, say, maybe things that are in disequilibrium in the atmosphere. So there are a number of things you could think about. Physical artifacts, we actually don't deal with that, but it is possible that machines have gone through the universe and we have a monolith on the far side of the moon or something. But hopefully that will, could be interesting in the future, or maybe on Mars, and exoengineering like Dyson spheres and so on. And we've talked about looking for atmospheres, either biosignatures or technosignatures. We certainly have technosignatures in our atmosphere. We call it pollution. What we focus on, though, are electromagnetic waves. It's a nice, photons are massless and are cheap to produce, particularly at the radio wavelengths, and they can transit the universe. So if you look on kind of a time bandwidth diagram, nature, as we know, doesn't really compress in time and frequency to the extent that technology can. So since we have this plane that we can kind of look at different aspects of, technosignatures tends to look at very small bandwidth time products. That's also where technology largely is, and it makes this big schmear over there in this lower corner where technology is, and all of astrophysical phenomena are over here. The good news is, if we find something over here that is astrophysical, that's a pretty amazing discovery. As we know, pulsars were originally maybe postulated to be little green men because there wasn't any knowledge of that neutron stars could do that sort of thing. And for the radio SETI, we typically look for very, very narrow bandwidths. You could argue we could look at sub-hertz, but in fact, the interstellar medium tends to broaden things to a few hertz. And in the optical, we tend to look for very bright pulses. And that's because if you compress all the energy in a very, very tight pulse, you can actually momentarily outshine the star, the host star. You can also think about other axes, looking for weird polarization effects and so on. So doing technosignatures on the surface of the Earth, as most of all of our science has been done. Fortunately, there are windows where the atmosphere is kind. If you look in terms of octaves, the radio has the most available. And so we have concentrated on the radio for maybe historical reasons, and we're now pushing more and more to the optical because there are infrared and optical windows, and we're trying to up our game, if you will, on those wavelengths. And the other nice thing on the Earth is that there are amazing telescopes that are in use and that we use and are used by others. We try to engender partnerships so that we can get people locally to use the telescope and try to basically do searches for extraterrestrial intelligence. There are more coming. Obviously, in South Africa, we focus on the SKA. but there's also the Rubin Observatory, the Cherenkov Telescope Array. Those are kind of amazing because they're just these huge light buckets, and they look at very fast time cadences. NGVLA is hopefully coming down the line, DSA 2000, ELTs, and so on. So there really is a richness of telescopes that we can use, or are using, and can use in the future. However, the purpose of this focus meeting is radio frequency interference. And this is just a simple plot. When I kind of got this charge to do this talk, I just waggled an ATA dish around for 20 minutes or something and just took spectra. And so this is just pointed at random directions up at the Hat Creek Radio Observatory in Northern California. And, there's a lot of RFI. This is, you can argue, it's pretty much nearly fully occupied. There are bumps and burbles and stuff, but really, are you going to believe a technosignature? Say you find a quiet area and you see a little bump, that's a technosignature. In this sort of landscape, it's kind of hard to imagine believing it. We know the problem. I was trying to be clever with Photoshop and have the Pogo cartoon interspersed with the intervening RFI, but it's hard to see what's going on. And of course, we know the enemy, and it is us. And I say enemy lightly, like I used the term RFI lightly, because I've got every device. I have a car that emits, my phone, my watch. Basically, everything about me uses that technology. So I think if we went to war, we'd probably lose because most people like their cell phones more than they are enamored with radio astronomy, despite the amazing pictures we can take of the center of the galaxy, for instance. So that's at the Hat Creek Radio Observatory, which is a good site, but not one of the world's best sites. If you look at two of the world's best sites, you see that there's still RFI. So I work on a telescope called Hera up at the Kourou site, and this is a spectrograph that we make. And you can see all things that are cut out. This is from about 50 megahertz to 230 megahertz. We basically give up an FM. So worldwide FM is really not viable certainly for technosignature. But even up at L-band and so on, as you just saw earlier, there is RFI. Now, fortunately, there are nice empty regions. You can do great science. So I'm not meaning to be gloom and doom, but it is harder. RFI is there, and for technosignatures particularly, it's pernicious. At the Murchison Radio Astronomy Observatory, the MWA, again, it's a wonderful site, but there are regions where technosignatures particularly is very difficult. You also have DME from aircraft. And if you go to an ASCAP monitor, you see, again, very good, but there are many places that you can't observe a large fraction of the time. And again, would you really believe a little blurb you saw there for a technosignature? So RFI is the problem in radio astronomy. It's maybe a little overstated, but really, if there were no RFI, we could leverage all that computing power and brain power to getting the amazing science out of it. All right, I mentioned we know the problem. It is us. And a little bit of latency, apparently. There we go. So we love our cell phones, and this just shows the cell phone coverage just from one carrier. Actually, the one in Australia might be multiple carriers. There are nice clear regions, but we know that radio waves don't just stop, and radio waves can bounce off planes and, micrometeorite trails and all that fun stuff. Another thing that's coming, and there'll be a talk about this later, I believe, by Balt, is that supplemental coverage from space. This means that you're going to be able to use your cell phone from anywhere. And these are the channels that are being put on spacecraft. In fact, I know at least 10 Starlink spacecraft have this package on it, and they're using it in test mode. And I believe that they're going to start a service later this year. So, even these clear regions are going to have some issues. And again, he'll tell you the real story later today. Our cars, I have a Tesla. It has all sorts of gizmos, but all new cars have LTE and all sorts of stuff. This is actually from an article about the possible health impacts of all the RFI and EMI your car is emitting as you're sitting there in your drive across the Kourou, for instance. And planes, I mentioned planes. This just shows the global international routes, and it looks pretty splotchy. And there are a lot of planes, and they are quite large, and they reflect. And if you're going to do technosignatures, if you see a glint off a plane, that's going to be a pretty big impact. If you zoom in on domestic routes or other international routes, all the continents get traversed. And then I think it's kind of the thing we're focusing on these days are the mega constellations, because they're here, they're growing, and we see that it's growing exponentially. And there are a lot of satellites, and they have bands, but there are also out-of-band emissions. And now, for the first time, optical astronomy is impacted. So there's about an order of magnitude more optical astronomers. And so, as they look into this, we're there'll be some interesting possibilities. And in fact, the problem is even greater because there's a lot more stuff that isn't emitting than that is emitting that is a potential glint for an optical astronomer. So it looks like I'm out of time, but now I have what we can do. There are a lot of things we can do, particularly for many fields in radio astronomy. There's a lot of good news, and receiver design can be improved. The telescope site, we picked the best in the world, and we're developing there. Satellites are the great equalizers. That's kind of my TM quote, I guess, for what satellites can do. We can try to avoid RFI avoidance, point smartly, use filters, and so on. We can handle the radiation or the EMI. The first thing is identify it. There are a lot of algorithms, excise it, flag it, blank it on fast timescales, have two widely separated things to uncorrelate the signals, and subtraction. I maintain that subtraction, though, is never going to quite be appropriate. So all of these will improve the research and technology, and we'll continue along those lines. But none of them, I don't think, are going to enable technosignature observations through it. You're not going to subtract an FM station, and even if you could get to the levels, believe what you saw. And of course, RFI will only get worse in time. All right, so what can we do? There's policy and management. I think that's tweaking along the edges. I'm on the last slide, but there is a few animation. There's canaries. We're the canary in the coal mine. I was going to talk a little bit about dynamic sharing, radio dynamic zones. That's something I'm working on, and that's maybe the future of what we're going to do on the Earth. Part of my is the slowness of the latency here. And then, of course, so we can have a reservation, and instead of just having allocation, we can observe something at a specific time and place. And then, of course, we have the option to go to the far side of the moon, and there's lots of fanciful large telescopes being planned in the future. I'm actually planning a telescope that we hope to launch by the end of the decade that will have a small telescope for the lunar far side. But let's make the telescopes on Earth work as best we can and ensure future generations can do radio astronomy from the Earth with the amazing equipments, and think about the moon also. Thank you.
Thanks a lot. One question. There is no time.
There's no time.
Is it true that part of the doom that you were sketching with the spectra is because it's integrated over a long time? Because those were 24-hour integrations?
So the ones I showed, for instance, of the ATA were each was about a 30-second integration. Even for Hera, right, those are 18-second integrations in that time plot. So you can, like I said, there's a lot of frequency time space that you can try to excise and work within. And if you put like fast blanking with things on a chip that can blank actual samples, you can reclaim some. We're only going to lose more RFI, and we do lose RFI even with these great techniques. So, I think we need to keep working on the algorithms, working on the hardware. There's a lot of scope to improve, but we are losing access to spectrum, and we need to look at our future options.
Thanks a lot. This is really a great start. Many points raised, and pointer needs to be the next speaker, Tom Oslo. He's chairing the drafting group on H1 and will present. I'm going.
Thank you, Josh. Yes, my slides. Morning. Josh asked me to say a few words, briefly summarizing what is the impact of RFI on H1 science. After the gloom and doom of the previous talk, my talk will be slightly more optimistic than that. H1 is a very important part of astronomy and radio astronomy for many decades already, because a lot of very important processes, particularly in extragalactic astronomy, can be studied in the radio domain with H1 observations. Dark matter, for example, is a prime example. The influence of the environment, scaling relations to the Fisher relationship, this kind of science is fundamental science. And with the new telescopes that we are just have, like Bearcat or SCA, that we will have soon, we will hope to make significant progress in this area. And the question then, of course, is what is the impact of RFI? I will split my talk in three parts, depending on what part of the universe you're interested in. And I will start with a nearby universe. One of the main reasons to think about the concept of the SKA was to detect H1 at redshift 1. That's where the square kilometer comes from. You need a square kilometer to detect M101 at redshift 1. But my point is that that's of course very interesting, the evolution of H1, but there is also still, very important science to be done in the nearby universe with the new telescopes. And the reason is that the typical H1 disk in a galaxy has the same surface density, more or less. It's between 10 to the 20, 10 to the 21. Every galaxy is, in terms of surface brightness, is equally bright. So that means that if you have more collecting area, you can go to higher resolution. And that higher resolution you can use to study the interstellar medium in nearby galaxies at resolutions that become interesting when you start, if you want to compare with, for example, molecular gas, ionized gas, say other traces of the interstellar medium. And I think, say currently you can do this on scales of about 500 parsec, kiloparsec, but then with the new telescope with SKA in particular, you will be able to do it at resolutions down to 100 parsec, or if you take a nearby galaxy, even better. This is a picture Robert Brown took some years ago of M101 with a resolution, spatial resolution of about 100 parsec, and you can see how much detail you can see in the galaxy. And it's an important tool to measure the energetics of the interstellar medium, the interaction of, say, the energy output from star formation, supernova, with the disk. You see here position velocity diagrams where you see gas being blown out from the disk by stellar activity. So that's an important thing that we will be able to do better with the new telescopes. Another one example is, for example, do dark matter galaxies exist? There are now some observations of galaxies. This is a classic rotation curve of a galaxy. The dots are the data, and the curves are the predicted rotation curve based on the visible matter. And you see that the model rotation curve based on visible matter only matches the observed rotation curve. So this galaxy does not seem to have dark matter. Well, there's only a few of these galaxies known, and there are all kinds of uncertainties whether this is true or not. But this we will be able to do much better with higher spatial resolution and more sensitivity. Another one I find particularly interesting, how small is the smallest H1 galaxy? If the theory predicts there is a lower limit to the mass or H1 mass that the dwarf galaxy can have, because if the galaxy is smaller, the H1 either evaporates from the dark matter halo or it becomes ionized. And it's crucial to know what is this lower limit. Another one is a classic one, the interface between the galaxy and intergalactic medium. The theory predicts that galaxies are surrounded by very low column density H1 that slowly accretes onto the galaxy and keeps feeding gas to the galaxy. The current state is the Mongoose survey with Meerkat. It has very good sensitivity on a scale of, say, a kiloparsec or a bit more, and they're not seeing very much. So there seems to be a conflict between theory and observations that these huge reservoirs, faint reservoirs that are predicted from simulations, we don't see them yet. So we have to go either to better resolution or more sensitivity, or probably both. The impact of RFI is very limited in this region. This is a waterfall plot from Meerkat of an observation. Here is 1420, and say the nearby universe, here is redshift 0.1, more or less. So this is fairly clean. So RFI is not so much of a problem down to redshift more or less 0.1, if you are in the Karoo or in Australia. Yes. This is when you're in the Netherlands. This is a plot of a noise frequency, 1400, 1300. This is the noise of a data cube we took with Aperitif, phased array system at Westerbork, in September 2020. And then in November, this is the noise now. So the military opened a new radar station emitting in our frequency band, basically killing the science, because most of the H1 detections are in this frequency range. Distant universe, also not too bad, I think, say above redshift 0.25. Much of that is about the evolution of H1. This would be a new area that we haven't been able to address very well so far. The evolution of the H1 properties of galaxies in connection to star formation, etc. The scaling relations of global properties, because most detections will not be resolved at that redshift. And of course, stacking. Some work is being done already. This is from the GMRT. It's quite impressive. This is at redshift 1, stacking, and there's a clear detection of H1 at that redshift 1. Other people are doing similar things with Meerkat, and the results do not seem to agree. For example, this is a plot of H1 mass versus stellar mass, and the red one is the higher redshift relationship, and the gray is the low redshift, and there seems to be a difference, so hinting at evolution. But this is a similar plot based on other data from the GMRT, and there seems to be no evolution. So clearly, we need more work on this. And this is one of the main, I think, science cases for H1 at, say, what we call the distant universe. Another one is H1 absorption, I think is quite important, because you get a unique view of the cold circumnuclear gas of the environment of an AGN. And it's very important for understanding the AGN physics and feedback. This is an example. This is 3C293. This is a position velocity plot. Here you see the H1, that is just the disk of the galaxy, and you see there is a broad tail, very broad in velocity, which corresponds to cold gas being blown out of the galaxy by the AGN. And this is thought to be, this kind of process is thought to be a very important ingredient of galaxy evolution. The current state is that below redshift 0.25, we have a fairly good idea of what is going on. Quite a high detection rate, say 30% of the radio AGN, brighter than 30 milligensky, more or less, are detected. The situation for higher redshift is unclear. Indications are that the detection rate drops, but this could be a selection effect because more distant sources, because your flux limited, say the more distant sources are much more powerful. So you're sampling a different population of AGN when you compare with a lower redshift. So we have to go deeper and higher space resolution and explore this redshift range. There are two main surveys going on, FLASH on ASCAP and MALS on Meerkat, but they have some of the limitations, in particular sensitivity, because some of these detections, these absorptions are very faint. This is a spectrum we took with Meerkat, and you see the optical depth is 0.001. So if you want to, and this is a redshift 0.46 or something like that. So if you want to detect these kind of systems, they can be very faint, so you need a very sensitive telescope. Situation is relatively clean. It's not entirely clean, but it's not too bad. This is a waterfall plot from one of our observations. This is DSM, and there is a little bit RFI in this band. This is the flagging statistics of Meerkat in the UHF band. So you see there is some RFI. It's not entirely clean, but it's not too bad. You can certainly do work there. This is another example of ASCAP. This is a spectrum taken from the FLASH survey from, I think this is 1,000 down to 700 megahertz. And you see it's relatively clean. There are a few areas here, and there's a nice absorption detected there. So you can do useful science in this. So far it's not too bad. Now the bad news, this, Jula showed this plot already. This is really a pity. This is the intermediate redshift range, 0.1, 0.25. And the RFI is a major problem. It actually kills the science. This is a waterfall plot of Meerkat. Here is 1300, 1150, and this is GPS, GLONASS, Galileo, etc. And it's completely blocked. And why is this particularly bad? And that's because every radio telescope has sort of natural redshift range for H1 work. And meaning, in my definition, it is the redshift range of detections if you observe the reasonable, normal amount of time, not these excessive surveys of 1,000 hours, but say a more of standard project, say of 12 hours or 50 hours. And this is the histogram of the redshift of the detections, of the H1 detections. And you see it peaks here. If 12 hours, it peaks just above 0.1. If you do 50 hours, it's sort of 0.15. And this RFI, yeah, oh, sorry. And this RFI that I showed exactly covers the peak of this redshift distribution. So if you want to do a normal project in this redshift range, basically you have no chance. So this is really a pity because it's sort of the natural redshift range of the telescope. This is where it's really good at. You resolve your galaxies, you detect many of them, but it's not possible to do any science there. This is for SKA. This is for the DSA 2000. These are the maximum redshift depending versus H1 mass, depending on what type of survey that you get. And for example, here, the All Sky survey, here, this is blocked by this RFI. And it's really a pity because you would cover from 10 to the 9 to a few times 10 to the 10, which is a large part of the H1 population. And it's completely blocked. So you have to limit yourself to the low redshift universe, say below 0.1, or you have to really spend a lot of time to get interesting science in this mass range. So this is really, really a pity. Not much we can do about it, though, but it's really a pity. So, well, this summarizes my result. I'm reasonably optimistic for H1 science, certainly in the nearby universe. I think there's still a lot of very interesting science to be done. Also, in the distant universe, emission and absorption above 0.25, but this intermediate redshift.
Next to go.
This intermediate redshift is a no-go area. Thank you.
Great. Thanks a lot, Tom. Here's your pin. And David, here. Any questions here? Lister.
Yeah, thanks, Tom. In terms of that redshift range, 0.1, 0.25 being a no-go for the SKA, I mean, the natural baseline lens that one will use will be quite a bit longer than for local observations. Could you say something about the attenuation that provides?
Typically, the fraction of data you flag goes down exponentially with baseline length. The problem for H1 is you cannot go to very high resolution because your column density limited, column density sensitivity. So you can go to very high resolution, but you resolve out your object. So it helps a bit. For example, the Chile survey at the VLA uses the B array or use the B array, and their flagging statistics is better than, for example, with Meerkat due to the longer baselines. But there is a limitation that you resolve out your sources at some point.
Hello. You said something in terms of nearby galaxies. Initially, we expected to find gas flowing onto, accreting onto these galaxies. But if we look at the current observations that we have, even with 50 hours of observations, we are not seeing that. So should we change our view on this, or do we expect to even go 100 hours using Meerkat for us to see that? Yeah.
Well, one possibility is the theory is wrong. The theories can be wrong. It happens. You have to match the right sensitivity with the right spatial resolution, the spatial scale. Say if the clouds have a size, say, 0.5 kiloparsec, then you need the sensitivity at that 0.5 kiloparsec. Say, single dish telescope has a very good column density sensitivity, but on the scales of tens or hundreds of kiloparsec. So that's not useful for detecting that. So either the clouds are smaller than they predict, or a bit fainter. Or, so yeah, we have to go deeper, or maybe also to higher resolution.
Thanks a lot. One last one, very quick, hopefully.
Yes, it's a quick. This is Franz from Chalmers Uni. You showed this spectrum of aperitif when the military turn on the radar. Is there any chance of talking to those people and asking them to turn it off every now and then?
Oh, we
or
work with them.
are you in contact with them?
It's very interesting. Aperitif used a phased array feed system. It was one of the first telescopes to have a phased array feed. Also, this radar is a phased array feed. It's a system very similar to phased array of Aptiv. Yes, we talked to them, but they didn't listen. They actually will build a second one. So we tried, but helaas.
Yeah, thanks a lot, Tom. And next speaker is Yun Yoon. Well, welcome on H1 absorption, please.
Yes, Tom already gave an excellent introduction on the H1 absorption. So I'll be talking about a little bit further universe, focusing on redshift point 4 to 1. So this work has been done by many FLASH member from the ASCAP team. So so I'll be just talking on behalf of the team. So ASCAP FLASH is a wide field survey to searching for the H1 absorption in the almost entire southern field of the sky, and focuses on the redshift point 4 to 1. So basically it is kind of targeted survey. So we didn't do any optically pre-selected. So we extract the spectra for the radio sources, almost all the radio sources with a certain flux limit. And with that spectra, we try to find the signal from the script. So I'll be just focusing on the technical aspect in this talk, and for the more results, you can just come to another talk next week in the H1 symposium. So the brief current status is we finished 2 phases of the pilot surveys, focusing on the 77 fields, covered 3,000 squares of degrees. And we started 5 years of the first survey, aiming to observe 600 fields. We already finished 136 fields process, and it's released on the CASA data archive. So you can download the data. And we expect to get the 300,000 spectra, and it covers wide range of the frequency range. So it is very good, excellent data set to see the RFI or any interference in the data. So unlike the H1 emission, the H1 absorption sensitivity, the sensitivity depends on the flux density of the radio sources. So it is not related to redshift. So we can achieve the more goal to understand the gas content to the further universe. So on the right-hand side, you can see the H1 cosmic density as a function of the redshift. So we try to look at the redshift from point 4 to 1, so which covers 4 to 8 look back time. So these are typical data products from the FLASH, so the nice continuum image, and there's no RFI for this spectrum. And the good thing is it covers large area of the sky, so it is very ideal for the wide field survey. And on your right-hand side, it covers also a wide range of the redshift, so you can get a signal from the a large band of the frequency. So from this spectra, we can get the H1 absorption feature if there are any signal in there. So just roughly show you the quality of the pilot data. So it covers the entire southern sky. So each field can be a good reference to cover to know the RMS noise as a function of array deck, observation time, and many factors. So we overall we could get an ideal continuum RMS noise almost reached 100 microjansky, and for the spectra we could get down to 4.5 millijansky per channel for the 2-hour observation per each field. But in the very beginning, we also faced on some kind of different challenges. So I showed you some mixture of the internal processing issue and also the RFI issues. So most of them actually fixed, because the main goal of the pilot survey is to prepare for the strategy, data processing strategy for the first survey. So the ongoing problem is tropospheric ducting and solar interference and some of the partially random glitches in the spectra. So I will just introduce briefly. So the glitches issue some kind of very narrow 1 megahertz feature somewhere in the spectra. So some of them we know the origin, but some of them it is unclear. So it would be very good if we can understand the origin of the feature because it appears randomly, but at the same frequency in the spectrum data set for the given field. So actually, Leroy, you can see the papers, and he identified that some of the glitches have some kind of origin, like a self-generated RFI within the clock, the receiver issue. So he tried to mitigate some of the RFI, and we could get some kind of ideal results after fixing this issue. So you can get some good progress from the paper. And another issue is solar interference. So on your right-hand side at top, you can see the expected solar activities as a function of the ER. And the gray shade show the expected solar activity, but actual activity is greater than the expectation. And the pilot survey period, we could get a very nice data set which were not affected by the solar interference. But from the beginning of the first survey, we already got the 13 fields are affected by solar interference. So we try to schedule that to avoid the solar interference because it is very critical for the spectral line science. And I like to highlight tropospheric ducting because this is the biggest issue at the moment. So it occurs at the particular atmospheric situation. So radio signals can be from the distant transmitter and reflected in the troposphere. So some of the frequency already introduced by the earlier talk. So the common frequency range is these 4, and we can see some severe feature in there. So we had to reject some of the data in the beginning and try to revisit some of the observation. But good thing is ASCA operation teams tried to incorporate some ducting alert. So based on the flux ratio of the given data from the very beginning of the observation, so we tried to understand that this observation anyway can be affected by ducting or not. So then we can just revisit the observation without a big loss of the observation time. So that is good progress. So what we try to do is, given the RFI interfered data, we try to sort out some kind of true versus false detection. So you can see the first count as a function of the redshift, and you can see some kind of specific frequency are affected by some many issues by mostly correlated dropout and ducted RFI. So what we do is try to understand the detection by machine learning technique. So what Xiu and Ivy did was train the pilot 1 data and make some prediction to the pilot 2 data. So which can be a real detection or not, because we try to run the line finder in the beginning, but we have a bunch of the potential candidate that is a mixture of the artifact and the real detection. So we try to train the data set and try to find some kind of real detection. In addition to the real detection, we was unable to find some from the beginning inspection. So almost there. While trying to fixing this problem, but we finally got 13 new H1 absorption from the pilot data. So I will introduce the more result at the science session next week. So I hope I can see you there.
Thanks a lot. Are there questions? So it's basically a comment from my side. So we have in this H1 session seen that there are 2 large windows through which we can still observe the H1. Now, spectrum is a very scarce resource, and we already got indications using a military radar, for example, that these windows are not a God-given or given. And we still have to care that they remain usable by us in a harmonization process with industry. And with this, I would like to thank the speakers in the H1 session. And now it's Giorgio Seringio on instrumentation. Thank you.
Good morning, everyone. Let's see if this one, if I understand how it works. So I will talk about the technical part, let's say, the receivers technology, and then starting talking about the spectrum, the electromagnetic spectrum that we use for radio astronomy. This one? Yeah. So this is part of the white paper that we are preparing. And the chapter that I'm sharing exactly about radio astronomy, spectrum coverage, and receiver technology, present and future. So this is something that you probably know very well. We saw this many times. And the reason why I'm showing this, because typically we think about radio astronomy, which is in this area, which is the most transparent part of the spectrum, as you can see. But there is quite a lot of radio astronomy done somewhere else. And where in this plot, they say that there's not transparent at all, but actually we can do ground-based radio astronomy. As for example, ALMA, where I work, and this is would be far infrared and infrared. Of course, this part of the spectrum usually is done from the space. And just quickly, I want to show you that the occupation of the spectrum, right? And this is 45 megahertz observations. This is quite new, 2011, and this is the Galaxy synchrotron emission. And but this started in the 70s already, with a group of people that were using the telescopes, the big telescopes that were built in that period, and went on at different frequencies. This is the H1, and this is from the WMAP, the satellite. And this is already higher frequency. Sorry, I'll go back. Yeah, this is 23 gigahertz. And the polarization comes out also, which is a very important characteristics. And this is also polarization. It polarized intensity taken by, oh, sorry, wrong button, by the Planck satellite. Again, this frequency is much higher, and so this is not what one thing about classical radio astronomy, but this is actually part of the present and the future. So we are expanding our possibilities to observe in the higher part of the spectrum. It's a very nice product. And this is something completely different, but I want to show this as well, because it gives the idea when we talk about redshift and redshifted galaxies. These are dusty, star-busting, star-producing galaxies. And the redshift makes possible to observe with just with one band. This is done with ALMA band 3, which is a relatively small RF range, around 100 gigahertz. But then with the same instrument, with the same receiver, is it possible to get a redshift from practically from, this is the lowest one is 1.87 and goes up to 6.9. And this is the identification of the redshift is done based on the carbon monoxide and some other molecular species that you see at these lines here. Well, that said, of course, I cannot go through all the bands used in radio astronomy. And this has been done already a long time ago. So there is a list that was compiled by the IAU General Assembly in '91. And another list has been prepared for the WRC 2000 by the UCAF. And you can find this in the website of the CRAL, which is the Committee on Radio Astronomy Frequencies of the European Science Foundation. And there is a total of 295 frequency bands and goes from 13 megahertz up to practically 1 terahertz. Okay, so what about the RFI? So we have other speakers already mentioned this. We have to consider that, as I mentioned, we try to use a upper part of the spectrum, and that part is still clean, pretty much clean, especially when compared to the lower part of the spectrum. So I make the division at the 30 gigahertz. Whatever is below 30 gigahertz is affected by RFI. Whatever is above 30 gigahertz is much more cleaner. But this is going to change quickly, unfortunately, because of the development of satellite constellations that practically affecting globally the whole planet. There is no, let's say, quiet zone safe from the sky. And the satellite operators, they are moving to higher frequencies because they need more bandwidth. And so they are starting to occupy even the part of the spectrum which is above 30 gigahertz. That was clean before. Okay, let's change topic and move to the second topic, which is the technology of the receivers. And I start with some definitions. I put it in this presentation, but this is actually for the public, so people can look at it. I will go quickly through this. It's not part of this of today's presentation. Anyway, so the concept is the receiver is just a transducer. So it takes photons and it transduces this in information which is voltage that you can then manipulate with electronics and digitize it. And so this is a schematic. There can be any receiver. Practically, there is a collector of photons somewhere. It can be an antenna, it can be a dipole, it can be a parabolic antenna or a horn antenna. And then there is the first thing is that you filter or you manipulate somehow the RF information, for example, polarization splitting. And then there is the detector itself, which is where the information is converted from RF, so photons, let's say, to an electric signal. And then this electric signal is manipulated with some analog electronics until it is ready to be digitized by some digitizers. Starting from that point, then you get some digital information and you can manipulate with computer software and so on. Typically, what it comes out is what we call the data cube. The data cube is practically a signal. Mostly in radio astronomy, this means amplitude and phase of the source as a function of time, of the coordinates in the sky, and of course of the frequency. And we have to divide the receivers in two groups, two large groups. One is the coherent receivers, which this means it's a type of receiver that can detect the phase of the signal together with the amplitude. And the other group of receivers is the incoherent receivers. And this can be done in two ways. So one way is that when there is some enough energy in the photons, that this can produce an effect, a physical effect that we can measure, like a photoelectric effect, for example. And this is called the direct receiver. Otherwise, if the energy of the photons is low, as it happens typically in the millimeter, submillimeter, for example, for whatever photons they are below, let's say 200 microns or 1.5 terahertz, there is no effect that can be produced directly. And so what we do, we integrate the energy of several of these photons, and then we try to see the effect in an indirect way. For example, with the change in temperature of a detector, which is cooled down in a cryostat, cryogenic temperatures. And the bolometers are a typical example of this. Now, these are a list of properties of the detectors, and then quantum efficiency, linearity, dynamic range, noise, number of elements, time constant, spectral response. I'm reading all of them. And I will skip this part. As I mentioned, this is mainly for people that want to go deeper in the definitions, but I go straight away to the conclusion. There is a slide with some conclusions, right? And of this slide, well, mostly what I made a summary here. So when we design a receiver, what we want to do, we want to have a receiver that has a high sensitivity, which means it's efficient for the observations. large collecting area, of course, if there is a telescope to be built, the larger the area, the more photons we get. And the large field of view, which means when I use this large collecting area, also look at the large part of the sky. And of course, the instantaneous bandwidth, because I can get more photons. Usually the receiver has a bandpass, right? And whatever is outside of the bandpass, these are photons. They are also collected by the collecting area, but they are lost. So the larger is the passing band of the receiver, the more information we get. And there are some challenges, of course. This is not easy to do what I'm saying. So that's the dream. But of course, whenever we increase the bandwidth, automatically we increase the noise. And also, it's a problem to keep amplitude and phase stable for a long time, because if we want to do integration and over a wide bandwidth, especially keeping the noise of the Gaussian type, so that when we integrate, it goes down. If it is not Gaussian, it doesn't go down with integration. And then there is another problem, which is to minimize all the calibration errors, because we also have to calibrate, and the calibration process introduces some more noise. So another topic that I want to discuss is the sideband separating mixer. So most of the radio telescopes, they use the principle of heterodyne. So practically there is a local oscillator, and this one mixes with the photons coming from the source, and we get an intermediate frequency band, so a post-detection bandwidth. And this is done, it can be done in different ways. But the most efficient way to do this without losing information is to use both sidebands. So because when you do the heterodyne process, the mixing, you get an image from on both sides, let's say, of the local oscillator frequency. I show in the next slide. So what I want to say is just that the typical design of any coherent radio receiver, it starts with the 90 degrees power divider. So, and then practically there is one channel that goes to one mixer, and the other channel is 90 degrees shifted. And these are the single sideband mixers. And then there is one more 90 degrees shift. And the magic of there is quite a lot of mathematics behind, but then the output is a separation of the two sidebands. And then this is the analog signal, that I mentioned at the beginning, the voltages that we can then manipulate. This is just to understand what I'm talking about. If this is the local oscillator, right? The mixing with the photons coming, let's say, from the sky, it ends up in two bands. One is below the local oscillator, the other one is above the local oscillator. And the band is defined by the frequency of the local oscillator, and then by the minimum and maximum frequencies of the design of the receiver, so what we call the intermediate frequency. This can be manipulated by the electronics, so we can decide this. So after the mixing, I can look at the sky in this range of frequencies or at this range of frequencies. Ideally, I want to preserve both of them, because if I don't preserve both of them, I lose half of the signal practically. So one important point is that this separation between, I go back again, the separation between the two bands has to be very well done. Otherwise, there will be a contamination of one band from the other band if they overlap or if there is some leakage of one of the other one. So one important parameter is the separation between these two. And this separation is sometimes challenging. And typically for a good receiver, this is about 20 dB. But it can be lower, and actually it is challenging to keep it constant over the bandwidth, especially if the bandwidth is larger, because we want to have larger bandwidth. The larger is the bandwidth, more difficult is to keep it at this level, or the whole band. Which means if there is some leakage, there is practically noise. So this is another concept, which is also very important, which is the polarization splitting. As I mentioned, we want to collect the most of the information from the sources. And of course, polarization is very important. And typically, receivers for radio astronomy use circular polarization or linear polarization. The linear polarization is easy to be split with the orthomode transducer. So practically it's a series of waveguides, and when you get the two linear polarization, one goes straight practically, the other one is flipped and goes in the other direction. And you have the splitting, and the splitting can be good as long as the waveguides are big. So this means classical radio astronomy at low frequency. But when we go to high frequency, let's say we go below 1 millimeter, then it starts to be very challenging to produce an orthomode transducer because mechanically it has to be very small. We're talking about 300 microns for the waveguide, and so practically the surface accuracy start to be not good enough to produce this effect. So in that case, we will call it quasi-optical. We use wire grids, polarizers, and here there is an example, for example, the ALMA Band 9 receiver. It's a very complex system of mirrors and wire grids to get it, the polarization split. So it's already over.
Yeah, time's
Okay.
sort of.
What about RFI, which is the topic of the focus? So we know that the RFI, of course, the most obvious is the one that comes directly in the antenna. But there are other points in the design of a receiver where the RFI can affect the final result. And practically this in the analog part, which is here before the mixing, the analog part which produces the local oscillator, and the local oscillator itself can bounce back and go in the first part and produce what's called self-inflicted RFI. And then there is RFI, of course, falling inside this part of the analog chain before the digitization. After the digitization, it's practically impossible to get RFI. So the concept is that we should try to digitize as soon as possible. Okay, this is where I can skip it. Mainly want to mention that the new technologies allow for a very large bandwidth now, is both in the RF and in the IF, and also for very large arrays of detector, which is a very simple way, let's say, to increase the collecting area because each detector looks through the same telescope. So you multiply the number of telescopes. So the final goal for the future is that we want to digitize the signal as soon as possible. So remove as much as possible the analog part of the receiver and make it digital, because that's the way to be safe from the RFI produced locally. And this is an example. There is a nice paper here. And, oh, sorry. So there are some group of people, they are working on the digital receiver practically. So again, all this part here is digital, and this is, for example, for the sideband separation. And you see, this is at the bottom of this plot, the sideband separation done with the schematic that I showed before. And this is the sideband separation done digitally with the powerful FPGAs. And you see that you gain a much better sideband separation, and also doesn't have all these peaks. It's much more flat along the band. So you can use this for very large bandwidth. And the other point I wanted to show you is that also the polarization splitting can be done digitally. You don't need to have really all these wire grids and so on. There is a very simple concept where you have this is a sort of a 4 antennas at 90 degrees, and then the rest of the job is done digitally. And you get better polarization separation that you can get with the wire grids at high frequency. So this is the future, this is the way to go. And then there is another concept that we have to also to look at in the future, which is the system on a chip. So everything can be integrated in one single chip. You get there all the amplifiers, LNAs, and also the hybrids if you need it, and the part for manipulate the signals, the digital processing can be done with one chip. This means that you can build arrays of receivers in with a very small footprint. So each receiver has a very small footprint, so you can make thousands of receivers in the focal plane of the telescope. And I think, yeah, this is the last slide. So just a recommendation for the future. So how the receiver should be built. We have to minimize as much as possible the opportunities for RFI. we have to invest in, of course, in monitoring and strategies to mitigate the RFI in the signals. I will show that before the talk, before me, they showed that it's a major problem for some frequencies. And the new technologies have to focus on digitize the signal as much as first as possible, close to the antenna. And compact design to make arrays to have immediately more collecting area. And that's it. Sorry for being late.
Thanks a lot. Thanks a lot, Giorgio, for this overview. We have one question. Quick one, please.
There's a bit of engineering that I don't understand, so I apologize for my ignorance ahead of time. In your plot about the digitizing as early as possible,
Yes.
I noticed that the noise floor has been raised a bit from the digital plot versus the analog plot. How then, and then of course there are no peaks, which is EP, everybody's happy. But how do you know that you haven't saturated your receiver, even though you don't have peaks?
Ah, you mean in the sideband? Okay, that's not there.
Yes.
In the sideband separation plot. It was. You gain one.
Sorry if I forgot that for the other.
Yeah. No, that was not RFI. That's the feature of the sideband separation operation. I can explain you because I was going fast. You have yes, I know. You have an RF hybrid and an IF hybrid. So these are these two power divided that they do the trick to flip by 90 degrees one channel. And then to reconstruct it, and you do the sideband separation. In this process, this is very frequency dependent, and especially if there is an imbalance between the first part and the second part, when you flip it doesn't combine perfectly. And so there are some ripples, but these ripples are, let's say, introduced by the same device. They are not coming from the outside. When you digitize this, and you do this all digitally, you can compensate and calibrate your system in a perfect way. And then it comes up with a sideband separation of, let's say, 50 dBs, which is a dream at the moment to do this only with analog electronics. That was the point of that.
Thanks a lot. I think we need to take this offline. Please also use the Slack. I haven't seen anything on the Slack, and you can still earn your pins. Next speaker would be Nadim on another view of on RFI. As I said, I'm looking forward to the technical chapter in our white book, and Nadim is leading another chapter on the summary chapter, basically. Please go ahead. Green is forward, red, back. And
Thank you.
Point.
Morning, everybody. I'm here today to tell you that we have analyzed 1 petabyte of data measured from the Meerkat Radio Telescope, and we have built a probabilistic model for characterizing RFI on site. It's a very simple model that can be used and applied to any observatory, and it allows you to understand the evolution of RFI across site. Very often when we talk about RFI measurement, we go and do directional measurement of RFI. Here, I'm going to show you how we take the data from the telescope itself, and we extract the RFI probability. We all hear that. We keep on hearing that the RFI is changing, the RFI is getting bad, and I want nighttime observation, I want daytime, I don't want close to the sun. But we are scientists. Claims and anecdote are not data. I'm here to find out, okay, how can I apply a data-centric approach to justify these hypotheses? So we all love getting data from the telescope. You collect all your data, and the data I'm going to use today is from the Meerkat Radio Telescope. And for some of you who may not be familiar with interferometer, I'm going to use the word baseline. Baseline is a vector between two antennas, and then the telescope has got an azimuth and elevation, and also you get your time and frequency information. So you collect your data, you want to make great images like that. But before you reach there, there's a lot of pain and a lot of hard work, especially calibrating your data and removing your RFI. So this is the Karoo Array Telescope historical probability. We get the data from the digitizer. I guess this is the line. Yeah. So your signal comes from the digitizer, goes into your correlated beamformer, where on the magic happen, and then your visibility come out at 0.5 seconds. For Meerkat, okay, that signal is go into an ingester, where it is further time average in 4 seconds, 8 seconds, depending on what science you want to do. So what we do is, at the ingester here, at the signal, every time you have a sample of data visibility coming, we apply an AO flagger, and we say, what is the how many samples of outliers do you have in your data? And therefore, we built a model of RFI, log outliers and data. And that's what we do. We bin our data in time of the day, frequency channels, baseline, azimuth, and elevation, but due to computational restrictions, we have to limit our data. And for some of the youngsters here, we use a lot of DASK and Z array and X array is very powerful for analyzing huge amount of data. So we produce a 6-dimensional array. I've showed you time, frequency, baseline, azimuth, elevation. The 6th dimension is the date of your observation. We look at L-band and UHF data, the cross correlation, the HH, the HV, and the VV, and there are potentials to do other stuff with your data. When we started that project, we wanted to know, okay, how this tool is going to be useful for operation. You want to schedule a very sensitive operation, observation. Where and when do you do that? RFI working group, we do have new RFI detected on site. We just pipe to them, it's like, hey, there's something new that is above some probability that you need to go and investigate. Spectrum and telecom managers, this is a very useful tool for you. And also, if you astronomers, you want to flag a data, you see a spike, do you want to flag a spectral line, or is it a known RFI? And what is the probability that it's an RFI? These tools allow you to understand that. So now that you have a 6-dimensional array, you can slice your data in whatever dimension you want. This one shows you the probability of picking up RFI as a function of frequency and time of the day. Remember, I told you that astronomers always say like, oh, I want nighttime observation from 1 petabyte of data. There's only like 3% difference between nighttime and daytime observation. So I don't think, okay, if that's justifiable, okay, that you need nighttime observation. So the average probability of picking up RFI in the L-band is around like 23%. And these are the known GPS satellites. And also we have the GMEs and the GSM signal. And because we have a huge amount of data, we can also put confidence level on the probability. So you can also slice in terms of azimuth and elevation. And this is for the L-band, HH, and VV. And you can see those hotspots where you are most likely to pick up RFI. We can't say exactly where it's coming from because of the beam of the telescope, but you have an understanding, okay, how this RFI is changing is with direction. Now you can also slice it in azimuth and elevation. As I said earlier, this is the probability, this is elevation, and this is probability, and this is azimuth in orange. You see that, oh, okay, great, 70 to 80, like almost like azimuth. The RFI is lower, therefore, if you want to get less RFI, you use those regions to do your observation. L1, GPS satellite. This is the RFI distribution in HH and VV. And this one is a very interesting one, the L3. I don't know how many of you know about the L3 signal. We saw that when we were commissioning the Meerkat, there was this 1380 megahertz repeated signal that come from GPS nuclear detector active system. And we detected that signal in the days when we were commissioning Meerkat. And this is the time of the day that this signal is triggered. Actually, you can now get a specific frequency, okay? You can learn about your RFI. On top of that, we hear a lot about spillover because you have your satellite, they have a band that they work, but at times you can have some saturation from spillover on other channels. So with this data set now, you can also calculate the probability of RFI in adjacent channels and how they impact your data. So that's for the L1, and that's for the L5, which is, I read, I don't know, maybe someone can correct me, L5 is supposed to be silent, but it's not silent. We pick up the RFI from the meerkat. So there's nothing that you can hide if the telescope is measuring it. So this is the UHF band, which is much cleaner, probability of RFIs as a function of frequency and time of the day. And what is interesting with this UHF band is here, I will ask maybe some astronomers. So basically in the UHF band, we have GSM signal that dominate the UHF band. But when I look at the data in December 22 and January 2023, I found that the RFI signal during the day dropped. Can someone just guess what can be a cause for your GSM signal to drop? Because we know everybody is using the cell phone. So why are we seeing a drop in the signal, in the RFI probability? Any guess? No, that's during the day, South Africa. So people are well awake. Yeah, and not sleeping. Any guess? Lots of radio astronomers, yes? No? Any other guess? Great, we know South Africa, we have load shedding, power cut in December 2022. The cell phone towers were discharging, and after 2 hours they die, and the RFI probability just drop in the UHF. And then every 4 hours, we have another load shedding, and we see that again. So I love working with RFI, and the data from the meerkat even telling you now, okay, oh, there's load shedding. So if you had observation, wait for load shedding, we have generator, and you will get less RFI. Distance measurement equipment, we can also now slice our data, look at the emission from distance measurement equipment on airplane, air to ground, ground to air, and we found that actually the ground to air is slightly higher RFI as compared to the air to ground RFI. And the beauty, if you had observation during the lockdown, this is the RFI probability in the frequency for the DMEs, 1030 to 1100 and 1090 is here. This is the observation date before lockdown. This is how your DME RFI look like, and during lockdown, clean. So we can't remove, okay, all the planes crossing overside, but if you had data or you want to look at some clean data, go and search the Meerkat archive and look for those lockdown data observation. And we also have a clean band now. The L band is not clean. So we decided to use 2 band that we call the clean band. And now we can use the clean band because we are not supposed to have anything there. And now we can look at the probability. If something comes up there, then it should be an alert. And during December, that's 2018, during December, we were looking at the RFI, and then we found that, oh, great. By the 15th of December, the RFI dropped, but it peaks up before that because everybody just busy doing lots of engineering work before the closure for the holidays. So your data allows you, you want time of the day, you want weekends, you want every Monday, whatever you want, that 6-dimensional data allows you to do that. Here's my conclusion. So can we quantify RFI from a telescope perspective? Yes, you can do it. It's easy to do. The source code is available. Lots of people talk about machine learning and artificial intelligence when we're dealing with RFI. This is simple probabilistic model, and it works. We give you the confidence level, and I know lots of us, we are talking about how do we find the right balance between satellite transmissions and radio astronomy. We know that future satellite will affect. We are seeing already lots of unknown satellites in our field of view. We are seeing the frequencies from the Meerkat. So, yep, this is a tool that I'm sure lots of you will enjoy using. Come and chat with me. Thank you.
Thanks a lot for this wonderful presentation and the wonderful tool. Are there any questions?
Yes, Mario. Oh, sorry.
Up over there. Mario. Pin for you. Up.
Great, thank you. Yeah, great talk. So just I want to ask you, like, what's your definition of RFI? Because when you're showing probabilities, when you mention outside the band, so like that nice supposedly clean band, right? Because you could still do science there. So what's the meaning of saying, oh, there's a certain probability of RFI there, because maybe it's very low and then you don't care. Like,
yeah, so what I define as an RFI, okay, I'm just using the definition of an outlier. There are some outliers there. So many of them, sorry, we don't know, we have not gone like now in depth to analyze, okay, what are the sources? As you rightly said, there might be a low level RFI, but from 1 petabyte of data, you're getting, okay, this probability with a confidence level. So if you're doing your observation, you find a low level RFI, a low level outlier, it's up to you. If you want to confidently remove it, it's like, okay, that's always been there for 2 years, so that's most likely an RFI. But if it has not been seen before, it's like, okay, wait, that may be a good signal. So it's basically an outlier detection, and we build a probability model. Yeah.
Hi, Nadim.
Hi.
For this tool, I think most radio astronomers who deal with data will be happy to work with it. How accessible is it? Is it something that you can find online and use it, or you have to, it's not yet?
The algorithm and everything is available online. The data, we still have policies that, okay, we need to talk. Maybe we can have a chat, okay, with the office to find out. Because my plan is whenever you have an imaging observation, you have a probabilistic model of your data accompanying, but we need to implement it, put it in the archive. There are lots of things that can be done, but if you're interested in your data set, I can show you how to do that. Yeah.
Thanks a lot again. I think we need to finish this session now.
Oh.
Thanks a lot.
Thank you.
And coming to the final presentation by Bold Indermühle about what we should probably be afraid of is direct to cell. Thank you.
This is exciting.
Exciting, of course.
Rarely seen so many faces at an RFI talk. I'm glad CPS runs in parallel, otherwise this would be bursting. Thank you. I'm conscious I'm standing between you and lunch, so hopefully this is quickly resolved.
It's definitely an exciting topic that we have to expect. So I'm very sure that we will have the patience.
Well, not to take away from the talk that's coming, but while we don't see anything, that's actually sort of indicative of what I'm talking about, because we can't see yet what I'm talking about. Thank you. As you can see in the middle spectrum there, this is a piece of spectrum from our site out at the Australian Radio Quiet Zone, Western Australia, where the SCAP telescope is. And this is from our RFI monitoring gear. You can see at the bottom there's some mobile phones, base station transmission signals that is actually leading or coming into the site through ducting. And when the ducting breaks down, then it's a very, very clean site. As you can see, there's nothing there. So let me give you a very quick brief on terminology. Direct to device, direct to handset, direct to mobile, direct to cell, or the wonderful euphemism our American friends have coined, supplemental coverage from space. Sounds so much less impactful. They all do the same thing. They all provide your phone with direct connection to the internet through data from satellites. The challenges are not just there for us, they're also there for the operators of these systems. They deal with weak signals. Obstructions will likely lead to connections breaking down. We know that from Iridium handsets. Anyone who's ever had a play with an Iridium handset knows that as soon as you have a leaf between your antenna and the satellite, your signal's gone. Foliage, as I said. Inside dwellings or inside vehicles, this is unlikely to work. And further to that, beamforming at low frequencies provides very large footprints. So it will not be possible to exclude sites as sharply as Starlink, for instance, is doing very successfully around our radio astronomy sites to avoid illumination of our receivers at 10.7 to 12.7 gigahertz, where they have very small cells. Beam size is a function of frequency and antenna, or focal plane array size, of course. So by necessity, these are a little smaller on the satellites, most satellites, some are larger. So we have pretty large beams. And of course, self-interference for operators is a problem because they're using their own spectrum that is allocated to them for terrestrial use. So if they beam that spectrum from space into areas where they use it on the ground, they're interfering with themselves. So it needs to change how they arrange all of these cells. Now, in this picture here, I'm going to focus a bit on Australia in this talk, of course. You see the cell arrangements for the 1.8 gigahertz Australia-wide licenses. And you can see Australia-wide in that context means they are fairly limited to where exactly they are broadcasting. If you go to the 700 megahertz, 700 and 800 megahertz and 2.5 gigahertz Australia-wide licenses, that is what that looks like. So they can broadcast from satellites all over Australia, except for that tiny little bit here. Sorry, I can't see which one is the laser pointer. This one? No. This one? No. Oh, whatever. Oh, there. You see this tiny area here. This is the Australian radio quiet zone, Western Australia, where we actually have an exclusion zone for these signals. But as I've mentioned before, the beam sizes at low frequencies are very, very large, and it is unlikely to be of useful consequence to us. What happened? I think I pushed a button I shouldn't have pushed. There you go. Okay, so we need to ask ourselves, this is very, very high power interference that we're seeing. This is a completely unprecedented situation. We're looking at transmitters that operate in frequencies where we thus far have only had them in the side lobes of our telescopes. We've never had a direct illumination of a radio astronomical receiver straight down the beam with full gain. And that is exactly what's going to happen. So we are standing to lose a lot. And we philosophically perhaps can ask ourselves, you know, how does that stack up to against the perceived benefit of what we're getting from this? We have careful coordination in place around all of our radio astronomy sites. We're coordinating where those antennas are pointing for the mobile phone spectrum. And as I've mentioned before, we're observing these signals now in these telescopes, these satellites, straight through our high gain beams, meaning we will certainly see second and most definitely see also third order harmonics straight from the transmitters. Every transmitter produces harmonics, no matter how good and how well they are engineered. So our systems are optimized for sensitivity. We don't want to place notch filters onto these systems. We have fairly low sampler bit depths traditionally. So we need to work on improving the resilience. I think Dave has mentioned that already in his talk. We really need to improve the resilience of our receiver systems. That is on us to do. Of course, that comes at a cost. So somebody's going to have to pay for that. And that includes increasing the sampler bit depth, of course, to 12 to at least 16 bit, ideally. These satellite mobile towers are going to be visible essentially from all over the place. So this is a viewpoint centered on the Australia Radio Quiet Zone. For the OneWeb constellation, they're about 850 kilometers elevation. If we were to ask operators to switch off their transmitters when they are above the radio horizon for our site, they couldn't serve Australia at all. If we repeat the same thing for Iridium, a long-known interferer for radio astronomy, they could only serve sort of the eastern part of what we call the banana in Australia. And for Starlink, it's slightly better. But still, more than half of the country could not be served if we ask them to switch off. So we're not going to be able to do that, of course. So this is a simulation that I've done using the PyCraft software toolkit for the Starlink Phase 2. From the ASCAP telescope, assuming a 1.25 degree beam width. If Starlink Phase 2 is fully developed, we are having a satellite flying through the beam every 18 minutes, but this is only one of 5 constellations that we currently know that are planned. If all those 5 constellations are deployed, we're looking at a satellite in the beam every 4 minutes. And if we lose the entire bandpass every 4 minutes, that is a significant amount of data loss. I'm going to rush through this. It's a little technical. The thought was to estimate how badly are these second and third order harmonics going to affect us. We can use a GNSS proxy measurement because we have GNSS signals, as we've seen in previous talks, that are making us blind in the 0.1 to 0.25 Z redshift regime. And we can essentially estimate based on what we know about terrestrial networks and how strong the signals need to be for a mobile phone to work with a satellite. And we can see that we have about 52 dB stronger signals in the second order harmonic and about, 50 dB less in the third order harmonic outside the beam. This is what that looks like if we observe with ASCAP. On the right-hand side, you can see a image that is affected by GNSS interference, and that is 50 dBs less strong than the interference that we will see from direct-to-mobile satellites. The radio regulations are not much of a help in this case. Radio regulations are an international treaty framework. They are treaties between countries, not between commercial or research entities. And there's this famous Article 4.4 in the radio regulations that essentially enables administrations to override and say anything that happens within our national borders is our own thing we can do as long as it doesn't affect any third parties outside the country. The ACMA, our regulator in Australia, has determined that Australia-wide spectrum is the matter to deal with between stakeholders, and they can use their Australia-wide licenses from space. So we have to deal with that. Specifically, what that means is we have to worry about the base station transmit frequencies that we will be seeing from space. I can't be too specific in what I am showing you here on the exact frequencies and the operators in use because there are a lot of non-disclosure agreements in this space. But we are working with operators and with the satellite operators themselves, SpaceX specifically, to measure and accurately predict the actual impact of these satellite constellations. I am out of time here to run through this in detail. This is essentially a list of all the harmonics, and this gives you a list of the bands as they are usable from space. The green bands are essentially without problem. They're still a problem, of course, because they disable our opportunistic use of the spectrum. This is spectrum that we normally can observe with, but not if it's used from space. The longer term impact, the orange bands that I just blended in there, this is what's being considered right now and actually has been enabled right now for direct-to-device. And at the international level, there are efforts underway to repurpose IMT spectrum, so terrestrial spectrum, into mobile satellite spectrum. And when that happens, that is what that looks like. So L-band and X2 Ka band will largely become unavailable for radio astronomy should that happen. This is not a good look. So in conclusion, significant impact. The further mayhem I just mentioned, more repurposing of spectrum from IMT to mobile spectrum, mobile satellite spectrum. We need to improve our receiver resilience. We're testing what's happening with the systems that are being deployed right now. And as a consequence, our opportunistic use of the spectrum is becoming more difficult. The discovery space is shrinking. And I have 2 take-home messages for you. That's the only thing I want you to remember from this talk. Be careful with your public messaging. A lot of what we are doing is happening between operators, between satellite operators, mobile operators, and us as a radio astronomy facility. A lot of that is governed by non-disclosure agreements, and that allows us to be open and frank with each other, but it also means we have to be careful with how we make them look in public. So if you observe interference from these systems, go talk to your spectrum manager, send it up the chain. Don't tweet about it. This is a bad idea because it makes our work much more difficult because we are in constant engagement with them. And of course, it looked really bad what I just showed you, but necessity is the mother of all invention, as we know, and we have a lot of bright engineers working on this and scientists. And my colleague, Jane Kazmarek, is going to talk about some specific progress that's been made with the Parkes, the Marianne Parkes telescope. Thank you very much.
Thank you so much. Here's your pin. Yeah, thanks a lot for this insight about D2C. Are there any questions?
Thanks. It was really interesting. I know at the VLA they're working with SpaceX to do to explore the idea of like active sharing. So VLA will tell SpaceX where they're looking at and at what frequency, and then SpaceX can, if they don't have to turn it off, then they won't. Right. So it's not like they will always turn it off over the site. So is that something that you could explore to kind of mitigate the impact here?
Yes and no. Yes, we are also exploring similar avenues of spectrum sharing, although spectrum sharing in Australia is not a known concept per se. We don't have dynamic zones. We have clear radio licensing instructions that are telling our operators what to do. But we are very closely working with SpaceX and doing specific measurements, specific methodologies from bore site avoidance to a number of other methodologies that I can't really talk about here. Thank you.
Thanks a lot. Any other question? Well, then let's go to the break and remember, well, Balt's contribution here. There is a lot to do. We have heard about the L-band bands that are still available. So either we hurry or we work together with industry and administrations to get a harmonized situation for us all. And this is what this is about. See you after the break, and please return. It has been a very interesting session so far. Thank you. Try to ask the question.
Okay, good afternoon, everybody, and welcome to the session. I'm here, my name is Kobus Luther. I'm here on behalf of my manager, who's Ketemetsi Mlamu. Unfortunately, or fortunately, she went with the VIPs to site today, and she asked me to stand in. So if I don't know all the words for the slides, please forgive me. So we're going to talk about the Observatory of the Future, building on what we have done, and to a large extent, we will elaborate on the Ghana dish conversion. There will be several slides, so let me start off. So the introduction, this is this presentation, then we'll move on to mechanical, electronics, receiver, digital, backend, and software. Each one of the groups will do a presentation, and they assured me they will stick to the time, or even make up a bit of time because we're 15 minutes late. So just an introduction into our engineering team at Sareo. We've got 184 staff members. We are structured into 15 teams or groups, and you can see all the groups there. It includes each and every specific element of the entire signal chain, as well as civils, infrastructure, electrical, project management, program management, system engineering. And of course, we also have an engineering team at Hartrouw. And the RFI team, of course, our radio frequency interference team. So we have 4 focal areas, starting off with design and development. So as an engineering team, we are tasked to provide innovative solutions to complex problems, which will include most of the time some cutting-edge technologies, using of cutting-edge technologies, and also developing cutting-edge technologies. So that's the first focal area. The second one is maintenance operations. Once the systems have been built, of course, we need to keep them running. So to ensure continuous and effective operations of any of our systems, there's a lot of work to be done from the engineering side, including maintenance, fault finding, troubleshooting, and of course, eventually also upgrades to our systems to keep them, technology on the cutting edge of technology and technology relevant. Operations, we work very closely with operations, but our operations team usually rely on the engineering department, to do the engineering work. Then the third focal area is collaboration and integration. We deeply collaborate with many stakeholders, ranging from astronomers, scientists, other engineers, and also our international partners, of which we have quite a few. Integration-wise, we make sure that we integrate the various systems into one collaborative whole to ensure that we have a seamless and powerful observatory. And then last but not least, project management and system engineering, to make sure that all the projects is on time and within budget and keep to their objectives and deliver against their objectives. We've got a very strong project management team. And system engineering is underpinning all our engineering work. Now, as you all know, system engineering is a very collaborative and integrative approach that we're following to ensure that our systems from design right through to retirement are, well optimized. So those are the 4 pillars that we're working on, underpinning. So we also, as I mentioned, have some program managers, and we have some key programs within the engineering department. First being the Meerkat program, looking after all the Meerkat projects, including the Meerkat extension project. We also have a program aimed at SKA Mid specifically, because we've got quite a few contracts with SKAO that we are involved in, and that's under that program. Then we have the African VLBI network program, and there's also an Africa program. And then the other program within the engineering department is guest instruments, looking after all the other instruments on site, such as Jira and Hyrax, those kind of guest instruments that are being hosted on the site. Now, there's another bullet called Other, because there are other programs outside of engineering within the organization as well. So today, to a large extent, our speakers from the various groups will focus on a Ghana case study, but they will also talk about what they're doing, in all the other areas and looking forward into the future, what their plans are. For those that don't know, the African VLBI network is a Pan-African project with the aim to develop a very long baseline interferometer. There's 8 partner countries, 8 African partner countries that are part of this endeavor. And the idea then is that the interferometer be spread across Africa. And the objective is to develop skills, regulations, and institutional capacity required for the SKA. Now, the 8 partner countries supported South Africa's bid to host the SKA Mid, and you can see the outlying stations there, the white dots on the map of Africa. Those are the partner countries and the intended SKA outlying stations eventually. And you'll see they spread well throughout Africa. And each one of those partner countries are part of the African VLBI network program. On the Ghana specifically, the AVN implementations focused on the conversion of an existing very large diameter telecommunications dish that was transferred from, I think it was from Vodafone to the Ghana Atomic Energy Commission. And we've been working with the Ghana Space Science and Technology Institute for quite a few years to convert that facility into a radio telescope. And that is what many of the speakers will talk about today. The other approach that we had, 4 of the African partner countries do not have these large telecommunications dishes. And the strategy is then to build new stations from, it's almost a greenfield development then. The conversion of the large dishes has proven to be quite a challenge. So maybe in future, the rest of the African partners will also look towards having new stations developed. And I think that's probably it from my side. Yeah, that's it. So I'm now going to hand over to firstly mechanical. I've got 3 presentations. First being Yapi, talking about the antenna conversion in Ghana.
Thanks, Boris. I think you went over your allotted 5 minutes, by the way. You went over your 5 minutes. Afternoon, everyone. So this used to be like a 40-minute presentation, I think, and we 15 or 20 minutes down already. So don't blink. Right, so I'll talk a bit about the characteristics of this antenna that we converted in Ghana. The major modifications that we've done, there's quite a lot that we did. We're only going to cover today centering of the antenna. Then Wayne will be talking about the new azimuth bearing and encoding system. Tabang will talk about the track level compensation system that was incorporated. And we also replaced the quad legs, and we'll have a quick look at some of the performance checks we did. So as Kobus said, one of the partner countries, Accra, for those of you that don't know where it is. Kuntunsi is the station's name. That's about 25 kilometers northwest of the capital, Accra. It was originally built by TIW Systems, which is today's GD Satcom. And it forms part of 9 similar, well, it formed part of 9 similar antennas around the world, which formed the Intelsat network. It's been out of service since 2009, when it was taken over by Vodafone. And then somewhere in 2012, it was identified as a suitable antenna for conversion for the AVN network. These are some photographs that we found in an album on site way back late in the 70s. A group of Canadian engineers went to build this antenna there. It's got quite interesting history. If you look on the bottom row there, sort of second from the left, the crane actually collapsed when they installed the backing structure. The ground properties weren't properly evaluated, and the outrigger basically went into the soil. We also planned some craneage operations there, so we obviously a bit nervous about the operations, but luckily everything went quite well. So just quickly about the antenna itself, it's a 220-ton wheel and track type antenna. We're operating a beam waveguide, 32-meter diameter, elevation range 5 to 90 degrees. The azimuth range originally was quite limited. It operated as a satellite Earth station, and it only really pointed to 2 geostationary satellites, so very limited movement required. And we increased that quite dramatically to plus minus 305 degrees for radio astronomy. So that's one of the other major mods that unfortunately we won't be discussing much of that today. Then the antenna itself, quite remarkable wind speed performance, operating up to 80 miles per hour and survival up to 120 miles per hour. So one of the first things that we noticed is, I hope this laser works. Yeah, so in the middle where the azimuth pintle bearing sits, this antenna actually didn't have a full bearing. It had these 4 pintle bearing shoes that you can see on this picture here. And when we went and did some measurements there, we found that the gaps aren't equal. And basically that meant that this antenna wasn't rotating around its center anymore. It actually moved off its center. And so the science people let us know that that's going to be quite useless. We're off by about 70 millimeters for any sort of meaningful data. So we had to fix that. And the only way that we could do that was basically jacking the antenna. So we had 4 100-ton jack underneath these wheels 1 and 4. And we had a 5th jack in the center. We first rotated it and got it to the worst offset position, jacked the antenna and moved it across until we had a laser alignment system that we could align the beam waveguide with. So that was one of the first major tasks. Then also the quad legs, you can see here we're in a very poor state of repair, very bad corrosive area. For some reason, we don't quite understand why. And I obviously had to be replaced. And one of the big tasks that we set to do is to actually not do this in South Africa and then ship the parts to Ghana, because the Ghana Atomic Energy Commission had their own workshop, and they said they were actually making these fuel storage tanks. And they said, well, as long as the quad legs are not elliptical, they're round, then they can make them there. So we said, okay, let's go for that. So the first thing obviously was to just make sure that their processes are all aligned with what we would want them to be from a quality point of view. And we insisted on, they've got a very good X-ray facility there. So X-ray inspections on all the, on the circular wells, 100% inspection, and visual inspections and so on, of course. So we had them weld up first a typical section of what would be in the quad legs, and then had the welds analyzed, and then there was some training required. Fairly good welders, but they needed some more training. And this is a South African company representative that went across there and did the training over a period of maybe a week or so. It wasn't very long. They just needed some guidance really, and very quickly they could do these 300 millimeter welds without any defects, which allowed them to get their weld certificates to the American welding standard. So 2 of them were qualified, were certificated to weld the structures. This is just a photo showing them doing the welding and assembling. So the quad legs were made up of sections that are rolled and welded. It's a major operation. Basically, those 2 guys did the whole job. This is a photo showing the craneage that we had to employ in order to remove the old quad legs and replace the new ones. So the biggest crane we could get in that region had to go through the side, yeah, which meant we had to remove some of the panels on the dish. This was the day that we actually did the lifting, so the old ones were removed. They actually had to be braced so that they don't collapse during the operation. Excuse me. And as luck would have it, a massive thunderstorm erupted on that day. It was clear blue skies in the morning. Anyhow, we lived through that as well. This is the next day showing the installation of the final leg and the subreflector lowered back into place. Then the antenna steering control system, quite an old analog system. We couldn't get parts for it anymore. So we redesigned that with state-of-the-art servo drive system, and we built a test rig for that, Cape Town offices to qualify the software and the systems surrounding that. This is just some checks we did on the subreflector itself to confirm its service accuracy using photogrammetry. And then this is just a slide showing the analysis work that was done to predict pointing error. So starting out with 2D hand-drawn drawings that we got from site, generating the CAD model, very detailed. One of the Ghanaians actually did this. Converting that into FEA, getting the deflections out, and then finally the error map and associated pointing error. This was a logography done at 12 gigahertz, I believe, just to confirm the surface accuracy that we were after. It also indicated that the subreflector actually is in the wrong position by about 50 millimeters. And that's that from me. I hope that was in time. Thank you. Thank you.
So next up will be Wayne, also on mechanical side of things. I think if there's any questions, if you can leave it, till the end of the session. So Wayne and then Tabang. Wayne, please.
Right. Hello, everyone. I'm Wayne, one of the mechanical guys. Wait, let me see if I can get this moved on. Right, so what I'm talking about is the azimuth angle compensation system we did, and that comprises 2 parts. It's a bearing to help the antenna be centered, and then the encoder, which would also run off the bearing. So the introduction, I'll just give a brief overview of it, and I'll look at the wheel slippage we had. I'll look at the original design, and then what we did for the new installation. I'll add a few installation photographs, and then I'll just show the test rig that we used just to verify everything was right before we went to site. Right, so as you've probably seen on some of the other slides. That's the Ghana antenna. Just to get a idea of concept, I've just shown a picture of guys working on the inside. A few specs. So if we're looking at the antenna working at a site mean wind speed, we're expecting about 36 kilonewtons of load to go actually through that bearing. And the requirement was at that loading, we didn't want the encoders to move more than 2.5 millidegrees. And we didn't want a bearing deflection of more than 20 microns. If we went to survival or a drive to stow at 120 kilometers an hour, we expected about 960 kilonewtons of radial load going into the bearing. Although the design is such that only 180 kilonewtons would ever be transferred to the bearing. So the others are taken up a different way, and I'll explain that just now. Right, so as I said, we had a bit of wheel slippage, which was one of the reasons we needed to move the encoder from a wheel, or in this case, it's actually a resolver. And the right picture shows the resolver that was on the wheel. And what we found is if you move the antenna in azimuth back and forth a few times, you'll see that coming back to the original position, the wheel is actually off. And those two photographs were just a demonstration. So the left-hand one was starting, the red is the track, and then the white was the wheel. And the middle picture shows how the wheel is actually slipped. And so your resolver is not reading correctly. So that is not good for radio astronomy. Right, so what did the original system look like? So the Ghana antenna has got a large concrete pintle post, and into that, there's a steel ring. So the steel ring I've shown in brown. For context, that's about 3.2 meter diameter. In the center of that, there's a feed horn, which I was threatened that if I damaged it, I didn't even need to come back to South Africa. And then, as Yapi was explaining, on those 4 blue areas, there are plastic pads, and they rub on the pintle ring. So for telecommunications, that's fine. But when tracking is involved, it's not good enough for radio astronomy. So what did we do about it? Oops, wrong button. Right, so that's our new design that we did. So pictures disappeared. We took 6 bearing support brackets, which are the dark brown colors, and we drilled and tapped into the edge of the pintle ring. So the top right-hand picture shows the drilling we were doing. And we bolted these and supported them in the 6 positions. On top of that, we fitted a bearing interface ring, which is the red ring directly on top of that, which goes over the beam supports for the waveguide. And that we would center very accurately. On top of that, we mounted the bearing. And then on top of the bearing is the purple ring, which was a stiffener ring. The purpose of the stiffener ring was to ensure that we didn't put any direct load in one point on the bearing, causing deflections of the bearing and causing any lockup. So by having a stiffener ring, it spreads the load out evenly. Then on the 4 points where the pintle pads were, we removed those supports and we added other pintle pads supports into that. Those also have plastic pads, but not intended for rubbing. They have about a millimeter clearance. And the intention is when your wind speed picks up and you're above about 180 kilonewtons, that gap is closed. The remaining load is then transferred through those pads. When the wind comes off, those gaps open again. So your bearing will only ever see about 180 kilonewtons. Between those pintle pad supports and the purple ring, we've got 4 yellow plates. Those are flexure plates. So the intention is that the radial load is transferred very rigidly, but if there's any axial movement, which could be maybe from a track undulations, or if the exact leveling of the bearing is not correct, that will flex and it won't put any sort of moments on the bearing we don't want. So the bottom right picture just shows those 6 plates put in, and then the one is an example of the pintle support. Right, so how do you get these items into that room that are weighing sort of not quite, but close to half a ton, without damaging a feed horn, and without injuring anybody? So we cut a slot into the side of the house, and with quite a detailed lifting plan, we rigged it up, and the crane was actually suspended on the backing structure, and lifted it up to the slot, and we dragged it inside with some other rigging. Once inside, the bottom left picture, we lowered it over the feed horn. You can just see the feed horn sticking out in the bottom picture. Then the middle picture is the flexure plates, and we've installed one there. What you'll notice there is that there is some wires coming from the top. So that is strain gauged. So we had those calibrated, and it was used for commissioning. When we started the movement of the antenna, we wanted to verify that there weren't any loads going through that we didn't expect. So that was just a way that we could prove the system. The very right-hand picture is the encoder. So the bearing has got a very accurately ground gear teeth on the externally. The encoder has got two brass gears, which have some sort of anti-backlash system. So, and that just provided very little backlash going back and forth. And lastly, before we sent anything to Ghana, we had to verify that it worked in Cape Town, because you can't get there and have things go wrong. So we built this test rig in Cape Town. The left-hand one is partly built, but that's the bearing we installed. It's about 1.8 meter diameter. The right-hand is the CAD model of the system. What we did have on the system is a hydraulic ram, and that would verify side loads. We could use that to read the encoder as well. And that's all from my side. So.
Thanks, Wayne. Next up, Tabang.
Good afternoon, everyone. My name is Tabang, and then I will be talking to you about the TLC system implementation, which is the track level compensation system that we implemented in Ghana and antenna. The first thing I'll go through the introduction and context, basically why we need track level compensation system. Then we'll look at the TLC system overview, the sensing sensors we selected or measurement sensors we used. And secondly, we'll look at the TLC system hardware, like the location we selected for mounting the sensors. And we'll look at the FEA analysis that we did to validate the location for mounting the sensors. And then we'll look into the data processing, where we use Python for that. And then ultimately, after the data processing, you get your azimuth profile, basically how your track looks like. And eventually, we will look at the performance evaluation of the TLC system. For that, we used optical pointing to validate the track performance. We're basically in the process of doing that. The weather in Ghana is not ideal for optical pointing because it's quite cloudy. So why do we need a TLC system, track level compensation system? As CRP and Wayne discussed, the Ghana antenna is basically a wheel and track type of an antenna. So basically for your azimuth movement, the antenna rotates around its central axis with 4 wheels rotating, moving in the track. So the track unevenness is basically the major contributor to the mechanical pointing errors. It causes a repeatable tilting of the antenna structure. Because the nature of the error is repeatable, we can compensate for. So the causes of the track unevenness, basically the manufacturing and installation tolerances. We can't manufacture something to perfection, so there will always be tolerances. The gaps between track segments. So during installation, of course, there will be gaps in between, so that can cause tilting of the antenna, and then degradation of the track over time. As the antenna get used, it degrade, and then that creates low and high spots. So we had a requirement to work with. We got from the AACS requirements document. So it basically states that the AACS must use a continuous measurement system to generate a track level compensation lookup table. And secondly, it must monitor the track level degradation over time. And the resolution for the system should at least be 0.057 millidegrees. For the overview, for track level measurement, we selected the TEF tilt 420 high gain inclinometer. The resolution is 0.01 millidegree, which is quite good within the resolution we were given. And then to house this, we had to design a custom enclosure for it, and we had to protect it from the elements. So inside there is that head thing there. Sorry. So basically inside there, that's where the sensor sits, and then it is an environmental seal to prevent any water ingress. And for initial installation, we had to include fine adjustment nuts so that it is leveled, and we had to use a sun shield to protect it from the effect of the sun. Then next slide. And then for the inclinometer location selection, so we had to select the location to mount the TLC system. And then for that, we use the finite element model of the Ghana 32-meter antenna. And we identified node 45 and node 42, which I'll show you them in the next slide. Basically, that would be node 45 and that would be node 42. Those are the locations we selected. So what basically T1 and T2 means is tilt sensor 1 and tilt sensor 2. We selected those nodes because they are very close to the elevation axis, so they will capture the Y rotation quite well. If you look here, if you zoom into tilt sensor 1, the location there's how the tilt sensor will be mounted. And you will see that for your global Y rotation of the antenna, it's going to be captured by the X tilt of the inclinometer. And then for the X rotation of the antenna, it's going to be captured by the Y tilts. And then there are equations here that translates the global X rotations of the antenna from the Y tilts of the inclinometer readings. And then the Y rotations is given by this equation. And then for the Z rotation, it is basically your twist of the antenna as it rotates. And the equation for that is worked out from this, basically using the inclinometer readings to translate from local rotation tilt of the inclinometer to the global rotation of the antenna. And then here's just the overall antenna structure model of the Ghana 32-meter antenna. This is just a early structure where the main dish is mounted on. And then for the FE analysis, in order for us to validate that the location is optimal, in the finite element model, the procedure was quite simple. We applied a displacement load from 0.5 to 0.3 incrementally in the Z direction, while we have fixed the remaining 3 wheels. We applied the load in 1 wheel and fixed the remaining 3 wheels. And from that, we selected node 50 as the reference node. And then using the tilt readings or the nodes rotations that we get there and there. So those two nodes actually simulated the inclinometers. So using the equations above, we are able to calculate the antenna rotations that is picked up by the inclinometers, and we compare those rotations to the reference node. And from that comparison, if you look at wheel 1 only here, you can see that we are getting a very good correlation in terms of the reference rotations and the simulated rotations that is captured by the inclinometers. And then we repeated the whole process with all of the wheels, and then this is your correlation coefficients. And then we noticed that there's a very good correlation with respect to all of the wheels. Therefore, the locations were optimal. And then the next slide. So after we've plugged in the TLC system, the data we got was very noisy. And this is what we got when we plugged in we did a track survey, 360-degree, clockwise and counterclockwise. So what we got is basically this kind of data. This is something we cannot use. So we had to use Python and various libraries to filter the data. And ultimately, after this is what you get after filtering the data. So after we filtered the data, we had to remove the azimuth axis tilt, which is the natural tilt of the antenna, because that is compensated for in the pointing model. We had to remove it. And in the next slide, this is what you got after removing the azimuth axis tilt. So what this basically tells you is basically it gives you like from 0 to 360-degree, it tells you where your high spots are and the magnitude are here in the in the Y direction. So basically it just gives you, you can visualize it in this manner. It gives you where your high spots and low spots are on your track. Now, using the equations we looked at above, we're able to take this track angulation and then translate them into the global rotation of the antenna in the Y, X, and Z direction. And basically, this is what your lookup table looks like. And then now to evaluate the performance of the track level compensation, we had to use optical pointing. So we pointed at multiple sources and gathered the data. And from those images, what we did, we using Python for data processing, we detect the center of the source and get the offset of the center of the source to the picture frame center. And that offset, we compute the azimuth and elevation errors from those offsets. The TLC, of course, is implemented at that stage. And then from there, in the pointing model, we take those azimuth and elevation offsets, we reverse the effects of the pointing model, and what we get is a total azimuth and elevation errors. From there, the next step is we derive new pointing model, but in two ways. Here we reverse the effect of the TLC system, and here the TLC system is implemented. From these two, we can compare with and without the TLC system, how much of improvement we are getting. So basically, that's the workflow for evaluating the TLC system. Okay, thank you.
Thanks, Taban. That brings to a close the mechanical part of the presentation. We have less than 40 minutes left and 4 presentations to go. So I call on the next speakers to please speed it up. Next up is Len, and he will talk about the electronics part conversion.
Thanks very much, Gwibus. Okay, so I'm going to try and keep it as short as possible. So I'm going to go through the slides as quickly as possible, and any questions afterwards can be asked. I'm just waiting for the slides to come up. Press the button. Okay. So let's move on to the first slide. So the introduction is that the electronic team for the AVN was called upon to do a lot of different works. So I'll just go through the introduction, the controller monitoring, the temperature controller, the maser facility, and all of the temperature controller results. And then we'll show some multidisciplinary stuff that the electronics have done in terms of doing construction. Okay, so our first point is that the team core supports most of these things: electronic design and development, FPGA coding, software, and then we got an optical fiber team. So that's how our electronic team is structured at the moment. Okay, so for the AVN, one of the most important factors is the human capital development. So all of the work that we've done in Ghana was done with the Ghanaians. And we mentored them in the beginning of the program all the way through, and we did the training with them, and we used them to assist us, because none of the work that we did could have been achieved if we didn't have a team of people on the ground in Ghana helping us. Because normally we would be 2 or 3 people traveling at a time, and we would use our counterparts to help us do it. So without them, we couldn't have achieved what we did achieve, and we achieved quite an amazing feat. So yeah, so we did the electronic team did the ASCS design and wiring of the antenna, design of a RF and a RF controller and an infrastructure controller, then modification and installation of the 2 antenna interferometer. I don't know why it's actually so big, but it does go down to the EMS and the Maser facility. So I'll just jump to the next slide. Okay, so the Maser facility was a task that was asked of us to actually help with the infrastructure work, developing some form of an anti-static flooring in the building, a temperature controller, and vibration isolation. And the infrastructure sensors and monitoring monitors all of the rooms within the main building for humidity, temperature, doors open and closed, and that kind of BMS type arrangement. We also had one in the Maser facility that would monitor the temperatures within the rooms, so that we could compare that to the temperature controller's feedback to see how well the temperature controller was actually doing. But although the sensors for that was not as accurate as the temperature sensors used for the monitoring system, the control system. So we will go through that. And then the EMS was developed between Sarau and Heartrow. We based the environmental monitoring system on the Heartrow system, and we built it, the electronics identically to theirs, and we added a solar charger and a battery charger to that so that we could get our data continuously. Okay, so this picture just represents the models that we did to do the Maser facility. On the right-hand side of the picture, you see there's a concrete block with heaters on it, and then a representation of the Maser that would be housed on top of that. And there's cork on the bottom, there's rubber, there's a board, the concrete block, then there's zorbothane and marble top. And those all have different natural resonant frequencies, and those natural resonant frequencies cancel or mitigate other resonant frequencies. So it turned out that we had one resonant frequency we could not get rid of because it's a combination of all of those resonant frequencies, and that was 12 hertz. So that block basically resonates, has a resonant frequency of 12 hertz. Looking at the three rooms, the main 3 rooms. So on the veranda, we have a diesel generator that is a backup diesel generator. The first room is the equipment room, and the equipment room houses the equipment. It houses the temperature controller and the air conditioners on the wall. So the design of the temperature controller was a very simplistic design. It was 2 standard air conditioners that we can alternate for maintenance, and a temperature controller that did not use fans or forced air or anything into the room. It uses natural convection of heat and a cycle. So the equipment room is cold. We then pump the cold air in at the bottom of the room. We heat it up on the heaters at the bottom of the pedestal. That rises, it causes a bubble around the Maser facility. It then has holes on the top of the wall, which the circulation happens, and we circulate it naturally. One of the things is we didn't want to use fans and things that needed maintenance. We don't want to do that kind of arrangement. And at the present moment, this topology and the way we're doing it is working very well. So just all of the different activities that we did was we had to do the ceiling frames. We replaced the roof sheeting. We had to insulate the walls. We had to put self-leveling screed on the floors. You can see there's Henry painting. And we had a good team of Ghanaians helping us. We put in cable trays. So we fitted this room out to have all of that. And before we could even put the temperature controller in, because we needed it to be completely isolated from outside and keep the outside heat out. So that's what we did there. So here's some of the temperature results. And I think the bottom plot on the right-hand side is the one that you need to look at the most, because you can see the two blue lines represent the ±2 degrees, around 27 degrees. And one can see that we way better than, as far as I remember, the results was 0.09 degrees that we met over a 24-hour period. So we are meeting a very tight specification in terms of temperature, and we're using the most simplest way to do it, and that is not fight with nature. Let nature work for us and not fight against nature. So here's just multidisciplinary type stuff. You can see we did all of the work ourselves, between ourselves and the Ghanaian team. All we were there was to do is to manage and facilitate the activities that happened on a daily basis. Thanks very much.
Thanks very much, Lynn. I think we should move on. If there's any questions, I'm sure the speakers will be available after the session to answer any questions. Next up is Wesley on receivers.
Hello, everybody. My name is Wesley, and I'm presenting on behalf of the receiver team. It's that one to skip, the green one. Okay. So let's get started. This is just a summary of what I'm going to be presenting on today. There we go. I'll talk briefly about the receiver that we developed for Ghana, and then we'll go into some of the other projects that the receiver team is currently busy with. I would like to claim ownership of this photo. I took it. That was used previously, just to properly attribute it. Yeah, we've already seen this photo, but it's a slightly bigger one, and it just shows this, gives you a sense of the scale of the dish, and nicely aligned with the moon and in the just above it. Moving directly to the block diagram of the receiver system, the receiver subsystem. Just go there. So it's maybe too much information, but it just shows the from the main reflector and subreflector through the beam waveguide into the feed horn. Oh, I can see it there as well. That's cool. And then into the receiver front end, which is made up of stage 1, 2, and 3. Mainly, the purpose of the front end is low noise amplification and down conversion, and then to the receiver backends, which have a few purposes, but yeah, I think that pretty much covers everything. The green one. Then just a zoomed in photo, picture or a 3D model of the receiver, just the stage 1 of the receiver, showing just the complex waveguide structure with the filters, the waveguide filters, the polarizer, the ortho mode transducer, and where the low noise amplifiers go. There's some specifications on the screen there. You can see it. I'm not going to go through it in too much detail. Yes, let's move on if everyone's happy. Cool. This was pretty cool. So the first time doing hot load cold sky testing. Photo on the right is in Cape Town on a nice little, very convenient little forklift that we can just wheel in and out. And the one on the, sorry, that was the one on the left. The one on the right is in Ghana, the final testing when we were characterizing the receiver and calibrating the noise diodes. It was really a great experience at this point when you lift that ambient load and you're looking at cold sky and you actually see the temperature dropping on the spectrum analyzer. And you can actually physically see something that you know in theory, but you're seeing it actually, actually happening in front of your eyes. So very cool experience. Definitely one of my highlights is doing the testing on sky. This was another one of the highlights, was actually while we were installing the receiver at the right time, because it was after YAPI had done all of their corrections and they were able to point quite accurately. Peter actually and the software team were busy doing some pointing and testing that system. And they said, why don't you just capture some data while we're pointing at a maser? We're doing maser tracking. And so this is not scientific at all. This is from an engineer's point of view. But I just think it's really awesome to be able to point and capture data with your receiver that you've built, see it with your own eyes, you know, and see something that's awesome. So let's skip past that quickly. So on to some other projects that we're busy with in our team. This is the cryogenic test facility. The purpose of this is characterization of low noise amplifiers at cryogenic temperatures. And the status of this is at the moment, we're busy doing the ready for stability testing. Yeah, so that's on the left-hand side, the 3D model. On the right-hand side is the actual photo of the current system as of a few days ago. Then another one of our projects that we're busy with is the wideband ortho mode transducer, wideband ONT. And the goal of this was to simplify that a complex structure that was in the Ghana stage 1, and to try to, yeah, essentially that was the goal. By making it wider band, we can use it for both bands essentially at once. And it's been pretty successful. Yeah, there's some results. I think I'm going to not spend too much time on it because we're a bit low on time. But if you want to know more about any of these things, please come and talk to us at our stand. More than happy down in the exhibitors area. We're more than happy to discuss it further. Another one of the competencies in our team is antenna beam pattern analysis, using holography to characterize the radiation pattern and the surface of the reflector and subreflector. Then arguably, I don't know if you've heard about this thing called MeerKAT, the MeerKAT telescope, but arguably our most in our team, our most successful product has been the MeerKAT digitizer, and there are some specifications: 2.2 gigasamples per second max, and 10-bit ADC. That was the limit with this digitizer, and we are still responsible for ongoing maintenance and of the system. So, not too much more to say about this. The next one, or let's say where we're going with this, is the next generation digitizer. So this is what we're currently busy building and qualifying, is making the digitizer wider band. So we want to get the instantaneous bandwidth is being designed for 3 gigahertz, and direct digitization up to signal of 6 gigahertz. Yeah, and then also, yeah, so the final thing I want to mention here is the option to include down conversion in the digitizer. So, and then finally, actually, the other idea here was to make it more generic, so the modules can be used for more than just one purpose. And that's it. Yeah, I think that was pretty short. Pulled it in. There's our team. It's a bit of an old photo, but we managed to Photoshop the new team member in. So yeah, there's contact information. If you do have more, it was a very brief presentation. If you want more information, please contact us or come to the exhibitor's stand. Thank you.
All right, thanks. Thanks very much, Wesley. Next up is the digital processing and pipelines team. Is that correct? Yes. James Smith and Andrew. Thank you, Roy.
Okay, thanks, ladies and gentlemen. As Kobus has said, I'm James Smith. So as Wesley has explained, the Ghana telescope has two main purposes, both to do VLBI and single dish observations. So this is also a little bit of an old picture, but it shows both of the digital backends. So the analog signal chain plugs in there. And this is the next stage in the pipeline. So on the top is the single dish backend, which we developed in-house, and I'll be focusing most of my attention on that today. This is the first iteration, which was intended to be paired with an older model of that receiver. On the bottom is a backend for very long baseline interferometry, and that's taken off the shelf. Granted, it's a very expensive shelf from a small manufacturer in Italy. So the job of the digital backend is to perform the first stage of reduction. So there's some initial signal processing, maybe some time averaging, and then passing the signal on for long-term storage in a format that is useful for the user downstream, whether that's an astronomer or a VLBI correlator. Before I delve too much into what we're going to do, I want to sort of make a bit of a hat tip to Casper, which is the Collaboration for Astronomy and Signal Processing and Electronics Research. Soraya has for many years operated as a part of Casper, which originated in UC Berkeley, but now has collaborators all over the world. The purpose of the collaboration, quoting from their website, is to streamline and simplify the design flow of radio astronomy instrumentation by promoting design reuse through development of platform-independent open source hardware and software. And the Ghana single dish backend was developed using Casper hardware and software platforms. So the first iteration, we've seen a picture something like this a little bit earlier. This is called a roach. So it's a bit of a Casper tradition to name boards after insects. So it was built around Xilinx's Vertex 5 platform, which was at the time the top of the line FPGA for signal processing. The roach was initially designed to function as a processing node for Cat7's correlator, which was the first interferometer built by Soraya. It was such a successful design, it ended up all over the world. So we use it in Ghana. The FPGA bit streams were based on Cat7's F engines, but without the complicated parts required for interferometry. So it was a great case in point because we could reuse existing IP and get the job going relatively quickly and at relatively low cost. Roach 2 was developed after the Roach platform. It was very similar in design, but leveraging the improved capabilities of the Vertex 6 to work in the initial prototype correlator for Meerkat. And during the course of the Ghana project, we realized that the original Roach was not clocking it fast enough to handle the bandwidth and the frequency requirements. So the IP was ported over to Roach 2. The porting process was relatively quick, only took a few weeks. So yeah, that was a successful project. To give you a bit of an idea of what's going on under the hood, the signal path goes through some amplification, as Wesley taught us about. It gets digitized. So in Ghana, we have the digitization inside that box. Then those four sort of, there's a laser. These four blocks happen on the FPGA, the ADCs, and an add-in card. There's a polyphase filter bank to do channelization. We calculate Stokes on the FPGA. There's some accumulation for a variable amount of time. And a packetizer sends the data out over a 10 gigabit link to a analysis computer, which is acquired. It's combined with relevant metadata, such as the telescope's pointing, environmental conditions, and then stored to hard drive. So to give you an idea, here's just some numbers for the sake of completeness. We have three main observing modes. First, a wideband spectrometer, which is used for continuum radiometry. A narrowband one, which is used for maser observations, such as the one that Wesley talked about. And there's also a pulsar timer using some user-supplied equipment from the University of Manchester. I wanted to highlight it's quite cool that a small thing roughly the size of a pizza box is able to do all these various different things, which is for me, quite an interesting use of technology. Over to Andrew. Thank you.
Okay, so I'm going to follow on from James a bit and talk about stuff that was happening a little bit, not the LBI, but about some of the spectrometers and correlators we built. So basically, our organization was birthed from the SK sitebed in the early 2000s. A small team of engineers was formed from around 2005, and we began looking into different radio astronomy sort of technology, which we didn't have much experience with here in South Africa. So pictured here on the pictured here is a FPA that we actually bought from, well, we got from the Australian CSIRO. So this is on one of their dishes. We actually got one of those and we played with it in the early days, and we were using a custom software and some bought sort of ADCs that we got. That was in 2006 when we sort of the year after we sort of first started. In 2007, we attended the first Casper workshop. James spoke a little bit about them. And we became part of the collaboration. It sort of made sense to us. They had some useful stuff. We acquired one of their hardware boards, which was called an IBOB, Internet Breakout Board. And we used it to build our first spectrometer, which we used to test the first prototype Cat7 dish, which we actually built in Hartral, which was up in Pretoria, because we didn't actually have anything really on site at the time. So you can sort of see it off to the right there of the main. This is the main Hartral dish, and the little prototype dish was installed there, and we use it for testing. And with that, so we built something called the XDM. So it's a little 2-input, as I said, using the IBOB board. And that sat on the back of that and was actually used for science for quite a long time, I think pulsar stuff. So in 2008, we built our first correlator. So it was it used a single Roche board and used Casper signal processing blocks. So pictured here, you can sort of see this is in MATLAB Simulink. So you basically drag these blocks and you sort of double click them and set their parameters and things like that. So it's like a graphical programming sort of interface. And basically we've used the Casper stuff like this all the way through to Meerkat. You can sort of see the 4 inputs as they come in. There's a polyphase filter bank, the first stage, and then the FFT, and then this goes on to more processing. And we actually did our first fringes. We've acquired our first fringes with this system, which we call the Fringe Finder, which we built to test the first 4 Meerkat dishes. We did it in India because we also didn't have actually our first dishes. So while we were developing this, we had to go across to India to use their dishes to get our first results. In 2010, we finished with Cat7. So pictured here is the system. So the analog RF over fiber came in from the dishes, and it went into the front of these Roche boards, which had the ADCs inside. You can sort of see the analog inputs coming in there. Inside this first stage of boards, we did channelization, and then we sent packets via Ethernet. You can see 10 gigabit switch at the top there into the second stage of processing, which is the correlation. So this was our first sort of system composed of multiple sort of processing stages and boards that we all had to tie together using the switch. Okay, and then from 2010 to 2017, we built Meerkat. So a lot of things happened during that time. So we obviously had a lot more dishes, 64 dual polarization sources. So that meant we needed, instead of being able to get away with a single switch, we needed like a huge switch, basically, that we built using smaller switches. So we have this big switch set up in the processing room. We needed wider bandwidth. So we developed Roach 2 and then Scarab, which is our final processing board. to be able to handle all of this. We have over 200 of them installed in the Karoo. We have multiple channelization options, different like data outputs. We have a beamformer that we added. We also changed to sampling at the feed instead of having RF over fiber. We sample at the feed, so the full system had to be asynchronous. So you're basically getting Ethernet packets coming into this big processing system, and Ethernet is routed around in packets, and everything is sort of data driven, all the processing. There's no clock coming in from anywhere, sort of clocking the thing. Yeah, so that's, and they're pictured here is sort of the, I would say is still the coolest picture that, from an engineer's point of view, cool science that we did, one of the early things. So this is a picture of our galaxy, and the cool part is the large sort of scale structures that you can, that is unique to sort of what Meerkat, well, it's what Meerkat does very well. These sort of big, not very bright, but cool sort of filaments and clouds and bubbles and things. And then Meerkat Plus. So we, starting in 2021, we started building the next correlator. So the idea is we're increasing the number of antennas. It's the same, built for the same specs as Meerkat, but fundamentally different implementation. So advances in GPUs means that they can actually process sort of these very high data rates that it used to be you only could do with FPGAs. Obviously, GPUs are off the shelf, and there's a lot of ease of development and lower costs and things like that associated with them. There's also a big switch upgrade. So we've got a second big switch linking all of these things together. And that's going to be deployed this year and hopefully next. Yeah, James is involved with that more. So I'm still from the old days of the FPGAs. And then, yeah, so a summary of all of that. So it used to be that we built a lot of our own hardware. We took advantage of the Casper idea and sort of shared hardware and shared IP, which is great. And these days, we're trying to leverage more and more sort of off-the-shelf stuff. So GPUs, obviously all the software that comes with GPUs, testing and things like that, with the idea that obviously we can do it cheaper and quicker. So instead of having these big black box kind of telescope instruments that it used to be, you build this thing like a military project and then ship it out, and it runs for like 30 years as a big thing that you have to maintain and stuff. These days, you can iterate every few years, basically. You just get the latest technology, upgrade, and take advantage of all the stuff that you can get with that. That's the idea. Yeah, thanks.
Thanks, James and Andrew. Okay, last but not least for today, Peter, Rowan, and Sidol on the software.
Hello, I'm Peter, software engineer from Sarajevo. I see we don't have a lot of time, so I'm going to go very quickly through my part of the slides. So first part is a background. As a hardware and mechanical and electronic hardware were installed, we basically every time we build a little simple interface, user interface for people to be able to control the antenna, to control the receiver. And then once we've done that, we got to the point where we saw that we need some integrated software to control the whole telescope. And then there was also a lot of different other protocols that we've used, and we've decided to build on the what Glenn mentioned before, the RF controller software, to more than our own proprietary protocol to convert all the other protocols into CATCP protocol. We've decided on CATCP because it's very known in the company and we use it all over. NASA field system was used to provide the VLBI capabilities, and also it interfaces with the VLBI backend. Then in the end, timing is very important. So every software component or computer system needed to be synced to an NTP server. Rowan will do more on the current software that we've done, and then Cyril will be talking about some future enhancements.
Thanks, Peter. So this is architecture of the software system. So as more subsystems were developed, they necessitated the need for some central processing unit, and this was a station controller, which provided the data flow and the action or the control from all the various subsystems. And as Peter said, they all needed to be synchronized through a network time protocol server. In addition to this, there was a lot of devices that were off the shelf that used a lot of different types of protocols. We use our in-house protocol that was also developed in conjunction with Casper, which was a CATCP protocol. And these needed to be translated into this CATCP protocol. And so we have a protocol translator. There's a few there that you might recognize, Modbus and SNMP, but there was many others that are proprietary, and we needed to translate that into something that we can pass the data around to all the various subsystems. The station controller software, obviously, the main purpose of it is to gather all the data from the subsystems as a user interface to provide control for the receiver and the backends and the antenna steering controller. Also have monitoring. All the monitoring of the sensors from all these subsystems is logged for use at a later stage. There is also safety sensing, so that when there's high wind speeds or power monitoring, the antenna can safely stow. And we have alarms when sensors go into error or failure states that the operators can be alerted to address those issues. And the tracking software the tracking is all done through the station controller system. And all the algorithms are based in the station controller. And lastly, we have the spectrum from the RF side that is displayed. So this is just a picture of part of the operator station. We can see the control and monitoring windows, and there is also the RF display showing the maser that Wesley showed earlier.
Thank you. The software to control and monitor the two telescopes, the Ghana telescope as well as MeerKAT, is quite different. And the difference comes in the fact that the Ghana telescope is a single dish. It has one receiver, it has one antenna steering controller, and one back end. Therefore, the operations of that telescope is much easier than the one that we use in MeerKAT. On the other hand, MeerKAT is an interferometer, so it has multiple antennas. To be specific, it has 64 antennas. Therefore, it will have 64 receivers and 64 antenna steering controllers and a correlator. The operation of MeerKAT telescope is complex. So if we do fix the operations of the telescope for MeerKAT, we can actually infer it to the Ghana telescope. Oh. And this one. Okay, sorry. The challenges for the two telescopes are also different. The Ghana telescope is in Ghana, as they have already said. So we have environmental and technological problems there, or challenges. Ghana is very hot, so the weather conditions affect the computer components. And affecting the computer components deteriorates the lifespan of the computer components. And therefore, there is a lot of maintenance that needs to go through for us to fix the computer components. On the other hand, MeerKAT is in South Africa, in the Karoo. We have more technological problems. We monitor the telescope sensors or the health indicators. For instance, one antenna has approximately 800 sensors that we need to monitor at any point in time. And we have 64 antennas, so it multiplies by a factor. And we are not only monitoring the telescope itself or the antennas itself, but other telescope systems such as the cabling. So this is done manually now to monitor the telescope sensors, and we could improve that. We also have a problem of time loss when scheduling observations. There are gaps in between observations, and we lose time there, and we are not using the telescope to its full potential. An observation takes place, and the expectation is for it to go to the archive. However, during the transfer process, there's problems, and then the observation doesn't get into the archive. So there's a time loss in the fact that the problem occurred. And therefore, when there is maintenance, we need to schedule it we need to fit it into the schedule. So we thought of future possible enhancement for the telescope. And we are thinking of a scenario where artificial intelligence could help us optimize and revolutionize our observatory to be an intelligent observatory. And that would be research and development to create an automated telescope operations, where we automate the scheduling of observations to have a timetable for like 3 months, 6 months, or 12 months. In this way, we'll be utilizing the telescope resources optimally. And we have an ever-increasing number of health indicators that we have to monitor. And it's quite unrealistic to expect a human being to be monitoring approximately 100,000 sensors at any point in time. So we need to we're thinking of creating a tool that will monitor these indicators and perform predictive as well as preventative maintenance to monitor the faults. And whenever there is a fault, it should create an alert to the relevant people. And when we do get to a point where we have an alerted fault, we need to squeeze in a maintenance into the schedule for us to fix the fault. And in that way, when we have a tool that will schedule, monitor, and maintain the whole telescope, we'll be creating an automated telescope operations. Thank you.
And that's it from us for today. Thank you very much. But before we go, I just wanted to mention in Ghana, the subsystems and the groups that did presentations, there's some more that we did. We've got quite a complex timing and frequency reference system, very well distributed between the main building and outbuildings. And we did a lot of civil works, a lot of digging, a lot of pipe laying, and a lot of cable laying. We also redid the entire electrical system for the facility, including the main facility and the major facility and everything in between. So we really, in Ghana, tackled, okay, apart from the dish, but as you saw, there were quite a lot of work on the dish to be done. But apart from the dish, we tackled each and every single component of the entire signal chain, as well as civils, engineering work that we did. So I think for the team, it was quite an accomplishment. We're not done yet. There's still some work to be done before we hand over the facility to our Ghanaian colleagues, and then we'll move on to the next one in the next partner country. So thank you for the speakers. We made up some good time, so we're just 3 minutes late. And also thanks for your attendance. You've got the contact information. Sorry it was so quick. You've got the contact information. If you need anything or want to ask any questions, please feel free to contact any one of us. Thanks very much, everybody. Thank you. Bye.
Thank you. Yes, apparently. Not sure why, but
Yeah, well, I don't know, I saw her yesterday, walking down the thing, but she.
conceived corona or Kendall's. So the session before it was not in the schedule. Yeah.
They were taught about session.
Okay, probably.
I think I put my Chinese name on. Yeah, that's.
Do you know if anybody is on Zoom? Do you actually see
Kim.
people? No, I mean, participants.
Yeah. They are.
Okay.
I'll track them.
The third person, so we'll see. And if she doesn't show up, we'll just move on to the next one.
Yeah, let's do that. Okay, can we start? Yeah, let's. Is there no Kim? Oh. No, I didn't mean the talk. That's the first presentation. Okay. Let's go. So my apologies. Apparently there are hidden sessions there, which did a little bit of overtime because we did a little bit of overtime. And so things are pushing forward. And I hand over to Wendy, who will chair the next two sessions.
Great. So I'm Wendy Williams, project scientist at the SKAO, also helping on the SOC. So now have the task of chairing the session. So without taking too much time, since we are running a bit late, we're going to start this afternoon session, Current and Future Impact of RFI, with Dharam Lal. And you will hear the audible warning that your time is running out. So go ahead, Dharam.
Good afternoon. I'll be speaking about the good, the bad, and the ugly part of Band 2 scenario of UGMRT. So just more than a decade back, we upgraded the GMRT to wideband system. So essentially, sorry about that. Okay. So essentially, I'll be focusing on Band 2, where essentially we replaced 150 megahertz legacy band 120 to 250 megahertz system. And the upgrade was done in phased manner, essentially. And we had band 4, band 3, and band 2. What you see on y-axis is the amount of improvement, the occupancy in frequency space as a function of various bands. So we essentially reached almost to 40 to 60% of the occupancy. This little piece is L band, and the yellow piece which you see is the Meerkat occupancy over there. And we essentially used the Meerkat occupancy and matched occupancy of band 4 and band 3. We built a project called SuperMighty. So when we did this upgrade, it was a fantastic scenario. We felt we are on par with many other facilities in terms of sensitivity or in terms of angular resolution. GMRT is not a great survey machine, but it did well in terms of survey compared to other. But the price that we pay is the following. What you see over here is power as a function of frequency occupancy. This is 125 megahertz, and somewhere here is 250 megahertz. And this is the band which you are seeing at band 2 of GMRT. This little piece is what radio astronomy protected band is, just 1.5 megahertz apart. This is one piece. And what you see here is the television signals from Pune and Mumbai, which essentially kills all the information that you can grab. And these are other terrestrial television signals. So we are living with many other transmissions, and we being astronomer, like we are ambitious, encroaching into other part. So I'll show you what best we could do. So I'll presenting few band shape one after the other. What things are, these are from the good part of the data. I'll show you the bad and worse also. So this is essentially some random set of antennas, R channel or the L channel over here. This is in units of channels, or if you want to see it in units of frequency, that is what is shown over here. And that's a television signal which has been killed over there. It doesn't get killed completely. I'll come to that again. So this is amplitude. This is how phases are behaved. And if you want to see it, two separate chunks below the notch filter and above the notch filter, like the television signal where things are, that is what this is shown over here. So this is the high part of the frequency. This is the low part of the frequency. And you may say that this looks very ugly. Give me a little time. If you are lucky, so this is again, what you see over here is amplitude and phase as a function of frequency. If you're lucky, you can even pick a small 3 or 4 megahertz band in this somewhere and make a fantastic image of few arc-minute across source to a very good sensitivity and dynamic range. And you can be a little ambitious. You can pick this over here or across the whole channel, and you can increase the signal to noise further. So this is something good if you're there. The scenario changes. There are occasions, even though you see a band shape which is fairly neat, you essentially have RFI sitting which you can handle. And I'll show you a little bit about bad and ugly part of this thing. So for extended sources, when you're talking at 150 megahertz or band 2 of GMRT, depending on what you're doing, you have to be a little careful. So what you see here is the full full band being used for L channel or R channel, or over here, you can use the lower part of this thing or upper part of this thing and separate frequencies. I'll take one at a time next. So this is a little bad situation, but in a decent state. So this is our Supermighty project data, which I'm showing at band 2 over here. So what you see over here is fairly neat. If the field is point source dominated, this field is XMMLS. Sorry. So this field is XMMLSS field. And if you're where there are no extended sources and you essentially reach few hundred microjanskis per beam as the RMS noise in any of the two channels, what here you see is the following. In a typical 8-hour observing integration run, I am asking a question once I've done the flagging, calibration, all data, low signal to noise has been flagged off. What is the fraction of data that is remaining? That is what you see on the y-axis as a function of spatial scale in band 2. This fraction is just a few %. It looks bad, but since you are point source dominated field, you're okay, and this is the best you can do. The difficult situation is the other part, which is ugly part, where you do the same thing. You only pick up a couple of point sources, but this field has essentially supernova, which is 40 arc-minute across. We do not image this supernova. And this is again the same plot, fraction as a function of spatial scales, a few % over there is what you're seeing. So even though data look decent, good fraction was flagged, and if we could salvage some bulk of it, we couldn't map the extended diffuse structure. Okay. This is next piece. What I'm showing you here is essentially time as a function of frequency. So this is 250 to 125 over here. So this is a filter where television signal is. If you look at it, this little 1 hour over here, this is kind of police wireless communication. This kind of kills the whole signal. And I was showing you results from this part of this band, which looks decent. We are working on this thing. We know how to handle this part also and see that the whole band doesn't get saturated. So that's something which is happening. We're also working on, suppose you have a field and you ask a question, this is the center of the field and I want to go to the primary beam or first null. What are the satellites which are communicating? We can tell you exactly this frequency, this timestamp. You need to just flag it out. That's when the satellites are communicating in your field of view. Right. So I showed you a good, a bad, and ugly part of situation. So the main challenge that we are encountered have been taking care of man-made RFI, and it's the biggest challenge. Containing self-generated RFI, that's another big challenge. Mitigating RFI from external sources, you'll be hearing from Kaushal and Divya Oberoi also about this. And of course, we are broadband impulsive RFI and spectral line RFI, which we are struggling with. So this was my version of the good, the bad, and the ugly of RFI scenario at band 2 of GMRT. Thank you. I'll take your question.
Great, thank you very much, Dharam. Just a quick reminder not to forget those people who are watching online. We will probably take questions from the room first. And just to remind everybody, we have the Slack channel. So if you have questions also to the speakers from beforehand, do post them there. And a reminder to the speakers to look at them. Any questions now for Dharam? Anything? Oh, yeah, okay.
In one of your very first plots, you showed a wideband spectrum from the RFI team. Oh, actually, I guess it looked like the power went up and down. The baseline was not flat, particularly at the lower frequencies. And do you know what the excess power, what's causing the baseline to fluctuate like that?
Yes, you caught me. And so to answer you, the baseline is definitely not flat across the two ends of the spectrum. And the pattern which you are seeing is essentially how the electronics is. So that we are limited by that part over there. But further, if you look at 110 to 150, that baseline is also not flat, it's fluctuating. And that is again how the electronics is. But that's correctable. Like you essentially have a large band and you can do that.
Okay, any other quick questions? Otherwise, we will move on. Thank you very much, Dharam. Our next speaker is Harry Chiao. I'll be speaking about the impact of satellite constellations. So go ahead once we have your slides up. Okay.
I guess one page ahead. Do I press this? It works? No. Nope. Can I go back? Okay, cool. Hi, I'm Harry. I'm the radio spectrum scientist at the SKA Observatory. So today I'm presenting on behalf of the Radio Spectrum Management Group at SKA. And we're looking into some of the active transmission impact from satellite constellations to the future SKA Band 5. So just a bit of background on how satellite RFI appears in our data. As constellation sizes will expand exponentially, the impact to radio observations will just be increased even further. And on the image on the right, this is an example of 18 hours of imaging from ASCAP by Emma Lunk at the Australia Telescope National Facility, where some of these satellites at 1.4 gigahertz are appearing in this image as shown here. But what we're concerned about is not from these active transmission satellites such as Starlink or OneWeb that I'm going to be talking about soon, is that they have beaming options where they beam into the side lobes of our telescopes, even if they're not within our field of view. And that creates even more imaging artifacts to our observations. So just a bit of background of how and why we are conducting this study in this way is in the ITU, where the IAU CPS and other organizations such as SKAO are discussing regulations and stuff. We need to quantify the amount of contamination by these satellite constellations through something called equivalent power flux density. So this is collecting all the RFI signals from all the sources that are interfering with us and the equivalent power flux instead of like what is the, and that defines what we need to send into the ITU and tell people, hey, we want Starlink below this level of emissions. So today we're not actually looking at Starlink, we're looking at already operating satellite constellation. So this is OneWeb. This is an internet service provider. They operate at the KU bound downlink for their downlink transmission. So that's between 10.7 and 12.7 gigahertz. They are a relatively small constellation where they have 720 satellites and 18 satellite planes. So they're basically, it looks a little bit daunting from this picture, but it's actually just like every 40 satellites in the line, and you only see 2 of them in the sky at any time, any location in the world. So it's not that bad, but they're operating active service. And so we decided to use this as our case study for developing techniques and how to do RFI mitigation in the future. Just to remind why we're interested in this frequency is because SKA band 5 is going to be between 8.3 gigahertz and 15.4 gigahertz, where we call band 5B. And within this band, there's only one protected band by the radio spectrum management, which is this tiny little 20 megahertz band between 10.68 and 10.7 gigahertz. So it is a massive concern if we're going all the way to 15 gigahertz while OneWeb or Starlink is taking out 2 gigahertz of the bandwidth. So this is how the OneWeb satellites will look at the location. It was supposed to be a GIF, but it's a PDF, so it's not moving. But you'll see that you could see the satellites just going down in those circles. And on the right, because used to be a pulsar FRB person, so I just decided to plot the periods and do some autocorrelation. So they have a period of roughly, I don't know, 2 or 1 hours. You can see them just cycle again. And the interesting thing about OneWeb is they have not just one beam, but they have 16 beams transmitting different frequency bands across plus or minus 27 degrees of their nadir pointing, which is pointing straight down perpendicular towards Earth. So on the right-hand side is what a simulated pattern Federico created from their documentation. And on the left-hand side is just to explain what nadir is pointing at. It's basically pointing down towards straight towards the Earth. So it's like you can point backwards or point forward based along the directional movement they're moving across the Earth. And one issue we were really interested in for our observations is like, in order to calibrate exactly how much equivalent power flux density we're receiving from these active transmitters, we need to consider the transmitter gain as well, not just our own telescope gain, because we can characterize our side lobes pretty well, I guess. But like for these satellite transmission providers, it's kind of their kind of commercial technologies, and it's up to us to check on it and also to discuss with them, and let us know as well how exactly their patterns are and how can we try and coordinate to avoid them in the future. And also in between, after you apply the gains of both sides, there's also transmission loss. So similar to propagation effects, we need to consider the flux loss as well. So to our data collection, we've been using the on-stellar twin telescopes. So these are VGOST telescopes. They are two 13.2 antennas with the baseline of 75 meters, not very long baseline. But what we were using was we have a 3 gigahertz spectrum analyzer backend and 2 gigahertz bandwidth correlator between 10.7 and 12.7 that are currently under commission by the VGOST team there. So Gary kindly arranged observations using these backends for us. The correlator provides 1 second time resolution coherent dynamic spectrum dumps, while the spectrum analyzer provides single dish data at 1 megahertz resolution with 1.8 second timing. Anyway, so we did over 60 hours of data. I'm not going to show all of it. I'm just going to show the first 16 hours on the first day. Oh, my screen disappeared. And for flux calibration, we've been observing Cas-A, which is kind of weird for me at this frequency, but because it's really bright and satellites are even brighter, so it should work fine. And this is how the data looks like in signal to noise terms. And as you can see, these stripy bits going over to time is where the satellite emissions are. They go over 8 separate bands, I believe. So you can see like there's like wideband chunks. But of course, there's something bright in the middle. So I actually have to clean RFI data for RFI, which is kind of weird. But you know, you have to clean what's not needed. And then the final thing as an astronomer we need to do and tell everyone how bad this is we convert it to Janskis. And then you see the horrible log scale plot on the right, which is going to 10 to the 6 Janskis. So that's the first 16 hours of data. And this is basically the average flux band pass I get from all actively tracking satellites. So this is just like if they go into your main beam, how bright are they? And they'll go like between 10.9 to 11 gigahertz, they'll go up to 6 times 10 to the 4 Janskis. So that's very bright. One thing we were particularly interested is because the first channel, band 1, sorry, I'm mixing up band 1 and SK band 5B, but like band 1 for the satellite is 10.7 to 10.95. They told us they had 250 megahertz channels. And what we found interestingly is that we were seeing like there's side lobe shoulder emission that goes all the way to 10.9 gigahertz. So they're kind of outreaching what their original designated channels were. We ran a satellite capture script. So we made snapshots to capture all where each of the satellite was and where the location was, and also the bandpass. And if we collect the separate data from each of the bands, we were able to determine which exact beam of the 16 beams they were emitting from the satellite frame. So you could tell exactly which direction the satellite was trying to point for each channel frequency, as you can see on the right-hand side. So band 2 is between 10 and 20 degrees elevation, while you can see band 3 is exactly 10 degrees elevation. Then we look into like the exact emission statistics, and you can see it's pretty bimodal. So we are assuming this is like times where we're completely main beam to main beam. And there's also situations where it's side lobe to main beam. And we can see that if you get on beam, the flux levels will be around 10 to the 4, while if it's side lobe emission, it's around 10 to the 2 in Jansky's. And then we also did some emission density studies on the azimuth and also the elevation. So you can see that it's highly correlated with what elevation we're pointing at to track the satellites. Although I admit there's some bias because this was easier for us to capture it in that direction and that elevation. But it kind of tells you that we don't really see anything above at exactly a zenith location. And also it is correlated distance, but that's kind of expected. The closer they are, they will be brighter. So if we make a sky map of our whole observations, this is what the sky looks like, the mean flux of every single observation pointing we had in the area that we observed. But that's also, I look into statistics a bit, so I think it's not really, it's a little bit biased because we only pointed once in zenith, and that's if we get a really bright source, then this picture isn't really representative. So how many detections did we actually see satellites in each of the locations? We actually saw more of them around the 50 degrees elevation range. So if you apply a weighted flux measurement, this is the cumulative satellite flux we get from each location on the sky we were pointing at. And that's what I would estimate as the average kind of fluence you would get from that many times of observations. So just to summarize, we tried to quantify the RFI emission between 10.7 and 13 gigahertz. And we had a lot of statistics of RFI occurrence and the signal strength across the sky. These results will contribute to the SK Spectrum Management Group's work for technical regulations at ITU meetings. And also we'll be able to develop satellite flux measurements for our simulation models for observation tools and planning to avoid high RFI zones in the sky. And I would like to point you to the software that we're developing to actively avoid these through simulations, such as this plot on the right-hand side. And you can check out our poster for the IAU CPS session through the QR code. Thank you.
Great, thank you, Harry. You did eat into your question time a bit there, but I'll take one quick question, try and keep it quick.
Thank you, great talk. How did you disentangle between OneWeb and Starlink?
Right, so it's gone. So originally in the satellite capture plot, I also obtained all the OneWeb TLEs. So I had all the OneWeb positions as well. And we were able to see that every detection, the OneWeb satellite was off beam and not within beam. There were occasions where I actually deliberately said, when was the OneWeb satellite in beam? And it's kind of curious, but we never saw any emission when we were directly pointing at OneWeb. So it may be because they weren't beaming in our direction. So that's yet to be discussed. But I know OneWeb has some negotiation with WIGOS telescopes. They're actively avoiding some of them. So that might be the case.
Okay, great. Thank you very much for that. Thanks, Harry. And just a reminder again, there is the Slack if you want to continue the conversation. And next up, Francois, if you come up so long. Yeah, I'm just going to change that. Just trying to give you a 1-minute warning before I tell everybody else. So Kim unfortunately couldn't make her presentation. So we're going to move on to Francois, to our next talk. And we're shifting track a little bit towards molecular lines, not radio recombination lines, because Kim isn't here. So our next speaker is Francois Combs on, well, there you go, new and future discoveries with observing molecular and atomic lines.
Okay, so I will speak about molecular and atomic lines. Yes. So I choose to illustrate the new and recent work and prevailing for the future, 3 topics, but there are many more, but at least they are all related to high resolution and high sensitivity. The first one is for ALMA, that we have discovered a lot of dense gas around the AGN, active nuclei. And this resolution comes to 10% scale. So it was the first time that we can look at these AGN like that. The second is for feedback. In fact, we learn a lot about molecular outflows since a few years. And you know that in this outflow, the molecular component is more massive than other ionized gas. And finally, I will speak about H2O measures that have been also a lot of new results and absorption lines. So the first one will be an example of this molecular tori, NGC 613, which is a barred galaxy. And in the barred galaxy, the bar is driving gas to the center. So you see that at the beginning, at 100 parsec scale, you have the gas, which is driven in inner Lindblad resonance ring that you see in CO322 with band 7 of ALMA. And then when you make a zoom on this, what we see is this nuclear spiral in the center that was not seen before. And when you make a factor 10 zoom here, you see again this spiral that you see here in contours of CO322. And in the center, what you see is a synchrotron emission of the AGN. At the same scale, you find also this HCO plus 423 that we observe in the same simultaneous with the band 7. And the main surprising thing is that they are not aligned. When you see here, the kinematic axis is from east to west. And when you look at HCO plus, which is a 10 parsec scale, and it is north-south. So it means that the two scale, the disks are not aligned to the big galaxy orientation. And this is a random orientation that is seen in very frequent galaxies. You have this case of 1068, which is also a prototype for Cipher-2 galaxies. We see in many wavelengths, we see in optical, here the reflection nebulae with HST. You find the Merlin jet here and the torus. You see the VLBI torus, which is 1 parsec. So we have a very high resolution 1 parsec. And in orange, you see the HCN 322 from ALMA. It's also torus perpendicular to the radio jet that you see the orientation. And in contours, you see the ALMA continuum, which is dust heated by the stars and the AGN. So what we think now is that the paradigm of the thick torus is no longer there, but you have a thin torus, thin molecular torus. And what made the extinction of the broadline region is more the outflow, which is very dense in the basis of the outflow here. And this makes the extension, which is really very high. Another example here is a very nearby galaxy, Circinus, so you can have a high resolution also. Again, you find this spiral, nuclear spiral at 10 parsec scale, which have a very nice velocity field. And it is edge-on, while the galaxy is almost more face-on here. And the interesting thing here is that the CO322 begins to disappear because it's on the dust, and you see still the HO plus, and now we have this tracer, the C1, which is atomic gas, which is even competition for the CO322, and so the atomic gas is here, but tracing the molecular gas, so it's quite interesting. We have also example of outflows, as I told that the molecular gas is the main feedback tracer here. Here we have this remarkable 1377 example, where you see in gray the systemic velocity of the galaxy. You have in blue the blue shift and the red shift. And you see 3 kind of resolution with ALMA in the CO line also. And you see that it is very, very thin, which is surprising because the radio jet is no longer there. In fact, we see with the VLA the core only. So maybe the radio jet has disappeared, but you need some kind of radio jet to trigger this very thin molecular gas. And here you see that it is blue and red at the beginning, but red and blue. So it's inverting. Why? Because it's in the plane of the sky. You need just a little precession to have 10 degrees precession to have the reversal of the velocity. So, and you see here also in the velocity dispersion. I will also show this maser that we know now they are very numerous. For instance, here I just mentioned that there are more than 100 H2O masers. The main maser, the main powerful maser is 22 gigahertz. You have several other lines like 183 or 321, but they are lower intensity. And this strong intensity make it very useful because you can have the VLBI. So I pointed out two new results that here you have a dwarf. So it's the first time it's look at dwarf. So you have an accretion disk. You have the velocity here. And since you have a 0.2 parsec resolution, you can enter the sphere of influence of the black hole and measure the mass of the black hole, which is here in the dwarf galaxy. It's an intermediate mass black hole. And here you have also a record of the distance here. It's 122 megaparsec maser, H2O maser. There is two components here. One is in the core in the accretion disk, and one is in the jet. So you can have also a maser in the jet. So here, I also show the example of 1052, which is quite remarkable also. There is a radio jet here that you see here. The color you have the index map, spectral index map. And here you have the 22 gigahertz maser, also 321, but the stronger is 22. And you have some absorption in the center. And what is the problem here is that you have not the center here, and there is a jet. So we think that the maser is in the jet also. So looking at this interpretation here, there's a lot of absorption line. Absorption line is very easy to have when you have a very strong continuum source behind. And you can have a lot of chemistry. Even you have here vibrational HCN, you have all these sulfur molecules, SO and so on. In sub-millimeter, you have the core is dominating, while in a millimeter, you can have in the jet. So all this is absorption lines. You see the optical depth, so it appears positive, but it is absorption, and you see how it is possible to have a lot of molecules in the chemistry. I will also show some absorption lines in cooling flow clusters. It's very interesting because in the cooling flow, you have sometimes at kiloparsec scale, you have no rotation. You have filaments of gas cooling from the hot atmosphere of the cluster, and it's becoming in CO. We don't know in general in emission if it is inflowing or outflowing. So in absorption, it's very interesting because you can have here, you have the emission, and here the absorption. And you know if it is redshifted that the gas is inflowing. So here I just show a summary, a statistic of what is discovered. Okay, just one or two. Here you see the around zero velocity. You have some blue and redshifted because when you are very close to the continuum source, you can have some rotation in non-circular motion. But then afterwards, you have some only redshift. So we conclude that it is inflowing. So you have indeed a cooling flow inflowing gas. And finally, this last slide, summary slide. This means that you will have a lot of new results in the future with SKA. For instance, you can have H1OH. I've not shown that the absorption was seen in all H1OH and CO and so on. And you can have also redshifted HCO plus and HCN. You can have this maser of H2O 22 gigahertz with SK1 if you go to Z equal 0.4, so it will be possible maybe. You have more sensitivity, you can have exploration of sub-parsec AGN scales. And in absorption line, and you see some example here, you can do a lot. For instance, in this continuum source, very well known, you can have a chemistry at Z equal 1, but with the SKA, you will detect more continuum sources. Thank you.
Great. Thank you very much, Francois. Do we have any questions? Yes.
Yeah, thanks for the nice talk. You mentioned the CO outflow in NGC 1377, and you said it's radio quiet galaxies.
Yes.
Yeah, but is there any other evidence to show it's agent-dominated sources?
We don't know, in fact. In fact, there are several possibilities. I had no time to show that. It could be also like a bipolar flow in a star that it is magnetized, or a radio. It is very, very thin, like a collimation. So that's why I intend to prefer the radio jet. The radio jet is relativistic. It has a very small timescale duty cycle. And the molecular gas, of course, is dragged with only 200, 300 kilometers per second. So it has to survive after the AGN radio jet is no longer there. So maybe it's an explanation. Another explanation could be a magnetized disk and an outflow from this, but I don't explain why it is so thin.
Thank you. Yeah, I also wonder it's still a feedback or aging feedback.
Yeah.
Thank you.
No, there is no starburst, no stellar feedback.
Great. Do we have other questions? I wonder if maybe, unfortunately, because Kim couldn't give her talk, which might have given a slightly wider overview, maybe if you could just very briefly say what biggest problems RFI poses for your studies.
Yes, in fact, it's bigger because we don't know where the galaxy, the lines will be, because we are just looking at any redshift. So that's a problem. We cannot observe only in between the RFI. We want to have all the band, and we don't know which one. And what Kim would have developed, in fact, is radio recombination lines. And for this, radio recombination in H1 and C carbon. And it's very weak lines. So, it's when an atom is very big, and you have Rydberg states, and there are many, many recombination lines. So she's doing the work of stacking all the until 100 of lines. So she has a lot of band to observe, and then the RFI is a big problem because you will lose half of the recombination lines. So I think this, if she was there, she will develop this RRL, recombination lines.
Great. Thank you very much, Francois. Okay, so now we're going to shift focus a little bit towards continuum science, and our next speaker is Kenda Knowles.
Right, once again.
You just need to wait for the slides to come up. So when it comes, Kenda will be speaking on present and expected science in radio continuum astrophysics and limitations of RFI.
Cool, there was a title slide and I'm not moving anything. So, but anyway, this is fine. This is my first, there we go. Thanks very much. So yeah, I'm involved with a couple of other people whose names I've listed here in terms of putting together a chapter on the continuum science for this white paper. And so when I was busy putting together this talk, I was initially going to go very science heavy, and then I looked at the program and I decided against that. So this title might be a little bit false advertising, but we'll see how we do. So obviously we're now in the era of amazing instruments and, amazing science, but we're also needing to look towards the future and to see, what are these big questions that we're going to be going after with things like the SKAO and the NGVLA. And at least in continuum science, I shamelessly went and grabbed a lot of this from the current SKAO pamphlets, but also with discussion with the working group. These are some of the things that we have highlighted. I do want to say I'm hoping this is not an exhaustive list. So if you have your pet science that you feel very strongly about and is not on here, we do welcome more people. Do come chat to us. But so going from astrophysics of nearby well-resolved galaxies to doing cosmology, looking at AGN across redshift space. There's obviously stuff in our local neighborhood with the Milky Way, and that's got a whole bunch of things that look at the interstellar medium. You've got radio stars, supernova remnants, and all of that is studied in continuum. You've got star formation history within clusters, both so basically looking at environment in clusters and in the field, looking at that across cosmic time, the first stars, etc. You can look really far back into the distance past with gravitational lensing. You've got a lot of AGN, and I think a lot of great science is going to be shown next week during, I think it's session 394, but I could have the number wrong. And then obviously there's a lot of science to be done with galaxy clusters, diffuse emission, galaxies within those systems, how filaments interact with these systems. So obviously, we're already doing a lot of this science with the current pathfinders, current precursors. And I know a lot of this conference is focused on the future and the amazing things we can do with the SKAO and the NGVLA. But I did want to highlight, there are telescopes here that are already doing amazing things that we have never been able to do before. And this is going to prepare us very well for this next generation of instruments. But these are obviously very expensive instruments, and SKAO and NGVLA, which are just even larger projects, are even more so. And so we want to do this amazing science. We've built these fantastic tools to do it and are planning on building even more majestic ones. And so if we can't do our science once we get there, that is a massive waste of investment. So I grabbed this slide from something that Josh presented when he was chatting to us about the white paper. And this was the first time that I'd seen the RF spectrum, so the radio frequency spectrum. So this is from obviously quite outdated now. This is January 2016. But essentially what you're seeing here is it goes from, I think, 3 kilohertz at the top all the way down to 300 gigahertz at the bottom. And each little block is a different part or different aspect that has been saved. So for example, it's teeny tiny to read. You'd have to zoom in like mad to see the individual things, but I don't want you to focus on that. But what I'd like you to see is there's tons of different colors. That's lots of many people and projects vying for parts of the radio frequency spectrum. And then I wanted to highlight what these new upcoming experiments are going to cover. So you've got SKA low, SKA mid, and NGVLA. Obviously, this might be expanded, contracted, there might be gaps, but that is the general frequency space that we're going to want to utilize for continuum science. And these are the bits that are currently saved for radio astronomy. And most of these are really, really narrow aspects of the frequency space. And the bit at the bottom by 300 gigahertz was that's not a contiguous bit that's saved, but there's a lot of space there with individual bits for radio astronomy, which is good, but a lot of the science that we're doing is at lower frequencies. So this is obviously presenting a bit of a challenge. This is one of the reasons we're wanting to put this white paper together is, what science are we doing that's going to utilize all this frequency space, and how do we justify trying to save some of these for radio astronomy? So now for continuum, I was interested to hear Francois say that, you're doing with line emission as well, and you still have these problems of going, how do we decide what part of the spectrum is most critical for our science? And when I think of continuum, I'm usually thinking about broadband studies. And obviously we want it all, but we can't have it all. So this is the current question that we come to. And what I'd like to come from this talk is David Spurgill from the Simons Foundation said at the opening ceremony last night that this conference is meant to start conversations. And I think this is the main point of this talk, is I'd like to start these conversations for anyone who works in continuum or does a lot of RFI, so that we can start trying to see, how can we work together? And certainly from the continuum science side, how do we work with maybe the other aspects of science like H1, which is fairly specific? Maybe we need to work together there. So going back to the science, I just wanted to use some example of the science to kind of drill this point home. And this is why we work in teams. I'm not an authority on most of what's on this slide, but I do work in the field of galaxy clusters. So that is what I'm going to use in this case. So for those of you who don't know what a galaxy cluster is, so these are massive groups of galaxies. They're the largest gravitationally bound systems that we know of in the universe. And they fill this really cool place between cosmology, so what the universe is doing as a whole, and astrophysics, which I tend to see as the nitty-gritty small scale stuff, but where small scale is still, megaparsecs. And obviously in astronomy, and this is what you're hopefully seeing at the IAU, is that when you're wanting to look at a system, you need to go across the entire waveband to get a full picture. So optical and infrared to look at the individual galaxies. You can do lensing studies, usually with optical infrared, to find out where the dark matter is, how it's distributed, how much it is. You can use X-ray to start looking at the thermal emitting, so the hot gas. And when you add the radio picture, this is a very unique way to probe magnetic fields and cosmic rays. So my main focus in my research is what we call diffuse cluster radio emission. That was the big fuzzy green blob that you saw in the previous image. So this is basically faint radio emission that is large scale. So we say when we call large, we're talking about sort of 100 kiloparsecs or more. It's all very steep spectrum. So it's power law spectral with so it's brighter at lower frequency than at high. And typically well, so far we've thought they've been rare, but that might have been a telescope sensitivity problem. There's different characterizations. I won't go into details, but they are distributed in terms of where they are in the cluster, their polarization properties, how big they are, what type of cluster that they're found in. Is it dynamically disturbed? Is it relaxed? And also if there's any connection with AGN. So for the radio halos and relics and the mini halos, there isn't a strong galaxy connection, but that might not be the case for one of the other types, which are the Greets or the Phoenixes. So the key thing with this emission is that it's synchrotron. So you're looking at very fast electrons spiraling along magnetic field lines within the cluster environment. And so this the top plot in the top right is basically showing what you expect from a synchrotron power law spectrum, where you have a whole bunch of individual electrons with different energies, and they sort of all co-add to have this nice sort of straight line in log-log space in frequency versus intensity. So I'll get back to that later. So now, obviously, a lot of what we know about these things are observed or gained from both individual studies of, you know, sort of the poster children, things that are well resolved on the sky. They're very bright. They're easy to study in detail. And then statistical studies, which is what I mostly work in, because most of the population of galaxy clusters are not nearby. And so you need to look at statistical properties to understand things like how are the different sources generated, how do they evolve over cosmic time or evolve with the properties of the host cluster. So the key thing I wanted to highlight here is that certainly for the poster children, and these are the ones that I'll focus on from now on, a lot of what we know about these objects and the way we can constrain a lot of our formation models is through multi-frequency observations. So this is one of the first sort of major poster children that was studied. It was also in my sort of science gallery. This is called the toothbrush relic. And so this is basically emission that you have at a shock. So you've got the plasma being compressed, and you've got this large-scale diffuse emission that is steeper spectrum away from the shock edge than at the shock front. And this particular object has, you know, there's over 10 papers just on this individual object that's studying everything from basic observational properties to using those observational properties to constrain a variety of formation mechanisms. So there's this really nice study. There we go. Raj Purut in 2020 showed some great results, I think with the, I can't remember which telescope, but it was definitely the VLA and something else. But basically this is showing why multi-frequency observations are useful for continuum and the different types of information it gives us. So for example, if you're just looking at the same frequency, then you can look at a variety of resolutions, and that gives you a different idea of the level of detail or the level of minor structure that you've got in the objects. But if you're looking at different frequencies, so here I'm just showing similar resolution for comparison, but you can also see evolutionary properties across frequency, and that is telling you something about the electron population. And if you know something about that, you can say something about what was generating the emission in the first place. How were those electrons sped up to relativistic speeds? So this is another example. This is now a radio halo in the Coma cluster. It's very nearby. It's lovely and bright. It's one of sort of the poster children for radio halos. And so this is work from 2022, where, so the cool thing about the Coma and why it's such a poster child has become that is because it is the most well studied across the frequency space. So on the left here, you're seeing the radio flux density across versus frequency, and you're covering more than 2 orders of magnitude in the frequency space. That is very rare. You can imagine the amount of telescope time that's gone into a plot like that. But what you can start doing with plots like that is start separating out your different formation models. So there's the solid line and the dotted line on that plot. Both of them represent 2 different formation models for radio halos, secondary mechanisms versus primary mechanisms. And so if you didn't have that entire frequency space of information, you wouldn't be able to distinguish between those two plots, but, well, obviously depending which bits you get. And then the plot on the right-hand side is then looking at the spectral index. So again, in order to get a spectral index, that's looking at the slope of that spectral line. You need at least 2 frequencies. Obviously, you're getting more constrained information if you have higher frequency or more diverse frequency information. But what you're seeing on that plot is the spectral index, how it's changing spatially from the central part of the halo to the exterior in different parts of that. And obviously your spectral index, that's why I wanted to mention that spectral index plot before. So if you consider this is a nominal power law spectrum that's been generated, your higher energy electrons are going to lose energy faster. So what that means is, you have some generating mechanism, it's producing synchrotron emission, and then that emission is propagating through space. As it's moving, it's losing energy, but the higher energy particles are losing energy quicker. So you end up getting a steepening of the spectrum. And so where that what is that steepening of the spectrum? Where is it occurring in frequency space? A lot of that can tell you something about the mechanism again. What is the physics behind it? What was generating it? And so the question then becomes, which part of that spectrum is important to know? You need to know the ends, you maybe need to know where the knee is. You don't know where the knee is. So if we now look at different parts of this plot, let's assume you only had, half of the point of the information, the radio frequency information. 2 minutes to go. Thanks. Then it becomes, well, which ones are most important? And that's the question we're currently struggling with. So if anyone's got ideas, please do come chat to us. Are there specific combinations that are going to be helpful? And then this is obviously a very narrow science sort of theme. As I mentioned before, this is much broader. And I wanted to just show some real data from MeerKAT. This is one source that's been observed at UHF, L-band and S-band, all within, I think, maybe 2 weeks of each other. So if in terms of time scale in the year, it's fairly similar. And so as has been mentioned by other people, you can see the L-band is quite contaminated by RFI. Things get much clearer at the UHF. And even in the S-band, there's some really nice clean chunks. But the question is, for your continuum science, which part of these bands is more important? Maybe for diffuse emission, you want to look at the lower frequency stuff. But if you don't know what's happening at high frequency, you don't know if that spectrum is bent over. So just in summary, I think, obviously, we've got these amazing instruments currently, and certainly the ones coming up. We want to do really groundbreaking science that's pushing the edge and really making the most out of these instruments that we've built. But I mean, this focus meeting is really focused, excuse the word, but on the, what is the RFI environment that we're going to have to deal with? And if there are people like Josh and other communities that are willing to try fight for some of the spectrum for us, then I think it's, from the scientist side, we really need to work hard on trying to support them in terms of saying, what do we need to, what is most critical for us? And certainly for Continuum, I don't know yet. So writing this chapter is going to be interesting. But if you'd like to get involved, we're obviously very open to having more people come on board. So please get in touch. My contact details are over there, and I'm happy to take any questions.
Great, thank you, Kinder. Do we have any questions? Yes.
Thank you for the nice talk. In fact, I was curious to know from polarization and the magnetic field, can you retrieve the shocks in the relics, or are there the orientation of magnetic field?
So at the shock edge, you would expect to see an ordering of the magnetic field. So there's been some really great studies on well-resolved relics, which have shown exactly that. So the toothbrush relic is one of them. There's also Abel 3667 with MeerKAT observations. So yes, you do see an ordering and a compression of the magnetic field at the shock front, and it starts becoming more disordered away from that
In
edge.
the bullet, there was not a very nice relic, or your green thing.
So the relic in the bullet is a bit odd in terms of it's incredibly linear. And when you look at it in more detail, once we have much deeper data, I think there might be some AGN component there, that maybe there's some relic plasma that has created, that's the population of electrons that got re-energized to create the relic. But I mean, the toothbrush is also very linear. So there are cases where we see incredibly linear shocks, rather linear relics. But then we also see other examples where for example, the sausage relic, it's beautifully arc-shaped and it follows the shock front beautifully. So why some do that and some others don't is obviously one of the questions we try to understand.
Thank you.
Thank you very much for your presentation. I just have a small question regarding these important bands. Have you considered to try to do it the other way around? Because I think you've shown us what frequencies are already identified, like as radio astronomy frequencies in spectrum. And I think initially when they were identified a very long time ago, maybe there were some similar discussions. So is it possible to maybe consider starting from those bands to see if they are enough or you need something extra.
Okay.
Maybe, you know, like, because if you'll just arrive with a different set of radio frequency bands, it might be really hard to get people out of
Classify
there.
it.
So
Yep.
maybe.
Oh, that's a
that-
really good idea. Thanks. Yeah. So I guess what you're saying is to start from what's currently, and Josh might be able to comment on that, I see, but to basically go from, look, this is already reserved for you. And I guess I don't know if things are reserved for perpetuity or for a certain lifetime, but then to go from that and say, if we only had that, how would that impact our science? That's a good idea. Thanks. I think Josh wanted to comment on that.
Yeah, just a very brief comment after I switched off this. This is exactly what we're going to do as a next step in this process. So first, we now have asked ourselves, so can we do this from scratch? And since we do have the list already, this was actually what I wanted to forward to for the white book, especially to the authors of the chapters to have this discussion, and I will bring it up tomorrow.
Yeah. I mean, I suppose they are very complementary because you have to know what science you want to do in order to know how it's going to get affected, but to reverse it like that. Thanks.
Great. Well, thank you very much, Kendon. Next speaker is Fengxia An on radio spectral properties of star-forming galaxies. We just need to wait for them to bring up the slides. Great, thanks, Fengxia.
Yeah. Good afternoon, everyone. I'm Fangxia. I'm based at Purple Mountain Observatory in China. Yeah, it's my honor to introduce to our recently completed project on study radio spectral properties of star-forming galaxies. My collaboration is one of the MeerKAT's larger survey project mining team and the LOFA, LTS, and the GMRT team is especially the for the people correct data in the ELAS N1 field. All right. Yeah, Kinda already gave a very good introduction about the radio continuum, but here I just wanted to highlight that for the radio continuum spectra, that means we study the radio emission at different frequencies. And the radio continuum, as you know, consists of some synchrotron emission and some free emission. For the sorry, yeah, back. Yeah, for the sorry, yeah, I just wanted to point. Okay, yeah, for the free emission, it's it's originated by the accelerated electrons in the H2 regions, so it's traced a star formation rate within 10 milliyears. And for the synchrotron emission, as Kinda introduced in his session, it's the relativistic electrons that accelerated in the by supernova elements or the radio jets. So it's traced both the black hole accretion and the star formation in galaxies, although it's a delayed trace of the star formation since it traces the end stage of the massive stars. So this origination, means that we can use the radio continuum a powerful observation tool in exploring cosmic evolutions. That is why the current powerful radio telescopes that they all carry out the high sensitivity and the wide field extragalactic radio continuum service. Hey, I just showed two examples: the MITIN and L2SS that will be used in my work. But as I mentioned before, the radio continuum consists with some synchrotron and some free emissions that choose the different underground physics. For the star-forming galaxies, the synchrotron emission will dominate the radio emission below the anti-low frequency below 13 gigahertz, and it could be well described by a steep power low spectrum with spectral index around -0.8. And the free emission becomes increasingly important at high frequencies. That means high frequency, higher than 13 gigahertz, and it has a flatter spectrum with spectral index around -0.1. Traditionally, when we use the radio continuum as a star formation indicator based most on the receiver from 1.4 gigahertz luminosities. The reason for this, as have mentioned by several talks in this session, that it's the receiver frequency of the H1, so it's the protected windows for the radio observation. And to this frequency range, the radio emission is dominated by synchrotron emission, so it's delayed star formation rate indicator. So you're typically for the calibration, by use five-phase radio correlation will be carried out. But when we study the star forming galaxy and high redshift, the receiver 1.4 gigahertz emission will be shifted to low frequencies. So to answer can that question, which frequency will lead? Low frequency, so we need the low frequency data to determine the radio spectra, and then to do approve the calculation before we use the radio continuum to trace the star formation rate in galaxies. That is the exact purpose of our work. So firstly, we use the Meerkat data from one of Meerkat large scale project, mapping the early stars data in the cosmos field, and we combine the publicly available way and the GMRT data in the cosmos field to study the radio spectral properties of star-forming galaxy and to reach 3.3 to 10 gigahertz. We first combine the two, high sensitivity data in the field, the Meerkat 1.3 gigahertz and WAIR 3 gigahertz data, and obtain the 2-point spectral index, and we obtain the mid spectral index around -0.8, which confirmed that the radio spectrum and this frequency range is still dominated by synchrotron emission. And we found that the mid spectral index is not strongly correlated with the receiver frequencies. But we do find that the radio spectrum will slightly steep with increased stellar mass, and this could be seen in different redshift and different star formation rate beams. We also found that the radio spectrum is slightly flat, so with specific star formation rate. And when we go to the low frequency region, because the GMRT data is quite shallow, so we only made an individual measurement for 200 star-forming galaxies and do the stacking for the remaining one, and we do find that at low frequencies, the radio spectrum is also steep with increased stellar mass. And when we compare the high and low frequency radio spectrum, we found that about 24% of the radio spectrum SFG that has radio spectrum significantly flat and low frequencies. And if we use the high frequencies in calculation, that traditionally in the literature, because the limit we mentioned have been mentioned in several talks, and low frequencies, we found that if you use the spectral index and high frequency in calculation, that you will significantly underestimate the five-phase radio correlation parameters for this 24% SFGs that have a flat radio spectrum and low frequencies. This will further influence the studies of the evolution of five-phase correlation parameters with cosmic time. But the main limit of our work is the low frequency data is quite shallow, so we have to rely on the stacking results. So our second project is uses the LOFA 115 megahertz data, and our GMRT data in the N1 field. I just go this quickly. We get a mid-spectral index until 115 to 600 megahertz is minus 0.5. So you see it's flatter than what we get in the high frequencies. And we do find that the radio spectrum is slightly flatter at low frequencies. And also the middle panel shows that the radio spectrum slightly flat with increased octave depths. And we also found that the radio spectrum slightly steep with increased stellar mass. But when we include high frequency 1.2 gigahertz data, we can't find that the correlations with optic depths. And yeah, on average, the radio spectrum we found that the radio spectrum of star-forming galaxies flat and low frequencies and high frequencies. I have no time to go detail of this, but yeah, we discussed that the physical mechanisms that drive these correlations, like for the radio spectrum, steeps with increased stellar mass, as Kinda already introduced that we say that age-related function nodes could explain this, and for the radio spectrum flat, so with increased octave depths, it might caused by the free absorption, and both of these two mechanisms could cause that the radio spectrum of ST is flat and low frequencies and high frequencies. All right. So one take-home message is, before we use the radio continuum to exploit the cosmic evolution, or well determine the radio spectrum is important. That's all. Thank you.
Thanks, Xia. Do we have any questions? No? Okay. I think we'll move on then. Thank you again, Xia. Okay, our final speaker for this session is Keegan Trehaven. Sorry if I pronounced that incorrectly. Go ahead, Keegan. So Keegan's going to be talking about meerkat view of the Shapley supercluster. I see you have a meerkat in your hand.
Yes, so for those who haven't met Timon, this is Timon. He's my mascot because I usually work with meerkat data. So there we go. Okay, is the volume okay? Is this okay? Okay, cool. So
just give it a second for your slides to come up and then.
Yeah.
Okay, great, thank you.
Okay, how do you? Okay, and then back. Okay, right. So my name is Keegan Trehaven. I'm a PhD student at Rhodes University, and I'm very thankful to be here at this prestigious event. My talk is titled. My talk is regards to the Shapley supercluster, basically meaning that I have the best project in the world, and I'll tell you why now. So we've heard some fantastic introductions to diffuse radio emission in galaxy clusters and synchrotron emission in general. So this is just a recap of the previous two speakers. The main point is that with diffuse radio emission in galaxy clusters, we're probing large-scale structures. And in my particular project, we're probing the largest scale structures that can be probed in this type of science, is intercluster radio bridges. There's certain classes of diffuse sources in galaxy clusters. These intercluster bridges are actually now in between two gravitationally interacting clusters. So it's the intercluster medium, not the intracluster medium. So this is a broad view of the Shapley supercluster. We have, it's a large area on the sky, about 4 by 4 degrees with the main core. There's a density peak at 3558, and there's a 3562, and then there's two smaller galaxy groups in the middle. So this is optical density, and then overlaid on the radio on the radio ASCAP image. This is just to show that we have very bright sources in the radio, but we also have very faint sources in the radio. And what we're interested in is this this red rectangle here, which has an intercluster radio bridge, which is very, very faint, and which is why we require the best radio telescope in the world, Meerkat, to observe such faint structures. And that is exactly why this source is ideal for emphasizing the fact that without robust characterization of the RFI environment around our astronomical observations, we won't be able to reach the noise sensitivities that we need in order to break through this the veil of going from the intra-cluster medium to the inter-cluster medium. So because the supercluster is so large on the sky, we need to image at a uniform sensitivity, but over a large field of view. And that can only happen with current technology if we mosaic on the sky. So we've developed a visibility plane mosaicing technique for MeerKAT, where you use a imaging software called DD-Facet to mosaic several pointings on the sky, and that takes care of the primary beam in a more robust manner. So this is the current, wrong button. So this is the current Shapley bridge between 3562 and one of the SC groups. This fluffy bit here is the intercluster bridge, but you can also see that sort of at a similar significance, there's also this fluffy erroneous stuff on the top right. So now that's with upgraded calibration, we now have a more robust detection of the bridge. And now with the visibility plane mosaicing, all that fluffy emission has been calibrated out because we are now able to deconvolve the fainter sources, differentiate them from all the erroneous stuff, and calibrate it out. So I'm talking about the bridge. What is it physically representing? It's physically representing a flyby interaction of this SC group flying to the right and above this A3562 cluster and probing the turbulence that is resulting from this flyby interaction. This has been postulated for some time now. It's just we need the observational evidence to prove it. And we're getting there with new UHF data, so we can make accurate spectral index maps that will map the injection of the energy into the intracluster medium or the intercluster medium. So that's the bridge. The other main source that we are interested in is this 3558 halo. It's interesting because it has it's the biggest mass density, but the halo is very weak. So there's a common correlation with giant halos saying that the radio power should correlate with the mass of the cluster. For this one, we're sort of suggesting that it's a mini halo because it's not following that correlation. And mini halos are a known class, but this mini halo is showing a trend in a plane that is distinctly superlinear, distinctly positive, distinctly greater than 1 for this type of object, but we're seeing less than 1 for this type of object. And that's a direct indication of the production mechanisms. So from the literature and from simulations, we can see that, thank you, we can see that a correlation in this intensity to intensity X-ray to radio plane, that less than 1 indicates turbulent reacceleration, and greater than 1, there's really no discriminatory power. So this is really something that we're finding just because it was observed for the first time with MeerKAT data. So for the spectral index distribution, we're seeing that it's correlated very nicely to an X-ray cold front. And so for the first time, we're seeing a real connection between the thermal and non-thermal emissions that is directly injecting energy into the thermal and non-thermal components of the ICM. Then I have this little thing just to end off. just to show the dangers of large-scale interference patterns when we're trying to observe structures of the scale. So we have 3558 halo here and the bridge here. This is 1GC data, so after transfer calibration. And you see this big large scale plus structure, which we thought was real, but after further investigation and a little disappointment, we found that after rigorous flagging, it can be flagged out. And as a young scientist looking to perform transformational science, it's just a warning to show that even if you find something potentially interesting, you have to go through each step of the scientific method to actually reliably decide whether you're producing real science or not. It ain't science unless it's reproducible, right? So, and then the last one is just something similar, but on the dangers of over-flagging. Because we're looking at such large-scale structures, you could flag out the scales that, the scales that your science has actually found in. Okay, thank you very much.
Great, thanks Keegan and Timon for the important lesson and nice images. Do we have any questions? I'm not sure whose hand was first, but you haven't asked a question yet, so we'll go this way first.
Thanks, nice talk. Do you find any flux scale offset between your image plane mosaicing and visibility mosaicing?
No, we did rigorous testing, at least against point sources, to see that the flux scale of the point sources was conserved throughout the calibration at every step. So from your first image, it's consistent all the way up to the final mosaic, whether it be image plane or visibility plane.
Okay, we'll come to you.
Thank you. That was a great talk. Thank you. And one of the most important lessons that you've illustrated here, that scientists need to understand their data. Can you elaborate a little bit more on what you mean exactly by rigorous flagging?
So we flag through MAD through MAD strategies, meaning median absolute deviation, and that there was a poster by John Kenyon on Quarticle, an in-house calibration software at Rhodes, and depending on the certain threshold values you use, certain baselines are flagged out and certain baselines are kept in. Rigorous just means, for my purposes here, whether you turn on that flagging or not, and the level of the threshold. So in calibration, at least thresholding can be a bit of a dicey thing because you never know if whether you're probing some artifact that is above the noise or something real that is below the noise.
Great, thank you. You want to comment?
It's just a question that came just up now. How do you know that this is not really real or has a real component?
Well, that's sort of the question I pose to the audience, because there's an X-ray component that is aligned horizontally, but there's also a vertical axis to that large plus structure. And there's no real physical mechanism we can think of that could explain both the horizontal and vertical orientation.
Yeah, no, it's just my own experience. So when I was doing these things in the past, and I suddenly had a beautiful image.
Yeah.
In the continuum, beautiful continuum image, it looked really completely clean. While I'm an H1 astronomer, so I have the advantage that I can use these data to actually check the calibration.
Yes.
And what I did before, when I get a reasonable result in the H1, then the calibration is probably also more or less reasonable, at least. And this was a disaster. I didn't see anything anymore, which made me to re-reduce the data, and suddenly I saw the H1. Before one decides whether something is RFI or not, it's sometimes not as clear as one thinks. Even if the image looks nicer, doesn't have the shadows and so on at large scales, it might still be more real than the very clean image. But I mean, I'm not saying that this is the case here, but it could be. That's my only remark here.
I totally understand, and that's why it's just a warning that it could definitely be real, but then if that's the dangers of I suppose human arrogance. You want to be the first one to discover something, but if it's not, you get to shredded in the media or something like that.
Great, getting very philosophical there. Thank you very much, Keegan.
Thank you very much.
And just to say thank you again to all our speakers so far today. We have coffee now. There is a poster session going on, so do check out the posters that are relevant to this session. We come back here at 3:30 for the next sessions. Thank you.
Yeah. I was a little confused. But no, hang on, this is very specific. Anyway, I gotta go do my poster session.
Thank you. Oh.
I didn't know that the criminal was not there.
I don't know what happened.
What happened?
Very
Last minute? Last minute?
Thanks a lot.
It's not bad. Yesterday she was okay.
Because I was really afraid that you're going to steal this whole IT. I was afraid that you're going to steer the wasp nest of IT. You know, if you arrive with a new set of bands and you tell them, oh, we need a completely new set of radio astronomy bands.
Oh, but I started with this. What are the most important things?
Yeah, I understand.
And I think now it's the time
to go from a different direction. Yeah.
I wanted to bring it up.
Yeah, because I'm not sure if you are into Vigos or not.
Just a little bit.
Yeah, so Vincenzo has been chasing me for some time. So apparently they were thinking about, because they look for frequency range from 2 to 14 gigahertz. And she told me that they're looking for four bands, 1 gigahertz wide. So yeah, I've been trying to explain here that, well,
That's I mean, we are pretty much involved in, but we have
oh, okay, so you're involved in that one. So maybe if you could also speak with Vincenzo, so it will not be only me.
Higher hardware. I mean, he's very much involved in higher hardware.
As well. Because I was surprised when I saw that email. I tried, but I tried, of course, to give all the information I could.
I mean,
and of course, when I mentioned that to our friend Vadim from ITU, he was just like, "Oh well, I will need to buy a popcorn for the next conference. They come with it."
Yeah, but well, best against that. There is something for some conference.
Yeah, I just want them to.
There's one part of compromise.
Even I would say something similar to what we have for space weather. In that resolution, because I secondly half an hour ago. Maybe it's like all decisions will be made. Cannot lead to or like can only make some patients. I mean, 1 gigahertz, if you take 4 gigahertz to 14, it's about 1/3. So yeah, even IT cannot get that. Well, you know that IT
I miss La Palma because I think we had some IAU meeting that was really close and we just. See how it goes. Here. I'm not sure because maybe we can also a little bit more about it. Oh, there's more here. Oh, I'm not going to go because I'm not a member. You're a proper. I don't have IAU member. Just here, United Kingdom. We need much more stuff, especially the directors. Also, the same idea. People want to be like you guys here who watch it up. You guys. Oh, hi, Harry. How are you? Yes, so he will replace my. Maybe around. Yeah, he's much more so he saves and be aside from all this. So I think CPT is more like science. It's like what
separation got inside our team.
Yeah, but it's good to have different.
True. And the related question is that we were looking for a person with experience with astronomy because we already have people with experience. Cooperation counts. Because other points I just so I hope I get I was just mentioning that I hope I feel getting something about astronomy and radio. The only concept that took all my attention with is quasi stars. Have you heard about them? It's like a really giant star, which is fueled not by nuclear fusion inside its core, but there is actually a black hole inside its core. So it looks like the matter is falling on black hole. Of course, it heats up. So it's technically again the source of heat. It's just a different source, not fusion. And the star has to be really massive, like 1,000 mass of ton. So we don't expect them to be orbiting nowadays. But I think somewhere I read it's like a candidate how all these supermassive black holes form. Yes. Yes, yes. So, and for me, it was just really interesting concept of a star, but it's black hole that is slowly eating the star from inside. And, for me, it was like terrifying, yet very interesting. Yeah.
You're not my dogs, they're dogs.
Thing over here. Attention, so back to. This is it, Kaushal J. Tony Beasley. Yes, but what is on this one? No, that's looking at the wrong one, yes. I scared myself. Pretty deal, so to be able to share the you know, Jane? Touch, right?
It's probably don't know.
Okay, welcome back, everybody. Just get the IT started with the screen up. So welcome back to our last session today. We're starting up. Sorry, I just have the find the right thing in front of me. Starting up talking about hardware excision techniques for RFI. And our first speaker is Kaushal Buch. With a UGMRT, sorry, I can't speak, UGMRT case study. So Kaushal, just a reminder, we have the audible alarm at 2 minutes and then I'll get up.
Thanks. So good afternoon all, and thanks to the FM5 organizers for inviting me to give this talk. Okay, so this talk will be divided into two parts. The first one would cover the general techniques in digital signal processing for RFI mitigation. And later I'll cover the UGMRT case study where we have implemented and released the system for observation. So as we know from this, that there are RFI mitigation is hierarchical and we have various methods. So I'll be in particular talking about the digital systems where due to the advent of high performance computing and systems like FPGAs, we are now able to build systems and make them work in real time. Which one goes? Okay, so what I want to show is that the signal model, the interference is additive. So if we broadly see the signal, it has the astronomical source, which is Gaussian distributed. Then we have the system noise, which consists of the receiver noise and the background, sky background, which is also Gaussian distributed. And but it's stronger than the source. And then we have RFI, which comes from man-made or natural sources, which is usually stronger than the system and source noise, and it is non-Gaussian and non-random. So basically, these are the differentiating points where we can detect RFI from signal. And the key thing why we would like to do mitigation well in advance is that the system fluctuations don't reduce upon integration because the signal is now non-random because of the RFI. So it reduces the theoretical sensitivity. So if you see an overview of the techniques that have been proposed so far, we find these three categories of techniques. One is excision, where we essentially, so this is a spectrum, and using a statistical estimator, we find interference and flag it, as you can see here. Sometimes this is efficient, sometimes it doesn't work very well, but this is a simpler way of implementation, doesn't need much hardware, but there is more data loss because you directly remove the signal. Then there is slightly more complicated technique where you have a reference antenna which points at the interfering source and the telescope which gets a combination of source and interference. So this essentially what it does is it does noise plus RFI minus RFI subtraction cancellation over here. And this would work well if the antenna is only looking at the source and so on. So there are limitations to this, but this is also one of the proposed techniques. And the loss here is lesser because it just subtracts. And then in case of array feeds where you have the facility to form the beam point nulls in different directions, you can form a null towards the interferer and get rid of the interference. So excision has been widely used. I'll be talking more about that today. So if you summarize this, if we have very strong continuous narrowband RFI, then the only solution is to have analog filters so that the system doesn't get into saturation. And that is mostly done in the front-end system. If you have intermittent narrowband RFI from, say, terrestrial transmitters, then we can do it in backend, either post-correlation or pre-correlation, depending on the kind of RFI. And here, the statistical RFI mitigation or excision techniques are very useful. Similarly, for the broadband RFI, which comes mostly from power line and sparking, the techniques used in backend are very efficient because they mitigate the interference in time domain, where it is more impulsive and easily detectable. And for specially confined interference, like for satellites and so on, one can have digital backend system as well as analog, depending on how strong the source is. and one can do adaptive cancellation, spatial filtering, nulling. These are more easier to do in these kind of things. And more will be covered in the chapter which is coming up as part of this focus meeting. So you can keep track of this chapter where we will actually give a good overview of all the techniques. So in case of excision, as I was telling, this is the most commonly used technique. The technique would work when the receiver is in linear region. So you have to make sure this happens either by putting enough filters in the analog system. And the RFI is not persistent because all of this works on statistics of data. So if the RFI is persistent, one may not be able to get the real statistics of the signal. And so the earlier you do, so this is the typical signal processing chain. So the earlier you do, the lower is the data loss because you will be flagging only those instances at maybe at the Nyquist rate. So the more you go here towards the end, you will be flagging more. But at the same time, if the SNR is not significant here, you might have to go here. So it all depends on what's the SNR and where you want to put the trade-off between SNR as well as the data loss. And advantages are because you do everything early in the chain, you get the benefits of reduced data loss, reduced artifacts, and improved sensitivity. So the most common things which people use in various telescopes is either, as I said, there could be two approaches. Either you detect outliers if the RFI is strong enough, or you do a non-Gaussianity check by kurtosses or such indicators. And then or you do this threshold-based detection wherein you get threshold using some robust estimator, and you do estimation, establish a threshold, and then detect it, and then flag it or filter it. If it's early in the chain, you can't keep a void there, so you might want to replace it with a noise sample or something. And if the RFI is weak, you might want to integrate it. So you might want to square and add a few samples to build up the SNR and then improve it. So this figure here was an early simulation that we did where we added impulsive noise. And we did, so this, what it shows is that the flagging is more if you used a normal statistical estimator like standard deviation because it gets biased. Whereas the median based estimators are good, say up to 40 to 50%, and then get biased. So if I come to the upgraded GMRT, I think already speakers before me have explained, but I'll just say something. It is divided into 4 bands, band 2, band 3, band 4, and band 5 with the frequencies mentioned here. And it is near seamless coverage from 130 to 1450 megahertz with a maximum bandwidth of 400 megahertz. So while we get an improved sensitivity due to all of this, we are also affected by interference, which is generally 30 to 40 dB stronger than the signal. And we primarily divide it into broadband and narrowband. And certainly because it limits the dynamic range and detection of weak sources and affects imaging. So we have to find some solution to have this. So this is the kind of GMRT array for those who are not aware of it. So we have a central cluster here of 14 antennas, and then the rest distributed in a Y-shaped pattern in the arms. Okay, so very briefly, I think the next, the talk by Divya would cover all this in detail, but the typical RFI environment at GMRT, this is one time versus frequency spectrogram at band 3 of GMRT. And so you can see that there are communication transmitters, broadcast services, and satellites, which are the main reasons at different bands. But you can see this power line, which is common up to say 800, 900 megahertz. And this exhibits as broadband interference. You can see this is the frequency axis. So this is the broadband interference, and this comes from sparking on power lines. So this repeats every 10 milliseconds on this scale because it sparks twice in the AC cycle of 50 hertz. You can see this as coming. So this is the most important source because this is broadband. We can't use any frequency selective filtering, analog filtering in the front end to counter this. So this has to be handled in the signal processing chain. All right, so a little bit about the power line RFI. So as I said, it occurs due to sparking on power lines. And this happens right away from band 2 to band 4. And you can see these are all, this is a digitized time series, time versus amplitude. And you can see these impulsive events coming from the sparking on power lines. And these are also outliers in the Gaussian distribution of the signal which we receive. Yeah, so why this is important is that, so this is the GMRT array as I showed in the previous slide. Here we can see these are the number of transformer installations in and around the GMRT array, which are all potential sources of interference. And some of them in the southern arm, which I have shown, there are all across, but I have just shown those in the central square and the southern arm. So it's very important for us to have a solution to counter this problem. So the way we developed this system was first to identify the problem, find the right algorithm to do it, simulate it, implement it on the signal processing platform, optimize it. Then there was a whole stage of testing where we did module level testing, engineering tests. We developed a system where we can inject controlled amount of RFI and test it, so control testing. Then we went to the users. Then we did simultaneous testing of unfiltered and filtered signals so that we can sample it exactly while the filter is on and when the filter is off. And then we did astronomical tests on image and on continuum and pulsars and so on. And then there was a phase of release where we built some, we did more fine tuning of the settings of the system, what would be optimal, what won't be optimal, how to do bookkeeping, how to add more features to it. And you can see this is a double arrow. So at every point there was a feedback which went, and we corrected this and then finally released the system. So this is one example plot of very early system where we plotted the unfiltered versus filtered data. And you can see this is at 150 megahertz GMRT time series. And you can see this blue one is unfiltered and the red one is filtered. This was very, very initial result till the image part where we showed the filtering effect on the image. So why this is very important for us? Because if you see, this is a time series plot taken on a high time resolution oscilloscope. And you can see this impulsive bunches coming from power line interference. And you can see this on a very short spacing baseline of 100 meters. You could see this easily with a visually we can see this correlation here in both the polarizations. So this certainly affects the central square cluster, which is closely spaced antennas. So this kind of RFI is correlated in shorter spacings, and it affects diffuse emission from extended sources. So we need mitigation before we correlate. Yeah, so this is the thing we finally came up with. So we used a robust estimator, a median-based estimator to do this, and then we established the right value of threshold, and then the detection on each sample, on each voltage sample, and then we replace the data with noise which is generated with the same statistics as that of the incoming signal or a constant value. This is user programmable, and we also generate flags. So in this, you can see this is the controlled testing where we have injected impulsive RFI in red, and then it's all picked up in the green one after filtering. So the most challenging part here was to develop this recursive median filtering in real time on FPGA. So this is where we have the RFI filtering block just after the ADC on raw voltage. It operates in time domain on every antenna signal and polarization. And we do this at maximum of 800 megahertz. That is each sample coming in at 1.25 nanoseconds. So the main challenge came in testing because we wanted to test the filtered and unfiltered data together. So we came up with what we call the digital copy mode or the simultaneous testing where we have the 15 GMRT antennas with filter and 15 without filter. And we pass it through a correlator and we see the output here. So this is one power versus time. Since the RFI is broadband, we can use any single frequency channel to see this. And you can see the unfiltered in red and the filtered in blue. Similarly, this if you take the Fourier transform of this, it should show periodicity in this series. And you can see the 50 hertz periodicity coming in, the harmonics of 50 hertz, which are removed. You can see the blue one where the thing is removed. So now moving to cross correlation, as I said, this RFI is correlated on shorter baselines. So one can see here that these The error bar, the measurement on the cross correlation function, the uncertainty is more due to this interference. And you can see that is reduced by filtering. And the error bar is same as a long baseline, so where there is no RFI. So you can see that this has picked up the RFI properly, and it has brought it back to the mean and the variance in the cross correlation function. Similarly, the closure phase for 3 antennas, which should ideally be 0, which changes because of RFI, and is brought back again by filtering in the green color. And you can see that there is an improvement. So then we went for testing in this, again, simultaneous testing mode where we have 15 antennas filtered and unfiltered. This is a extragalactic field at band 4, imaged using less than 0.5 kilometer baseline, because we want to bring out the effects and then the improvement in the due to filtering. So here you can see very clearly with only 2 to 3% flagging, we can see a noise RMS improvement by a factor of 3. Similarly, for time domain astronomy mode, pulsars, so this is one such weak pulsar, and we can see 3x improvement in the flagging. Yeah, so the operational system, we have bookkeeping through fractional count. As you can see, we give this kind of number to the users, and typical flagging is 0.5 to 5% at 3 sigma threshold. This varies in different bands, and we have given recommended options based on the various parameters that we have monitored. This system is released, and we have about 520 hours of observing in the last cycle. That is about 35 to 40% of the time. And we have all sorts of sources observed with this. And so this is one thing from the recently published work on Abel 521 in band 3, and you could see this weak thing. So this, I want to bring out that how much is the dynamic range improvement due to filtering and recovery because of the removal of the correlated RFI. And so for future work, we are working on the analysis of these algorithms on visibility data, and we are porting the same for narrowband interference from satellites and terrestrial transmitters. And we are now also working to port these algorithms on CPUs and GPUs. And we extend this algorithm to the expanded GMRT, which is a proposal coming up for the next decade or so. And then the LFA project, where we have overlap in the frequency band. And we are also trying to look at various automations in the RFI identification and filtering using learning-based approaches. Yes, I'll end here and acknowledge various staff members of GMRT for their help. Thank you.
Great, thank you, Tasha. Do we have any questions? Just a reminder, you get a pin if you ask questions. He did put up his hand before.
Thanks, that was really interesting. One of the kind of limitations with this is that you're only calculating the median over a single buffer that you're accumulating, right? Have you thought about ways to like accumulate like a histogram or something over multiple buffers? So it's not a huge memory impact, but then you can maybe accumulate statistics over, hours rather than seconds kind of thing.
So right now, what we are doing is we are estimating the sigma through robust estimator over 1.3 seconds of time scale, and we are applying it to the next buffer because we can't certainly with an assumption that the gain and things will not change in that short interval, but we can look at longer intervals by say keeping track of those values and see that can be taken up and seen whether how implementation friendly that would be in the real time, and how much the gain and things will remain constant at that scale.
Quick question. What is your definition of persistent? Because you said the method won't work if it's persistent, and then you showed power lines affecting you 15 nanoseconds or something like that.
Yeah. So yeah. No. So by persistent, I mean that the interval over which you're estimating the statistics, you should have some good data and some bad data. It should not be that, suppose if I'm estimating say if my on time of the power line interference is 1 millisecond, I can't have estimation over 1 millisecond. Otherwise, I will get a wrong estimate. So at least I need to have 2 milliseconds or more in that case, because I need at least 50% good samples to estimate the sigma of the signal. Otherwise, I'll be doing sigma of the RFI. I'll be biased by that.
Okay, one more quick question.
So what are your ideas for using similar techniques to get rid of spectral interference?
So there are two ways of going about it. One thing is, if we can afford to use the same techniques we have shown. Actually, I don't have the plots in this, but I have shown to be mitigating good amount of interference coming from navigational satellites. We can do across the spectrum filtering and spectral filtering over time to get the right estimation. And then there has to be some equalization of band shape, because band will not be constant. So, but we can do it post FFT or we can do post integration, either way. But if you do pre-correlation, you will have to do only on n antennas. Otherwise, you will have to go to n square baselines. So it depends on where you put the trade-off and how much your processing platform can handle. But the same technique works well to pick up impulsive things from the spectral domain.
Great. I think we'll move on from that. Just a reminder, the Slack channel is there if you want to converse more. Thank you again, Kaushal. Our next speaker is Jane Kaczmarek, talking about mitigation strategies with the mirroring receivers.
Thanks for the introduction. And since David used his laptop, I'm going to use mine by proxy. Oh, sorry, still waiting.
Sorry, just to interrupt you. You're using your own laptop, but
No. I'm trying to take notes to make my talk more relevant to Spectrum people. So I want to make sure that, yeah, sorry for the confusion.
We have remote participants.
No, we are good. We will all see the same thing. When we see it. Oh, we missed the first slide. That's okay. It was a really pretty picture. There we go. Thank you. I'll speak in the mic. I will try not to move so much. So thank you again, everyone, for inviting me to give a talk during the focus meeting. My name is Jane Kaczmarek. I'm the senior system scientist at Murraying, the Parkes Radio Telescope, also known as the DISH. And would like to start by acknowledging the Wiradjuri people. They are the traditional owners and custodians of the land on which Murraying and the Parkes Observatory are located. And I pay my respects to their elders past and present. So, this is the old version. There should be a new version of this talk. That's okay, we'll wing it. So the DISH is a 64-meter prime focus reflector single dish radio telescope. It is, there we go. It is the only large single dish radio telescope dedicated to scientific research in the Southern Hemisphere. So we actually do have a lot of challenges. Some of them are the fact that we're quite close to Sydney, but not so far. But the real challenge that we have is that we have a very, very healthy, healthy visitor center. We have over 100,000 people that come to visit us at our very iconic telescope every year. I will also like to acknowledge that we have been operating for over 63 years. So we have a lot of experience in this space of spectrum management, and RFI mitigation, as well as seeing the spectrum evolve over that time. So we can compare quite a bit of how technology has affected us. Now, I did say that the telescope operates from about 700 megahertz to 26 gigahertz. Currently, that is not continuously, but we are in the process of making that a continuous frequency range that we are able to offer at any time. So this is the current receiver plan that we are working towards. We have the ultra wide bandwidth low, or the UWL, which is our main workhorse. In fact, all current scheduled projects use the UWL, and that goes from 700 megahertz to 4.2 gigahertz continuously. We will be installing in 2 weeks our cryogenically cooled phased array feed, which is a beautiful instrument that I'll be going into detail in a little bit. And in the coming years, the final receiver in our new fleet is the ultra-wide mid and high, which will be seeing a, I think, radio telescope first of 11.5 gigahertz of instantaneous bandwidth, which brings its own challenges. But what I really want to highlight here, or not, it's going to go for, well, with seeing that or having this much of a bandwidth means that we see more RFI in our band. Or with phased array feeds, we also see more of the sky, which means we have more RFI sources in our beam. So outstanding frequency coverage, we are incredibly flexible. If you need some specific coverage, we can absolutely offer it. There we go. We're almost there. But it does bring its own challenges. Come on. Okay, so this is what the challenges look like to a typical observer. Here is the spectrum of the ultra-wide bandwidth low, or UWL. I don't expect you to read those numbers, but just know 700 megahertz is on the left, 4 gigahertz is on the right. The known transmitters are in the little gray boxes on the bottom, and the beautiful little purple boxes are the the important science lines. So we've got methanol, we've got hydroxyl and we have hydrogen. And you can see, especially in the 704 megahertz line on the far left, we are battling constantly with RFI. Now, that might be, some of these, this RFI might be due to the fact that we are, it's a site-specific challenge that we have to deal with and we can manage, but there's something that we all share, and that's on the top right. So that is those little blue crosses that you see are satellites at a random time in 1 second at parks. So that is something we all share. It may not be exactly like that, but that is something that observatories are struggling. And I think we've had some really good talks so far today talking about how we can work with the ITU to make sure that we can work on nulling and so on and so forth. Oh, goodness. One of the ways that we are working on dealing with RFI is in the back end. So one of the great powers of Murray-Yang and Parks is that we have one backend. So that is Medusa. It is a GPU backend that is designed by Fourier Industries, or Andrew Jameson, who used to be based at Swinburne. So GPU backend's extremely flexible, relatively easy to code. You can actually put in piecemeal upgrades if you want to do them. Now, when I say very flexible, I mean we have user-defined everything. You can actually have sub-second sampling. You can have sub-kilohertz frequency resolution across that 3.5 gigahertz of bandwidth. And that really opens up the doors on different ways that you can recover, not just flag, bad data. And the impact of having a shared GPU backend is the fact that if we are able to implement one thing for one of our receivers, we can then actually kind of we can showcase it forward into other receivers like the CryoPath or the UWM&H. Now, the current strategies that we have deployed for the UWL are shown here. We have high frequency resolution and high cadence. Excellent. Which you can see on the left, what is persistent RFI? Well, it's not the mobile handset on the very far left. So you can actually see, well, often that data would be flagged if you're not sampling fast enough. We can recover the lowest frequency data there. It's a little more intensive because you have to write the data twice, but the staff are willing to support that type of science or that type of use. We also have spectral kurtosis zapping, so that's something that essentially measuring the non-Gaussianity of the data. This is done in the GPU, data is only written once. That is the mobile phone, that Wi-Fi and Bluetooth band there, and after, I feel like I'm gonna get an extra minute because I'm waiting so long. Okay, there we go. A pre and post spectral kurtosis zapping is shown here with one of our pulsars. Now, it's worth the effort. This here is actually an image of polarization at the lowest frequencies, around 750 megahertz. Polarization is very sensitive to low frequency data because we have a larger lever arm in lambda squared space. So while it might not be, it might be a little bit more effort, you can recover data that we once thought was lost. That was supposed to be my very happy ending slide, which is how I can tell things are out of order. So the next receiver that we currently are, that will be going on in 2 weeks is our cryogenically cooled phased array feed. 72 dual polarization steerable beams with a 2 square degree footprint. That is a huge upgrade from our single pixel feeds that we currently have on Parks. Also a huge upgrade from what ASCAP currently has as well. I also wanted to, oh, where are my notes? We also will be having a data rate of about 9 terabytes an hour with that receiver. So with a phased array feed, we have things, we can do spatial nulling or beam nulling. That's essentially just taking the ACM, finding the brightest eigenvalues and kind of correlating that with a spatial structure, whether that be moving, whether that be a static object, something like a telco tower. This is something that has been demonstrated with ASCAP. The image here is actually towards a GPS satellite with in the L2 band with spatial nulling on and off. So we have the techniques to do this. We just now need to do it for a much bigger system. So here's the CryoPath actually on Murray-Yang. The photo on the left is the image on the left is a relatively clean band. You can see the actual cool dish illuminated as well as the hot polarized ground. On the right, another GPS satellite in L5, clearly in the bottom right corner. So beam nulling will work very well for the CryoPath in this instance. I'm not even pressing the green button, but that is the end of my slides. So thank you very much, and I hope now, dang it. So next Monday and Tuesday from 3 to 5, we'll also be doing live observing with Murray-Yang. So if you do want to come and see what it's like to see 3.5 gigahertz of data, there it is, 3.5 gigahertz of data at once, and kind of talk about what the sky looks like and how easy astronomy can be, come check out our booth for the CSIRO booth. I would love to have a chat. Thanks.
You're all good. Great. Thank you, Jane. We'll continue with the questions. There you go over there.
Yeah. So impressive. I mean, really impressive what Parks is doing. And much of what we've heard here works really well in terms of the RFI flagging or RFI excision identification for spectral lines that are always on. But as we heard in the Shaw Prize lecture, there was a very slick RFI excision routine that actually flagged the Lorimer burst in the beam in which it was strongest. So how much does that keep you up at night? Or what's
not at all, because Dick Manchester worries about that, not me. I mean, you're right. We can't plan for the unknown unknowns. But in my mind, it comes down to data volume. And I mean, Scott and I have talked about this at length as well. How do we keep all of that data? We have the advantage of being a single dish, right? It's not crazy data rates compared to many, but 9 terabytes an hour is still nothing to sneeze at. I don't have an answer, but I sleep just fine.
I'm concerned you're sleeping too well.
The jet lag is keeping me awake right now, at least, so that's fine.
Any other questions? No, otherwise we will move on, and I wish you more happy sleeping. Our next speaker is Tony Beasley, speaking about NRIO, SpaceX, data sharing.
Okay.
You have the pointer over there. Yeah. They just swapped it out.
Well, while we're waiting, thanks to the organisers for allowing us to speak. What I'm going to talk about today is some work that's underway at NRIO. As I think all of us are aware, there's kind of this increasing risk of RFI coming from the satellite constellations which are being built. And so over the last couple of years, we have taken some efforts to sort of explore this problem technically and look for solutions. And there we are. Okay, I am giving this talk on behalf of the team that has worked on this, Chris Dupree, Bang Nan, and others at NRIO, and our colleagues at SpaceX. Over the past couple of years, starting during COVID, we've done a series of experiments. And these experiments were early on to characterize the impacts on the arrays from these satellite constellations, these satellite transmissions, and more recently to actually look at active mitigations associated with them. Along the way, we've done experiments with the VLA and the GBT, and more recently, as I'll describe in a moment, we're actually interacting with SpaceX in real time to figure out the impacts. We have developed mitigations, this operational data sharing and telescope boresight analysis, avoidance, I'll show you a little later. And this has gone very well, but there are challenges ahead, and supplementary coverage from space is kind of the next one. And again, I'll talk about that in a moment. So our first experiments during COVID in 2021 were to try and detect Starlink. It was actually harder than we thought. In those early days, they didn't have quite so many spacecraft up. And so looking at the sort of 10 gigahertz, 14 gigahertz, the places where their internet service are going to be providing signals, we searched and eventually we got the software signs all right and we could actually detect them. Same with Green Bank, it was a little easier. We were doing testing of both the uplinks and the downlinks. Now, as it turns out, it's actually very hard for us to detect the uplinks. The uplinks are a couple of watts and your cell phone is 1 watt. And so just in general, the actual transmitting boxes that people have in their houses are less of a concern. But the downlinks were certainly present. And so we eventually got to this kind of point where we had a very good model for what would actually happen to the VLA from a constellation of satellites flying over the VLA. And it's a geometric model. It looks at the natural fringe rates on the baselines. It looks at the actual distance from the bore side of the antenna and so on. And so you end up with results like these, where you can see in the gray, these are sort of the, the RFI that would be predicted to actually be significant in an observation. And down here is sort of the noise like that is below the noise floor. And so what we were doing was starting to look at this and think about what the impacts would be on observations. To do that, we actually set up an experimental site. And we did this at the Alamo Navajo Reservation just near the VLA. As part of actually assisting our neighbors with educational issues during COVID, we actually purchased 60 Starlink systems and installed them at family residences. And again, the primary reason was education. But it was also a great test for us as we ramped up the number of systems and as the constellation grew, we could look at the impacts. And so this has been published in this EVLA memo. It's a quiet part of the sky. There are some weak sources in there so that we could actually make sure we were detecting things and not compressing the system. And these are the kinds of results you get. This is the RMS in the image. And you can kind of see over the course of 3 or 4 years here, with what must be a doubling or tripling of the number of satellites in the sky, we actually don't see a lot of result. We don't see a lot of change. And so this was sort of some of the first indications that we had of, we can actually perhaps coexist at some level at these frequencies with some of these systems. And the same tests, of course, are done in Green Bank. Here you're kind of looking at the Green Bank beam, and you have a close approach where one of the satellites actually comes pretty close to the bore site. And weirdly, that happens maybe once a day or every couple of days. It's not as rare as you think. It's certainly not monthly. And so again, we were looking at the impact on Green Bank systems of that. So emerging out of that, we developed 2 approaches. The one on the left is kind of a mitigation scheme. It's sort of zone of avoidance. What we actually do is we kind of know where these guys are transmitting to, or SpaceX does, and we define a region made up of sort of SpaceX cells within which they don't land beams. Essentially, they don't serve customers in those areas. And there are two areas here. The little yellow one, they never serve any customers. And more recently, what we've been doing in the green one is they only use 2 of their 8 channels. And so this is the kind of interaction we have with them in terms of trying to avoid impact on our radio astronomy activities. The other one is this sky zone of avoidance. Essentially, when they come anywhere near the bore side of the antenna, that satellite switches off and it does not transmit. Now, of course, these things are transiting in seconds. They're turning the satellite off for 15 seconds. It does not have a profound impact on their systems. To give you some sense of what that looks like, on the top here, you kind of see a spectrum, and you can see the SpaceX channels above the noise level in here. And then you can see when we actually do this bore site switch off, we actually get back down to system noise. It's not too bad. There are other interesting little things in here. You get these kind of little birdies between the channels and so on. And these are also things that we work on with them. Operational data sharing. So you can actually extract from a website the location of most of their constellation, but it needs to be updated. These things are changing all the time. In parallel, to actually do these mitigation schemes, they need to know where we are pointing and what frequency we are observing at. So we've actually created this system where we essentially publish on a secure port, what is the VLA doing? Where is it looking? What frequency is it at? And so on. They take those data and they then read them into their real-time system, and they switch on or switch off, or they change the way they're actually deploying their beams across the landscape. And so this eventually will be bi-directional. What we're going to want to know is what channels are they actually transmitting at, so we can verify the interaction and so on. So we've done the first test of this. This software exists, and it's been quite successful, I would say. The early tests are very promising. So there are challenges ahead. There's a lot of remote sites, and we tended to build our antennas in remote sites. But those sorts of assumptions are really being turned on their heads. A lot of the RFI is not coming in through some very low-level side lobe now. It's coming from the sky. And of course, one of the things that we do as part of our business is we kind of walk on everyone else's front lawn. We use a lot of spectrum which is not dedicated to us. And so there is a discussion to be had here in terms of how we can both move forward and increase what we're doing. And there is just this incredible rapid change of pace of change of spectrum use across many businesses. Now, supplemental coverage from space, this is a relatively new thing. This is the idea that actually a satellite can talk to your cell phone. And of course, to do that, your cell phone is usually talking to a tower which is 10 kilometers away or something. To do that, to speak to something 500 kilometers away, you have to pump out a lot of power. So it takes the bandwidth right down to sort of 5 megahertz. And so this SCS is sort of the next thing that we're doing. We have done some early tests on the VLA. They are very strong. And in fact, if they're in the sky, pretty much regardless of where you're pointing and what you're doing, you can detect them. And they have an impact on radio astronomy observations. And so in the US, this process of examining the mobile bands, the wireless bands for use for SCS, which is a safety service, is underway. And so there's a lot of comment. There are people making a lot of proposals and comments to this process at the moment. In particular for us, there's a threat to the H1 line, I would say, is that unless we sort of deploy our sub-bands carefully, unless we start to build our systems in a way that can deal with this, there's a possibility that SCS, if approved at 1.9 gigahertz, would actually impact H1 observations in the US, and that's a problem. And so we are continuing to work with SpaceX to kind of look at what the opportunities are. In particular, we may have to change the way that we actually build our receivers. We may have to look at things like notch filters to deal with the mobile bands. We have not typically needed to do that because they were sort of distant and on the horizon, but maybe we are going to do that. We do some of that already for things like Sirius XM and other things. So it's been a very collaborative relationship with SpaceX. We're very pleased. We are looking at these various issues. The current focus is continuing to develop ODS, mitigating more of these effects. And as I mentioned, this supplemental coverage from space thing is a concern. So this has been a productive testing, data sharing, and data analysis with our colleagues at SpaceX. We want to extend this type of relationship to the other constellation operators, both domestically in the US and internationally. There are engineering solutions to all of these problems. It is something that we have to work on together with these potential users. And it will require funding. If we decide that we have to notch filter every receiver that we produce anywhere near the H1 line, that has a cost associated with it. The industry will need to pay that cost if they want to take those services on. And so, as I mentioned, the RFI landscape is changing rapidly. We need to think about what we're doing and how we're operating to continue to do the science that we want to do. And so if you actually look at something like this is an example of kind of landing zones around the VLA. They never land a beam in here. They only land channel 7 and 8 in here. This is Pytown here. And you can see the VLA and NG-VLA on top of it. And so these are the discussions that are underway with the community. Thank you.
Great, thank you, Tony. I saw one hand quickly, another one in the back.
Hi. First of all, thank you very much for this interesting presentation. I wanted to just ask, because you mentioned that in your presentation, and I think orally as well, that supplemental coverage might be seen as a safety service. And I just wanted to double check that, because within radio regulation, safety service has a very specific definition. And unfortunately, according to the rules, if some service would be granted the status of safety one, that means that you can no longer complain about any interference coming from it. So, usually at least terrestrial component of IMT is not granted that status. So I just wanted to check if it's some internal US regulation or just some words around, or is it indeed legally binding and it's a US intention to treat this service that way? Thank you.
No. Well, I feel like you're accusing me of being a lawyer, which is very disturbing. So I don't know if I mean, I said the word safety service, and apparently that has a very specific meaning. I don't know if that's exactly what is meant by that. But certainly the concept behind SCS is that, yeah, you're hiking in a forest and you break your leg and you can use your cell phone to call a satellite to get someone to come get you. So it is a safety related service. Now, this question about the rules, I do believe that what's going on with regards to using the fixed mobile bands, from spacecraft as part of this service, this is changing the very nature of our business. This is not the set of rules and we are playing within the rules. I think the FCC and NTIA, et cetera, they are changing the rules of engagement here. And that's why, we certainly feel it's very appropriate to be looking at the technical side of this, because we all will be forced to the table, I believe. Yeah.
I have another question here.
Thanks, Tony. It sounds like an excellent relationship you've built up with one vendor, and obviously you want to scale that. So is this expensive for them?
So we've interacted with a couple of the vendors, and, these ideas that are being exposed, they've been published and discussed in other meetings and so on. So I don't think there's a lot of great surprises. Is it expensive? Well, to the extent that the mitigations, the operational mitigations we have here, no, I don't think so. I don't think it costs them a lot of business, if that's what you mean. I don't think it changes the design of their systems necessarily, some software changes, I guess. If every radio astronomy observatory in the world decided they needed tunable superconducting notch filters in the band to enable some of this, yeah, there's a cost associated with that. It's a very small cost compared to the size of this overall business and so on. So I don't think that their interaction with us and the interactions we have with OneWeb and Kuiper and everybody, I don't think they're being driven by economics. I think that certainly I feel with SpaceX, there's a genuine sense that they don't want to necessarily destroy radio astronomy here. So they're pursuing these things and so on. But it is, as I said, it is possible that we will get to a point where money does need to change hands. And so I don't think that's going to talk their business. No.
Josh, is your question directly related, because we do have another audience? Sorry.
Hopefully we'll get to you in a minute. Thanks, Tony. Really interesting. One of your slides mentioned out-of-band emission. I wonder if you could say a little bit about out-of-band emission and incidental emissions and what impact that has.
Sure. So, as part of the production of their transmit signals, they have local oscillators in their spacecraft and so on. And we have seen, as they've developed their systems, that, there was a bright line at the edge of one of their bands, and it turned out it was a local oscillator setting. So along the way, we have detected things like that and work with them to change their LO definition to deal with parts of that. Some of the broader stuff, the lower frequency stuff that was discussed at LOFAR and others, this is few hundred megahertz. I mean, this is chips, right? This is digital electronics and so on. Not sure there's a mitigation for that. But they can certainly look at, once they're aware of the problems, they can design their systems to try and improve on that. I think we're in a much better situation than, for example, our OIR colleagues who, there are not many mitigations that are available, and that has not proved to be, an easy problem in any way. So I think that, the work that I have seen that has brought some of that stuff forward is good, and you should discuss it with them, and maybe they can redesign in future generations the system to remove some of that out-of-band stuff. Yeah.
Very quickly, thanks a lot for the very nice presentation, and for all this research, also to SpaceX for doing this with you. So my concern, or my question concerns the level of interference you're measuring. So now you have a noise level, and you say it doesn't change a lot, but this signal that bothers us is maybe well below the noise. So how do you address this in your studies.
Sure, I guess we can't get the slides back up. I mean, that's true. We're sort of assessing the impacts by drilling down in a quiet field and looking at the RMS at the bottom and checking the fluxes of weak sources in the field and so on. Are you going to break the square root of T law if you go deep enough? That is possible. These are challenges we've always faced. You know, the systems, the actual observatories themselves have always had these sorts of problems as well. It's a good question. It's something that we'll have to develop an understanding of once we build big arrays. SKA will face this, and GVLA will face this, etc.
Great. I think that's been some nice discussion, but we do need to move on. So thanks again, Tony. Next speaker is Divya Oberoi about managing RFI at the GMRT.
Okay, so while the slides come up, yeah. So I'm going to talk about a different telescope, the GMRT. One of the nice things, or one of the things which sort of makes life a little easier for us, is the GMRT works at lower frequencies, from about 150 megahertz to about 1450 megahertz. And everybody is moving to higher frequencies. Your telecom service providers, all these satellites you talked about. So that makes life a little bit easier for us, and we're very thankful about that. There's another thing which is very different about GMRT, is that we have a lot of neighbors. Okay, here's the pointer. That's where GMRT is. This is a population density map of India, somewhere between 500 to 1,000 people per square kilometer, right? This is perhaps the only sort of extremely sensitive telescope, world-class sensitivity, which is operating in a neighborhood with so many people. So in a 30-kilometer radius around us, that's a few thousand square kilometer, we have order 500,000 people, about 230 villages. You know, all of these people just want to lead their normal lives. They need power to be delivered to their homes. They need their broadband. They have their microwaves, whatever. And these people were mostly here before we got there. So it's not possible for us to, you know, think of this place as a place where you might ever be able to set up a radio quiet zone. So if you have to think of how we are going to operate, how do we strive to maintain a clean spectrum in this band from about 130 to 1450, you know, the only strategy we have is coexistence. That is really the bottom line. We have to figure out how to live with these people, get them, you know, what they need, while we are able to keep the spectrum relatively clean for us to be able to operate. So you could divide this into sort of two major buckets: minimize the generation of RFI, and then on the other hand, whatever has already now been generated, figure out how you want to deal with it, right? So these, in this box, minimize the generation of RFI, are all the things which Dave mentioned in his first talk as what we should do, right? You keep monitoring to find out when something new is coming up so that you can go after them, talk to them, try to get it down. Of course, minimize self-generated RFI, work with all of your million neighbors to figure out how to help them curb RFI, work with the regulatory authorities, which I'll say a little bit more about as we go forward. And there are other government agencies as well, which have their own projects, you know, which make a difference. On the other hand, you know, for the RFI, which has already been emitted, which is now, you know, ambient, how do you avoid it? For example, looking away from the spacecraft, which are radiating down your bore site. How do you design, you know, come up with a system design which is more RFI resilient, so larger number of bits and stuff like that? How do you excise in real time, like what Kaushal was talking about earlier? And how do you flag what has actually made it to your data, like what Dharam was talking about in his presentation? Right? I'm going to focus primarily on, you know, these two things. I don't have a whole lot of time, but so in terms of, I mean, there's a lot of doom and gloom, and I've sensed that myself. I feel that myself. I don't think our spectrum is going to get cleaner, but I think we have had some successes, and I think it's a good idea to sort of keep those aspects in mind as well. So in our region, we primarily have 2G, 3G, and 4G spectrum, which is being used by the telecom service providers. There are 4 of them in the region where we operate. With 3 of them, we have good faith agreements that within a 30-kilometer radius of the GMRT, they will not operate in the bands where GMRT is operating. So they are moving, or they have mostly moved to higher frequencies, about 1800 megahertz or so. So there are about 250 cell phone towers, of which 200 have migrated. And the 4th one here, right? I said that with 3 of the 4, we have this agreement. With the fourth one, we have the exclusion zone they are respecting is 15 kilometers rather than 30 kilometers. We're trying to sort of convince them to move away. They're digging in their heels a little bit, but it's a good faith thing. I mean, that's the spectrum they have paid for. So it's really only in good faith that we can ask them to move away. For 5G, we worked with the Government of India, with the Department of Telecom, that's what DOT is, to establish an exclusion zone of 30 kilometers radius around the GMRT, where none of the spectrum in GMRT bands was actually auctioned. So that will remain clean. So that was a big relief for us. So none of the telecom service providers will have any 5G services in the 6, 7, 8, and 900 megahertz band. That I think is something we are very grateful for. The other, so the plan we've been trying to push in India is that, over this limited geographic region, give us protection over a part of the spectrum larger than the radio astronomy band. You've heard, many people pointing out those thin slivers of yellow, which are the reserved bands for radio astronomy. Everybody is going wideband, right? We can do 400 megahertz of bandwidth. And so if you had 10 megahertz of radio astronomy reserved band, that's not going to do you a whole lot of good if you had, 400 megahertz of these bandwidth. And we've fortunately found, a ear who's willing to listen to us in our Department of Telecom. So in the frequency allocation plan, which was published in 22, we have this entire region, 585 to 608, and then 614 to 890, which they say that to the extent possible, it will be reserved for this radio astronomy service facility at Pune, by which they mean GMRT. And for those of you who look at the stuff, you know that between 608 and 614 is anyway the RAS band, right? That's the band which is reserved for radio astronomy service. So we essentially have from 585 to almost 900 megahertz as a band, which our telecom regulatory authority is willing to try to preserve for us. That I think is huge. Our country is in the process of updating this national frequency allocation plan in view of the many decisions which were taken at the WRC 23. That's basically a big push by the telecom community to have more band allocated to them. And we are working here to try to preserve this footnote, which allows us this regulatory protection even as we go ahead. Okay, the 500,000 people who live there and the industries which operate there, they need power, right? And that's going to come via these high tension lines. And Kaushal was showing, maps of, the transformers which were there in that region, which are the source of that impulsive sparking, which he's trying to get rid of. And so we work with the power companies essentially to try to keep the lines healthier than they care for, right? As far as, their transmission efficiency is above some threshold, they are good with it, but we are not. So we identify for them the places where there is sparking, where there are loose contacts, and try to work with them, sometimes at cost to us, to fix those places so that we can maintain a clean RFI environment. We have also managed to succeed in pushing away some of the power lines away from the GMRT. They were originally going to cross through the GMRT, but now they have been moved at least the minimum distance between the power line and the closest antenna is 6 kilometers. And another one, which the terrain did not allow us to move it further out, that has been built to a higher specification, which therefore reduces the RFI potential of that particular that particular high tension line. In principle, we actually have the ability to regulate the industrial growth in our region, because any industrial power connection in that vicinity requires a no objection certificate from the GMRT. So we work with these industries to figure out exactly what is it that they want to do, what their setup would be, how can we work with them to mitigate the RFI which their equipment can produce, to provide them shielding solutions, usually not at our cost. But that's something which we actively engage with actually many tens of industries at any given time, and a few thousand since we started this effort. We've recently been recognized as a formal exclusion zone for industrial development by one particular municipal body. And this is a battle which we are fighting right now. There is a semi-high-speed train track which threatens to pass through not so far away from us. The original design had it running parallel to one of the arms and cutting through the western arm. That has mercifully been revised. The revised route, which is yet to be confirmed, is now proposed to pass through much further to the east of the array with the minimum distance of 10 kilometers between the nearest antenna and us. That is still sufficient to saturate us when the sparking happens, but that's a discussion which is underway. Also because this is now at one side of the array rather than cutting through the array. You can think of solutions which are going to reflect the RFI from these fraction lines to a direction away from the array. Okay, so in summary, I'd like us to sort of remind ourselves that, yeah, it's a very challenging environment in which the UGMRT operates, but we are still producing millijansky RMS in 600 hours of integration. So I think we have managed to make things work for us. It has taken a considerable amount of, effort, multifaceted approaches. You've talked to a lot of people, worked with a lot of government departments, industry, whatever. But we've managed to do this. We hope that we will be able to continue to do this. It's going to take us even more effort going further, that we recognize. And I do want to take this opportunity to thank the Department of Telecom, Government of India, to be friendly to us, to help us deal with this thing and be on our side when we needed their help. So with that, I'll stop and take any questions.
Great, thank you, Divya. Are there any questions? No? Oh, I thought I heard something. Never mind. Otherwise, we will move on and thank Divya again. And our last speaker on the topic of RFI mitigation, management, so on, is by Ningi Habana. Great. Talking about the alleviation of the impact of spaceborne RFI on geodetic VLBI.
Good afternoon. I don't know how this works. Okay. Anyway, while we're waiting, I will be, oh, there we are. We don't have to wait. Talking about our mitigation strategies at the Goddard Space Flight Center to try to deal with the RFI we see. There we go. A lot of background has already been given, so no need to go through that. Just our sources are further away than the satellites we see, and the satellite is much stronger than the sources. There's a lot of emissions and downlinks within frequencies we're interested in, where in this case, we is the VLBI Global Observance Service. And then there's obviously everybody here has the same motivations of trying to deal with RFI, is try to get as much clean data as we can. And multiple strategies have been discussed, moving from diplomatic, as the NRO is doing, instrumental and avoidance techniques that we just heard about. And in this talk, we will be talking about avoidance strategies, and the screen is off. Avoidance strategies, where we are developing a dynamic mask, where dynamic is in the sense of you have your antenna center, and these are the sources that are visible to it, but then you have satellites that are flying at any given time, and you know the path of the satellites, and you develop a zone around each satellite that you say, I can't observe at the zone at a given time, which is where the dynamicism comes in. And then we know that we have tens of thousands of sources that we could observe, but geodetic applications, which is what I mainly deal with, is limited to about 400 sources. And with this approach, those 400 sources become even reduced because satellite is within a certain path and you can't observe in those regions. And then the first step towards this dynamic approach is try to get a track of all the satellites that might be able to interfere with you. And for that, we have a database that we update daily with TLEs, two-line element sets, which is just the fancy orbit tracking. They give you averages of the satellite's track of the satellite's positioning, and you can sort of compute your look angles or your right ascension and declinations from those. And then the issue with those is, as was mentioned, these satellites move very quickly, and TLEs don't come as periodically as you would like them to. So, and again, they're also averages. So not the best way to go. Ideally, you would like to deal with the satellite producers directly and get the orbits from them, but that's never going to happen. So this is the next best thing. And then some other information that you would need within the database is not just the satellite's orbit, but also information about those satellites, like what bandwidth are they emitting at, what is the power of the emissions, certain things like that. Again, is not information that you are easily going to get, but luckily for them to be able to emit and be launched, they have to file with the FCC, which is the Federal Communications Commission in the United States. And in filing that, they have allocated specific frequencies and specific emission powers. And then for that, you need a very good intern that is willing to go through thousands of FCC documentation and get that information for you, and then you can put that in the database. And then with that information, we then say, if a certain satellite with certain information that we know about is within our path, here's the threat level that it poses. And then it will be flagged. And then what we also have near the observatory, we have our antenna at the Goddard Geophysical Astronomical Observatory is a 12-meter dish. That's where most of our observations are made from. And we've acquired a small 1.2-meter dish that is near it and has a much wider beam and a much wider bandwidth than it goes from 2 to 18, the field antenna, and the main dish goes from 2 to 12. So a small antenna is a standalone that can scan before the main dish sees a satellite. Thus, if it's a satellite that is threatening towards the main dish, you can get an alert from the small satellite, from the small dish, telling you here's a threat coming, and you can shut this one off. And then some observations that we have made of certain satellites. This was from the one on the left. I think this is my left. The one without things labeled on it was Sirius XM5. We observed directly at it, and we can see it raising the noise floor significantly by about 10 to 12 dB. 2 minutes to go. Yay. And then on the other side is when we're observing a TDRS satellite, and on the lower end of the spectrum is a DORIS receiver, receiver that we have on site. DORIS is another geodetic technique for positioning that observes in the lower S-band, and then TDRS is another satellite. And then we've also done tracking of satellites with antennas instead of those two satellites that we just saw were geostationary and geosynchronous. And then we could also track low Earth orbiting satellites like the UpStar satellite, where what we did is you just point in a certain position that you expect the satellite to be, and then you observe on the left, we have systems temperature, and then we have time on the y-axis system temperature, and then we have time at the bottom. And then you just wait for the satellite to pass by and then see how much it raises your system's temperatures. And then conclusions, you can just look at the screen for those. That's it.
Great, thank you, Mlingi. You might also win my award for the cutest radio telescope picture of the CEA. Are there any questions? No, otherwise we'll say thank you again very much, Lingi. And moving on now, switching track just a little bit for the last two talks in the session, we're switching to pulsar and fast transients research and the impact of RFI on that. So our first speaker there is Franz Kirsten, talking about fast radio transients in the era of big RFI. Big RFI, it's a different way around.
Big RFI, exactly, yeah. Is that working, I guess? Yeah, so that's another one of those high-level overview talks of two chapters in the RFI white paper and the future of radio astronomy in the ever-growing environment of RFI. So yeah, this is something I'm giving on behalf of a bunch of people, two chapters. So I'm most involved in the what should be called fast transients, because there's also the slow ones. I'm doing fast transients. And then the cosmic rays and neutrinos, we're touching upon that because this is also pretty short signals in the data. But I know I'm not an expert on cosmic rays. If you get a question on the science, I'll have to refer you to Anna. Right. Now, where's the forward button? Here we go. Okay. So fast transients, what are we talking about here? So we're talking about pulsars, so supernova remnants, neutron stars, spinning lighthouses in the sky, and you get a pulse at every rotation, synchron emission, steep spectrum sources, extremely bright, and you can do lots of things that I'll go into a little bit in a minute. Then we're talking about fast radio bursts, my favorite type of sources. So these are also highly dispersed objects, which means the higher frequencies arrive before the lower frequencies. Similar thing that we know from the pulsars as well. It's just dispersion, cold plasma law. It's just a propagation effect. And the figure you see here, oh God, how do I go back? This way. Figure you see here, this is actually the Lorma burst. So if you show the short price on Monday, which I missed, this is actually the burst for which they got the price. Then we're talking also about the long period transients, something that's very recent. So those are objects that are also quite bright, but they have rotation periods of up to 50 minutes. So we're talking something that rotates very slowly, but is a coherent emitter, and also there we have no real idea what they are at this point. And then there's the cosmic particle air shower. So we have cosmic rays or neutrinos impinging on Earth, interacting with either the atmosphere in the case of cosmic rays, or when you need a bit more matter for the neutrinos with ice or rock, and then you have radio emission coming from that. Now, going into detail a bit more, what we can do with the pulsars. So pulsars are, as you might know, extremely accurate and stable clocks. They actually sometimes are even more accurate than atomic clocks, and you can do great science with it. In particular, tests of gravity, be it GR, alternative theories of gravity, they all need to pass what you see with the pulsars. And it's all just because pulsars are such stable rotators, and you see all sorts of effects, be it propagation, be it if they are in a binary system where you can then measure binary orbits and whatnot. Equation of state of dense matter is, of course, a hot topic there as well. And then there is, of course, the gravitational wave background. So just because, gravitational waves pass through space, the distances change, and you see this as a residual in the timing, because all of a sudden you have a little bit of extra travel time, and then you correlate this across the pulsars in your array, and then you find your gravitational wave background signal. Pulsars are also subject to propagation effects. Most importantly, of course, dispersion, meaning just that they arrive late, which actually helps with RFI. I'll get to that a little bit later. There's scattering involved. Scattering is also highly frequency dependent, which of course with pulsars, you always have to find the balance where you want to observe them, because they are faint at the higher frequencies, where high for me is 5 gigahertz. That's where they typically get fainter, but there you have less scattering. So you want to go low, but then they're scattered to death. So then it becomes a bit more difficult to actually observe them. Then, of course, there is the fast radio bursts, which some people might call pulsars on steroids, even though we have no idea whether they actually are pulsars. We just don't know. Leading contenders there are the magnetars. Magnetars to the rescue whenever there is something bright and we didn't understand it, but that's all right. So down here at the bottom, this is the transient phase space where we have the duration of the transient plotted against the spectral luminosity. Down here are all the pulsars. Then we have, the crab giant pulses, some crab nanoshots, and then up here in the short and extremely bright corner, this is the FRBs. Most of the FRBs have only ever been seen once. Some repeat. So it's not all, so some, the question is it one type of source? Is it not? So this is still under, active research. We have no real idea. Nevertheless, since FRBs are of cosmologic origin, simply, we already saw this from the dispersion measure because dispersion measures are way higher than what you would expect from the Milky Way contribution. Lots of localizations showed that they actually are at redshifts of at least up to 1, which also means that these very point-like sources, coherent sources, traverse intergalactic space. And these signals have then impinged on them the effect of each and every individual electron that they encounter along the way. So you actually count the matter in space. And this makes them excellent cosmologic probes. And one such example of what you can do, this is what Jean-Pierre Macquart did in 2020. It's the Macquart relation where he sort of looked into the missing baryon problem, where you look at the redshift of the FRB plotted against dispersion measure, and then have a look into your favorite cosmology, and then you can sort of see, okay, the FRBs actually, we do see all the matter that we didn't see before because, it's super, very hard to observe all these baryons, but the FRBs actually helped to sort of, was one of the first attempts at solving this, the missing baryon problem there. Now, long period transients, slowest coherent rotators known, as I would call them. Natasha Hurley-Walker had this lovely paper. Oh my goodness. Nope. Oh, what did I do? I broke the system. Can somebody help? Sorry, broke a wrong button. No. Okay. Natasha had this lovely paper of this source that was an 18-minute rotating source, found it in GLEMAX MWA data through visibility differencing. So you just take your images and you subtract one from the other, and then something remains. And over time, you actually find that this happens again and again. So they're actually of galactic origin. So the dispersion measure is quite low, somewhere around, the hundreds. And they've shown to be strongly polarized, which is also very similar to pulsars. Pulsars are also strongly polarized, similar to FRBs. So that's also why again, this is why I brought up the magnetars. People are also speculating this could be extremely slow magnetars, but then it's always a question of how do you make them actually really pulse this bright. It could be all sorts of different objects. Also here, it's not entirely clear what exactly they are. Now then, coming to the cosmic particle air showers, here also we're talking about nanosecond pulses in the time domain. Here we got nanoseconds and an amplitude. The neutrinos would be causing these extremely short spikes. And with the air showers, you see somewhat of a spike and then a tail. I actually don't know why it goes negative. I need to ask Anna. I actually don't know. And in the frequency domain, you sort of also have this declining in frequency, where the neutrinos, they go all the way up to higher frequencies. But mostly for the cosmic ray air showers, the sweet spot here is somewhere between, tens of megahertz up to about a gigahertz. And, the question there is, where do they actually originate from? Because localizing those sort of cosmic rays and neutrinos is an extremely difficult thing to do because you got this very broad shrink of cone. But then, of course, the question is, how does acceleration happen there? Where are these sort of cosmic rays produced? What is generating them? Now, in terms of the spectrum that we're interested in for the fast transients, of course, with the pulsars, LOFAR observes them down to around 100 megahertz, where you can do all sorts of lovely things, like space weather, for instance, because if you have a pulsar that is somewhat, close to the sun, you can actually measure solar wind because you measure the excess in dispersion measure that you wouldn't see without the sun. And then the pulsars typically, like I said, they're speak spectrum sources. So we go to up to, say, maybe 5 gigahertz. But then with the magnetars and galactic center pulsars, because there is so much matter in the way, you might try and observe even higher. People have tried with ALMA and were quite successful. So somewhere around the 200 gigahertz range, we observed some magnetars. But our favorite range, I would say, is between the 100 megahertz to maybe 10 gigahertz. That's sort of, at least I would say, favorite region. The FRBs, well, FRBs are quite a beast. So we've seen them down to also, with LOFA, down to 100 megahertz roughly. Chime has seen most of the FRBs. I think they have about 5,000 by now. Around 400 to 800 megahertz. So this is where they see them all. But for the follow-up, we're also doing L-band, so 1.4 gigahertz. This is where the FRBs are. They've been seen up to 8 gigahertz. At least, this is in the breakthrough listen data with the GBT, the very first repeat up to 8 gigahertz. But then beyond that, I don't think anybody has tried. So we don't know. Maybe we can find them there. We haven't found any real good multi-wavelength counterparts to FRBs anyway. They have only been seen in the radio, so there's no optical counterparts at this point. Now with the long period transients, the sweet spot is probably somewhere between 400 to a gigahertz. Although in the previous plot that I showed you was an ASCAP detection with a 54-minute long period transient. That was actually detected also around L-band, so 1.6 gigahertz. But Natasha actually said, well, the sweet spot is somewhere between 400 megahertz and a gigahertz. Cosmic particle air showers, they're also down here, 10 megahertz to 1 gigahertz. So this is what we as the fast transient people really would prefer. Now, since we all love RFI, I thought I'd show you a few examples of our most haunted RFI that we come across. So for the pulsars, here on the bottom left, that's a dynamic spectrum, some 5 seconds of data of 0329. 0329 is so bright you could technically see it with your eyes. And you do see individual pulses here coming through. So the bright dispersed pulses, so this is undispersed data. You see the nice quadratic sweep. And then you have, of course, persistent RFI going through, and you have impulsive RFI at the GMRT. So this is all in there. If you don't take this out, I mean, 0329, you do detect individual pulses still, as you can see, but this is one of the brightest pulsars. There's others where you wouldn't be able to do that anymore. Then they have quite nice, as we've seen before, quite nice mitigation algorithms. Here, top right, in green, this is the unfiltered data. So this is folded data. So I don't know how many minutes or hours of data this is, but this is folded, which means, you're just taking the period and you're just stacking your data effectively. But if you didn't know that there's a pulsar here, you wouldn't find it unless, of course, you remove that RFI. Similar thing on the bottom right, also here. Well, I think you would doubt that there is really a source there because it's quite low signal to noise. For the FRBs, there is one nice example that I came across because we do a lot of single dish observations here with the Westerbork, a single dish station, 25-meter dish in the Netherlands. And we had simultaneous observations at Westerbork and the Onsala 25-meter dish there. And at Westerbork, we had this lovely detection, and you see the source scintillating nice and bright. There is persistent RFI because what we do is a pretty simple thing. We just flag wherever, or we continuously flag wherever we know that there is RFI because it's quite often it's just there, but we lose a lot of data, but still. So the point is, Westerbork detected this through our detection pipeline, nice and bright. Oh my God. Whereas at Onsala, we didn't detect it in the blind search, even though we had 500 megahertz of bandwidth, whereas Westerbork had 100. So you might think that there is something here, but the trouble is this is de-dispersed, right? So you see this sweep here, this is going the wrong way. So this is actually de-dispersed data. What you see here is an extremely bright radar burst. And if you then dig, because we knew we got this source and we should have seen it because it's similar sensitivity, you then zoom in and then there's this little spike here and then there actually is our FRB. It looks similar, but of course, signal to noise at Westerbork is way higher. So you just miss sources. That's the point. You just miss them.
With long period transients, this is an example also from ASCAP. They actually thought that this is another burst of their source, but this is a DM144. And if the pulse is tens of seconds, de-dispersion doesn't help you anymore because de-dispersion at this band at 144 is, I think, half a second or so. So, you have no way of saying, is this actually another burst or is it not? And it wasn't, it was just RFI. Similar, oh yeah, here is now an MWA example from Natasha. And since this is a PDF, I turned a GIF into a manual GIF. So this is now visibility data. And down here, this is actually a satellite, and this is 4-second integrations. And then, this thing just nicely moves through the entire beam. And I can't go back now, it's a GIF. But the point is here, if you do the visibility differencing, you get hundreds of candidates. You really get loads of candidates, so data rates just increase, and then you go through this and you realize there's nothing. And then with the cosmic particles, of course, there are similar things. So here we have a time series, function of frequency, and there's just satellites all over the place. And of course, they also, just like Olaf Wucknitz did once with LOFAR, they nicely track airplanes. So you have longitude, latitude, and then you have these lace flight numbers, and they just, you can track them across the sky. And that, of course, increases, again, your data rates, and you have so many false positives that you just don't want to have. So this is actually the last slide. So what's happening with the RFI? Of course, as you know, it just ruins science completely sometimes. You get data rates so high that, sometimes your students just don't want to go through this anymore because there's just so much rubbish. AI to the rescue, yes and no. Sometimes it helps, sometimes it doesn't. And so Clancy James actually said, potentially we're losing, in case of the FRBs, we might be missing 50% of our sources. So there's just loads of false negatives, in particular if RFI becomes worse. And yes, skewed spectral info. If we lose half the band, of course, spectral information gets lost. And most of all, as you've seen in the previous talks, this is bloody expensive because so much work has been going into RFI mitigation. Imagine this had been gone into science. No, it went into RFI mitigation. We're doing great statistics and we're teaching students great stuff, how to do signal processing. What if they had been doing science? Anyway, thanks.
Great, thanks, thanks, Franz. Do we have any questions? Oh, yeah, okay, there's a question in the back.
Okay, thank you for the presentation. Lot of complexities in it, and what is the final comment of yours? So what to do in the future for these rooms? Already you have addressed it less.
I don't have a good answer to that, to be honest. I really don't. I mean, in the end, you've seen all these great presentations on very smart algorithms on actually getting rid of RFI and trying to replace it. There is no other way than investing into that, unfortunately. But of course, try and apply for funding for an RFI mitigation project. I don't think this is very sexy. I don't think it's going to go through, but I don't know. Maybe people have been getting money for that. No, I don't have a good answer to that. Yeah, dispersion with FRBs, dispersion helps, of course, because if it's high dispersion, then you can tell 0DM from a real source. But with other stuff, and especially with the long period transients, dispersion doesn't help anymore.
Great, I think we'll leave it there and say thanks again, Franz, very much. And now on for our final talk in the sessions. Apologies for running a bit late, but our final talk is by Pai Wang on a fast perspective.
Thank you for the organizer. I'm Pei Wang, and from the NOC and the Chinese Academy of Sciences. And so I'm very honored and to have this opportunity and to introduce some of the outcome of the fast observation and the RFI mitigations. So I will talk the fast perspective on the dynamic universe, and I focus on that the pulsars and the fast radio burst. Thank you. I'm Pei Wang from NOC, and on behalf of the FAST collaboration. Okay. I just to further to introduce the FAST equipment and the RFI motivation. So, and we can see the FAST is a 500-meter aperture spectral radio telescope, and this single dish telescope is located in the Chinese Guizhou province. And we can see that the single dish, this is around the hills, and so that is far away and to the villages and the cities. And so relative have the clearly RFI environment. So so we can see the frequency range and for the FAST is from the 1 to 125 gigahertz, and with 19 beam L-band receiver and equipment. The sky covering from the technician from the -14 and to the plus 36 degree, and have the huge gain with the 16 Kelvin per density. And from the 2020 and the FAST in the for scientific operation. So, and we can see this is a cartoon picture, and this is the FAST can observe and for the pulsars and the FRBs and the black holes and the GW. And we can see this is the FAST, and this is from the 100-meter F-Sburg and the GBT. This is 300-meter receiver, and we can see all of the scientific goals, and we can join in that parameter space, and this is the space, time, and the frequency in the different region. And so the FAST is for the every year have the nearly 5,000 hours per year, and half of the time and for open time for the call, the proposal call. The FAST have set the radio point zone protection and have the locally, and we can see this is the center is the FAST set, and to see the different levels, and from the first round is the 5 kilometers reading, and the 10 kilometer reading, and this is 30 kilometers. The FAST have regular and to do the RFI monitoring, and from the different years. The red one is average, and the blue one is maximum. And we can see that the this is spikes. This is from the satellites, and we can see this is the baseline is flattened, and relative clear environment from the FAST set. And for the mitigation RFI, we based on the native beam receiver, and to do the spectral filter, and to use based on the native beam cross correlation functions, and to remove and mask the data. So the we can compare with the 300-meter receiver and to the 500-meter FAST, and have FAST have the design advantages. We can see that the shadow and from the receiver is huge because that is optic mass is heavily obscured. But we can see that is smaller in the FAST, and so that is clearly for that's the shading, and so the small shade and can reduce the RFI scattering and provide the accuracy and the stability in the flux and polarization measurements. Okay, I will introduce the progress in the observations. From the 2020, the first line to now, they have the 5 big surveys project and published about the dozen of the high impact journal and in the Nature and the Science, and 2 on the Science Bulletin. We can see the FAST search is the first step. The pulse search is the first step, and to prove the high density equation of the state and the emission mechanics, and also the basis and for the astrophysics. And so we can say this is a timeline for the pulsar search, and from that the first pulsar discovered and the first FRB and the first millisecond and the first exoplanet discovered. So, and we can see, and from the commissioning phase, the father have discovered the first pulsar. Until now, the fast the two surveys have discovered nearly 1,000 new pulsars, and we can see here in the recent years, the fast dominant the pulsar discovery number, and in the recent time. So the further sensitive the pulsar search in the different two of the surveys. The one is the craft is a conventional radio drift scan further survey, which has a huge efficient and on the sky coverage, and another is the GPPS, is the galactic plane and grading pulsar survey that is most deep. So, and after that, the new pulsar discoveries, and we have to do the follow up, the timing, and the new specialized pulsars. For example, that the double neutral stars and the millisecond black widow binary systems, and from the high energy associated the sources. Especially, and we have discovered and two of the long period the rolling pulsars in the global clusters, and this is sets a new record and for the longest spinning pulsars in the global clusters that confirms that they have another branch of the pulsar population in the global clusters, and we can see here this is that global cluster, and we can do the two of the samples in the PP dot, and we can see that is below the this line, and indicates beyond the dipole field radiation model. So, and for the FRB discoveries, and we have discovered dozens of the new FRBs. This is also comes from the low luminosities. They comes from the early stage of the cosmic age. The one is repeating the FRBs, so that is friends have displayed. The father have the discoveries the red dots, and in that transit perimeter space. Based on the sensitivity of the father threshold, and we can exploit to find that the high redshift fast radio burst. So for the radio burst, we have the two main strategy, and for the study, what is the reason, what is the central engine, and another is what is the environment of the FRB orange. And so this is one of the work, and we have detected more than 16 bursts from the one repeater FRBs. And so we have discovered that is the first the bimodal burst energy distribution, and from a repeating fast burst. That indicates that have the multiple type of the emission mechanics. This is another discoveries, and to use the Crafts survey, and we have discovered another repeating FRBs, and this is the first persistent active FRB keep going, and this is also have the highest DM axis for the FRB repeating. So this repeating that is far away toward the Marquardt relation. These results are also published in the Nature journal. And this is the first, that is the last page, and we can see the first is a highly efficient FRB or the pulsar funding machines, but have the small sky coverage compared with the ongoing interferometers, just like the DSA 2000 ISK median and NGVLA. And so combine the fast sensitivity and we decide the new telescope can use a snapshot and to combine the further sensitivity and to real time to search and trigger the deep observations. This is we call this is a cosmic antenna. Okay, thank you. The best is yet to come.
Great, thanks, Pai, and ending on that exciting movie trailer. We are over time. Is there any quick question?
Just quickly, what size is the cosmic antenna? I didn't see a size scale.
Yes, that is a very important question, and the scientific that is the key targets is the FRB and the pulsar. Because the cosmic antenna have the larger sky coverage, and we can increase that the FRB detection rate. And so, as you know, the time is leading that the discovery of the FRB numbers, and so that is a huge sky coverage and from the cosmic antenna and increase that the FRB detection ability, especially in the nearby FRBs. And so for the nearby the FRBs, and so we can easily to use a multi-wavelength telescope and to do some the information and from the nearly the source. And so I think the cosmic antenna and will be work powerful. Thank you.
Great. I think in the interest of time, we do need to move on, finish. So thank you again, Pai.
Thank you.
And just thank you again to all our speakers again, and to those who have joined us remotely. We don't see them in the room, but we do recognize that they are here. We continue again tomorrow. There's a poster session for the session again at 10 a.m. and then our session continues at 10:30 in the morning in this room. So thank you all.